My name is Andreas, and in this video we'll build out a fully functional ElevenLabs clone. Settle into a comfortable position and gently close your eyes. As you just saw, I am able to put in text, generate audio in my voice, and download the finished clip. Let's try out the voice changer feature.
Some call me nature.
First we select the audio clip we would like to convert from, and then we convert it to my voice. Some call me nature. Others call me Mother Nature. In the video, I'll show you how I fine-tune the model to my voice and also self-host the model instead of relying on external APIs, but we can also use other voices.
Some call me nature.
The AI models used are popular AI models on GitHub, which we'll fine-tune and host on an EC2 instance. Let's just try the last voice as well.
Some call me nature. Others call.
We will also build out a sound effect generator where you can describe any sound you want and then the sound will be generated. Under our examples, let's try and pick the heavy rainstorm. Here is another example. This is forest ambience. All our previously generated clips can be found and played under the History tab. Settle into a comfortable position and gently close your eyes. Take a deep breath in through your nose, filling your lungs.
Some call me nature.
Some call me nature. Others call me.
The clips are stored in an S3 bucket on AWS, and you'll learn how to upload and download files with pre-signed URLs. We will also build out neat features such as a play bar that you can minimize and still see the audio progress on, as well as a sidebar that can be pinned and unpinned. We will also build out a user system where users can create accounts and log in. Users start with 10,000 credits and have credits deducted every time they use a service. They are able to see how many credits they have left on all feature pages. Everything is of course also mobile friendly, and sidebars are turned into drawer menus or menus that slide up from the bottom of the screen. The first half of the project consists of getting 3 popular AI models up and running. We will prepare our fine-tuning dataset and make Docker containers for training the text-to-speech and the voice changer model. After uploading these to AWS Elastic Container Registry, we'll pull them down to an EC2 instance with an NVIDIA GPU and train the models. We will then create an API for each service, use the fine-tuned model files, and host the AI APIs on an EC2 instance using Docker and Docker Compose. To prevent the EC2 instance from being overloaded, we'll set up a queue system using throttling with Inngest. This way, if a user generates more than 3 times in a minute, the requests are queued for processing when demand is lower. In the Inngest dashboard, we can see the status of the audio generation jobs in the queue and the status of each step in our function. Being able to handle user demand is critical in production-ready apps, and I'm sure it'll come handy for you later in your career. Throughout this project, you'll touch on many modern technologies like Docker, AWS, Next.js, Python and FastAPI. You'll also learn how to work with other people's existing GitHub repositories. Before we start this video, I want to say that my voice is not for public use, so please don't copy or train models with it. On the Hugging Face datasets page, there are many voice files which you can fine-tune on, like these ones for example. You can download a dataset by clicking these 3 dots and cloning the repository like this. So, let's get started with the project. First, I would like to give you an introduction to what we are building and how it works. So, for the backend part of the project, we'll build 3 separate features. We'll build a text-to-speech, we'll build voice conversion, and then also text-to-sound effects. So, text-to-speech we'll build with the model called StyleTTS2, which is an existing model. So what we'll be able to do here is input some text into the model, such as "Hello, my name is Andreas," and then the model will output an audio file with the audio saying that in my voice or another voice that I define. The model comes pre-trained on a bunch of different voices, but what we would like to do is to fine-tune this model to a specific voice, which is my voice in my case. And you can of course fine-tune it to whatever voice you would like to fine-tune it on as well. Second of all, we're going to work with voice conversion. We're going to use a model called SeedVC. So with model conversion, you give the model an existing audio file with somebody speaking, and you can then convert that audio file to another voice, so you basically convert between different voices. And this model file, which we can access from the repository, of course also contains a bunch of different voices it has been trained on, so we can convert to those voices. But if we wanted to be able to fine tune to a specific voice, such as my voice or a voice you would like to fine tune on, you'll have to provide some audio for that as well. And I'll use about 10 to 15 minutes worth of audio. So I'll fine tune this to my voice in my case. Then lastly, we'll work with a text to sound effects model. And this model is going to be called Make an Audio. This is a model also on GitHub. And we won't really require any fine tuning for this model in particular, because we won't really be working with voices. It's more, you can give it a text such as birds chirping in the woods or something, and then it'll produce an audio file with the sound that you described. So it doesn't really make any sense to fine tune this on any voices, for example, because which voice would you want to fine tune it on? So as I wrote down here, all of these models have existing model files trained by the researchers who made these models. So although fine-tuning is possible, it is definitely not required. So up here you can definitely just generate some speech from some text to a voice on one of those listed in the repository. But to make it even more customized and also a little bit more of a difficult challenge, we would like to fine-tune it to a specific voice. That way we can also learn as much as possible. So when the researchers built out these models, they of course also trained them to do benchmarks on the models, and they made a lot of these model files public. So that's why we can just download these model files from the repositories and then use those as part of the models, just as a fully workable model basically, with both the model architecture as well as the model files that the model has been trained on. Contains the trained model. So what we'll do in our case for the backend is to use self-hosting. So when self-hosting these models, what we're doing is basically removing all dependencies from external APIs. So what you could do, for example, if you wanted to do text-to-speech, is to use an ElevenLabs API. So if you wanted to do that, you'd probably pay per use or per megabyte uploaded to the ElevenLabs API, and then get something back in return, such as the generated speech. But after finding these models ourselves and then also training or fine-tuning them ourselves and hosting them on a server that we own, we will be able to remove the dependencies to these external APIs, such as the ElevenLabs API. So this also means that you can fully customize how everything works, so you can fine-tune it exactly how you would like to and get around any constraints that ElevenLabs API might have, for example. But it also gives you the drawback of having to update things manually. So for example, if you use the ElevenLabs API, they would just make updates regularly to the models and to the API in general to make it better over time without you having to do anything, as long as you just use the API that you always used. But if you do this and self-host it like we're going to do, you'll have to do these updates manually. So those are kind of the pros and cons with self-hosting these models. So another plus for our use case with fine-tuning and hosting these models ourselves is that we'll learn how these model APIs or AI APIs actually work. Because what ElevenLabs basically do is just take a model like this and host it themselves, and then they expose an API where you can probably also do fine-tuning through the API. So ElevenLabs are basically just doing what we're trying to do in this video. So you will learn a ton about self-hosting AI and how you can do that efficiently in this video, which will be very, very valuable if you are planning to work with AI in the future, for example. So picking out these models specifically, you can do by going to GitHub. So all of these are open research projects that has just been made. It's probably papers for each of these. And then you can go on GitHub and then find models and then look over the papers, like how is the model performing, for example. And then you can see the GitHub repositories for the specific implementations. So when finding models on GitHub, you probably need to know kind of what the model should do. So if you want text-to-speech, you can go look up text-to-speech models on GitHub. Then you can look at the popularity of the repository, so how many stars the repository has. And also how does the model perform. You can look at the benchmarks either in the paper itself or just from the general sentiment of the model. Maybe you search on Reddit or Quora or something like that. You can also look at whether the model should be able to be fine-tuned or not. That is a pretty important requirement. So if you want to fine-tune the model, because it doesn't do zero-shot well enough, for example, you might want it to be able to be fine-tuned. So that is also something you should look at when checking out some of the model repositories on GitHub, and also how hard it is to get to run. So I'm using a MacBook, for example, and on my device, I don't have a graphics card. So these models should be pretty easily able to run on a CPU without me having to change too many things. But some repositories are pretty messy and have hard-coded devices, so the authors have basically just specified a bunch of times in the code that the model is set up to be run on a GPU, and then you'd have to go in and manually change all of these definitions in the code. So sometimes model can be very hard to get to run if they haven't been made in a proper way, basically. So that's why you should also check out how hard it is to get the model to run on your computer specifically. If you have a graphics card and run on a Windows computer, it's probably a bit easier for you to get some of these models to run locally, which is very nice for testing. So basically, if you want to find a text-to-speech model, what you can do is hop on GitHub. So this is what I've done. So I went on GitHub and then I searched for text-to-speech. And then we can kind of see what comes up. So a bunch of these models are text-to-speech models. So we would like to work with Python in specific, so we can then find out some different models. So converts text-to-speech in real time. It has 2,500 stars, which is kind of cool. It was also updated 3 days ago, which makes it pretty recent. That might be another argument for using this model, for example. Then what you can do is just go into the repository's README, like you see right here, scroll down and then see whatever the model is able to do. So scrolling down, you can probably see whether it's easy to install and use, and also how hard it is to use right here. So quick start, and then maybe you can see whether you can fine tune it or not. So if you search for fine tuning or training, it doesn't look like you can easily fine tune this model, or at least it doesn't have anything specific in the README about it being easy to fine tune the model. So this one might be not as good for candidate as the models I've picked, for example, because it's not as easy to fine tune. So after going through a bunch of these models, you'll probably get a list of models where you can pick from. And the one that had the best sentiment online, to my research at least, was the Style-TTS model, or Style-TTS2 model. So that is why I picked this model in particular. So when figuring out which models to use when self-hosting, this is a great approach. Just look through GitHub, find models that are popular, that has maybe been updated recently, and then live up to your requirements. So if you want to be able to fine tune it, if it can run on your computer even. So that is how I picked these models in particular. Great. So the next part I would like to talk about is how we're going to set up all of this on AWS. So we are going to create an API containing these 3 features, and then we would like to set that up on AWS, which is going to be the cloud provider for us. So what we're going to do first of all is to use EC2 instances, which is just cloud computing instances, so virtual machines with large graphics cards to do the processing. So we're going to do a couple of different instances. We're going to do an instance for fine-tuning, and then we're going to do an instance for deploying the models as well. And for both of these cases, we're going to use a model with the G5.x large machine number. And what this means is that we just have a large NVIDIA graphics card available. So to use this large graphics card, we will have to go in under quotas on AWS and then apply for 4 virtual CPUs. And I'll of course go over how to do this later on in the video. So after applying for this, we'll probably be able to create the EC2 instances. We'll need a fine-tuning instance first of all, where we can run the fine-tuning jobs. And then after fine-tuning, we close down this instance, and then we can deploy the deploy the model on an instance that also has a large graphic card. And then we can expose ports down here, so port 8000 to 8002, so a port per feature over here, per API. And then we should be able to call this API from anywhere on the internet. And then we of course also allow HTTP. So we have the EC2 instances for deploying the models, and then we'll have an S3 bucket, which is just storage in the cloud. So you can think of this as your local file system just in the cloud. So we'll create a bucket called ElevenLabs clone. Inside this bucket, we'll store a couple of different things. We'll store some of the model files, which we train over here in the fine-tuning instance. So when we fine-tune a model, it'll produce another model file, and we'll upload this to the S3 buckets, such that we'll be able to store them somewhere, basically. And then later on, when we do deploy the instance, when the model runs, for example, so over here with the text-to-speech, when you give it a text through the API, it'll generate an audio file, and this audio file will have to be stored somewhere so we can show it to the user. So this audio file will be stored right here in the Style-TTS2 outputs. And we'll create a folder inside this bucket for each one of the models, which we would like to store the outputs for. And then lastly, for the voice conversion, what we'll do here is upload a file to the S3 bucket, which the voice conversion model will then be able to pull down the audio file from, convert the voice, and upload it back up to the S3 bucket. So that is why we have this seed VC audio uploads as well. So this will store the uploads, which we'll use as the source for converting the voices. And then whatever voice conversion was performed will then be stored inside the seed VC outputs right here. So that is what we're going to use S3 for, and how the structure is generally going to look. Great. Then we'll use a service called ECR. So this is Elastic Container Registry. So how we're going to work with these features over here is basically with Docker files. So we'll be able to test out the models locally, so set up how the model should train. We'll then package that into a Docker file, so an isolated and local environment, and then we can then take these Docker files and push them up to a registry, which stores the Docker files, and then we can run these Docker files on the fine-tuning instances or the deployment instances. So we'll need a fine-tuning registry for the style.js and an API registry as well for the style.js model. And then we'll also need a fine-tuning registry and an API registry for the seed VC model, or API, sorry. And then also just an API registry for the Docker files for the make a sound model as well. And this one we are not going to fine-tune, so that is why we'll just create the API registry as well only, and then not the fine-tuning registry. Great. And the last service we'll use on AWS is going to be IAM. So first of all, we're going to create two things. We're going to create a user and then also a role as well. So whenever we create an EC2 instance over here, either a fine-tuning instance or a deployment instance, we'll need to give this instance up here access to a couple of different things to be able to work properly. So remember how we're going to save the models somewhere in the cloud. So after fine-tuning, we'll have to upload the models to this S3 bucket. Well, we'll need to give the EC2 instance access to actually do that. So we can attach a role to the EC2 instance which we create. We'll call this role something in the terms, or something in the likes of ElevenLabs clone EC2, and we'll give it permission to have full access to the EC2 container registry. Also give it full access to S3, and then we'll give it access to the specific bucket over here as well. So this means that this EC2 instance will be able to pull down Docker files from the ECR registry. So over here, the ECR registry, and then we can run those Docker files. And then whenever these Docker files do run and need to upload something to an S3 bucket, it also has access to be able to do that. So that is why we need to give these two instance this role, or attach this role to these two instance to give it permission to do the things that it needs to run functionally, basically. Another thing we'll need to do is also create a user. So whenever we want to run inference with the deployed models, we'll need to be able to upload an audio clip, for example, to the S3 bucket. So whenever we use this voice conversion, we'll need to upload the voice we are converting from to the S3 bucket, so we can convert from that voice to another voice. So to be able to do that, we'll need to create a user that is allowed to list, read, and write from the S3 ElevenLabs clone bucket. So that is why we need this user as well. So this is basically the services we're going to need for AWS. I'll go more in depth and also set up all of this with you later on in the video. This is just so you have an overview of how the basic architecture of the system is going to be set up. Great. So moving on to fine-tuning. What is it actually we do whenever we fine-tune? So hopping back over here to the features quickly. So let's say we have this text-to-speech model. Well, some researcher made this model and then built the model architecture and then trained it on a bunch of data to create a model that works generally for everybody. And then it has been trained on a bunch of voices. So it works for some voices, but if you want to use your voice specifically, or a voice like Obama's voice, for example, you'll have to fine-tune the model to that voice specifically. So what you'll need to do is fine-tune the model. So you take this more general model, which was made by the researchers, you then give it some specific data to learn, and then you get an updated model file out, which is modified to your use case. So you have this existing model file, then you run it through an EC2 instance or some computer with a heavy graphics card that can do some of the compute, and then you get a model file out of that. So that is basically what fine-tuning does, and this allows you to have a model file that is customized to your use case. So down here, right, when you fine-tune, you use a pre-trained model. So what you could also do is just take a model and then train it from the bottom up. So that is what these researchers did, and then train it on the specific data you would like to train on. But that really isn't a very good idea, because the amount of data you would need to actually train it to work perfectly, like this model made by the researchers does, is a lot. So you'll need to run the training job for maybe multiple weeks if you want it to work as good as the one that the researchers did. So when you use this pre-trained model and then just only fine-tune it on specific data, you can do it relatively quickly, which means that you use much less resources and you take advantage of the things that has been done before you, so you build on top of other people's work. And these researchers, when training the initial models, probably also took a bunch of specific choices and had a bunch of considerations when training this model to make it as good as possible. And it's very unlikely that you would be able to do it even better than the researchers who came up with the model architecture. Therefore, you really benefit of using this model that experts trained before you. So that is why fine-tuning instead of training models from the bottom up is usually a very good idea, unless you want to train a specific model that doesn't really exist yet. Another good point for using fine-tuning instead of just training a model from the bottom up is that text-to-speech, for example, is a kind of a large model with a bunch of components to it. So it knows, for example, both how to convert text-to-speech, like that is just one little part of the model, and it also knows how to use different voices inside the model. So what we're really interested in is just how to use different voices, because we want to use another voice that what it is currently capable of doing. But the logic of how to convert text-to-speech isn't really something that we're very interested in because it works already, right? So we're only interested in this part, and then we can fine-tune the model, this part of the model only, because this part already works fine. So that is basically what I mean when I say you benefit of using the model that experts has trained before you. And then another thing I wanted to talk about as well is that for this project in specifically, training should cost about $5 to $10. So if you do it perfectly with no errors or anything, it probably costs a little under $5 for fine-tuning these two models. And then it can cost up to $10 if you experiment a little bit more, try some different voices, etc. So this model is called G5.xlarge on AWS. And on demand for an EC2 instance, it's about $1 per hour. So fine-tuning would take about 5 hours for fine-tuning these two models, which isn't a lot, so you can do it pretty cheaply. And that is because we have these huge models, which we only need to fine-tune on a little bit of data to actually become very good for your use case specifically. So taking this text-to-speech model, Style.TTS2 in specifically, what you will need to fine-tune, or I found at least, is that if you have 10 to 15 minutes worth of audio in high quality, so studio mic like the one I'm using right now, for example, you can get some pretty nice fine-tuning results out of that. So what you would like to do is teach the model the relation between the transcription, so some text, and then the audio that comes out of that text. So right now, I'm talking, for example. So if you take my voice and transcribe that, then you'll have the text, and you'll also have the audio, so the speech, and then you can teach the model the relation between those. So you'll need to take some audio you would like to fine-tune the model to, and then you can take the transcription of that audio. You can then take that audio and segment it into parts of 1 to 10 seconds, which is what the model has been built for. And then you can fine-tune with that data. You'll also need to prepare a couple of things before the fine-tuning job, such as the specification, or specifying what is going to be the validation data and the training data. And there's actually a repository that is pretty close to the Style.TTS that has been made specifically for Style.TTS 2 for fine-tuning, which will handle a lot of this for you. And we'll use that repository so you can see how it is supposed to be done actually. Then when we're going to train the seed VC model or fine-tune the seed VC model, we're going to use the same 10 to 15 minutes of data which we used up here for the Style.TTS 2 model. The only thing is that speaker labeling is not required. So up here you need the transcription and then also the audio. Well, down here you just need the audio files. And that is actually all the model needs to be able to fine-tune to speaking with that voice specifically. So that is a little bit simpler to fine-tune than the Style.TTS model up here. So you'll be able to learn from two different cases of fine-tuning, which are probably pretty common if you want to work with self-hosting AI models. Great. So here's how a fine-tuning job kind of works. This is just a pretty simple diagram I drew. So I told you that we're going to use an EC2 instance for the fine-tuning job. So we're going to first of all build a Docker image that contains how the fine-tuning is supposed to work. And when that Docker image works online or works locally, we won't be able to train it on a local machine probably, because unless you have a very strong GPU, you'll not be able to run the fine-tuning on just a CPU or weak GPU. So that is why we define how the fine-tuning is supposed to work on the local machine. Then we push it to this Docker container registry, and then pull this Docker file down to the EC2 instance, from which we can run the fine-tuning job with a heavy GPU. Great, so that is kind of how it goes. So hopping back down here, we first of all build the training Docker image locally. So we'll build a Docker image called something in the likes of style.tts2 fine-tuning. This will contain the original repository files from the GitHub, also the dataset, and also a Docker file for how this Docker container is being built. So I want you to remember one thing as well, that is for this Docker container, we'll bake the dataset and also model files into the Docker image. So you have a couple of different options right here. Because you build this Docker image as a Docker container, so you can just take the dataset and build it into the Docker container, which will make the Docker image take up more space on your computer and be harder to move around. But you can also do another approach where whenever you start the Docker container, it then pulls the dataset and also model file from external sources, which takes more of a setup, so there's more overhead, but at least it'll do that automatically for you. But to keep things as simple as possible, we'll just take the dataset and model file and bake it into the Docker container, such that we can just ship this Docker container right to ECR with as little work as possible, and then start up the Docker container whenever we're on the EC2 instance. So that's the pros and cons I wrote down here for baking the dataset model file into the container. So we can ship the entire image as one runnable package. So you can just press start on any computer and in any environment you want. But of course, it also takes up more space, the Docker image and container, because the dataset model file is baked into it, and then it builds way more slowly, and also pushes to the ECR registry and AWS more slowly. It's also harder to modify because every time you want to use another dataset, you'll need to rebuild the Docker container and then push that onto the ECR registry again. Alright, so after building this Docker image on a local computer, what we're going to do is upload this to ECR, so Elastic Container Registry, where we have created this repository called style.tts2 fine-tuning. So that is what contains all the Docker images that we might want to use for fine-tuning this specific model. What we then do is start up a new instance of type G5.xlarge on EC2, which is the service for running virtual computers in AWS. We can then pull this image down from the ECR registry to the EC2 instance. So we pull this down and then manually start the Docker image. And because everything is baked into it, we can just start it up right away and then start the fine-tuning job. When the fine-tuning job has finished, we can then take the fine-tune model, so the file that it produced, and then upload that to an S3 bucket, so the one over here. And then after that, we then terminate the instance because we don't need this instance anymore, so we can then save that money. After that, we can then take this fine-tuned model, download it down to our local computer right here. So we download the model file from S3 down to our local computer, and then we can try it out on a local computer by running inference with this new model file to see how well it performs. So that is going to be the basic flow of fine-tuning models that we're going to follow. So because we're using the Docker technology, I would like to explain a little bit more about how that works, just so you have an idea of why we do use it and why it's smart. Alright, so with Docker, you can imagine that we're running a virtual computer on the computer we're currently at, for example, wherein the operating system is Linux. So right now I'm running on macOS, but if I ran a Docker container, I could run Linux inside my macOS and then do some actions inside that virtual computer that wouldn't hurt my environment at all, so macOS. So this allows you to run a bunch of different things inside an isolated environment. And you can then take that virtual computer or isolated environment, ship it over to another computer, and then run the exact same thing on that computer without having to worry about it having any kind of impact on that computer's operating system. And this way of doing things eliminates a bunch of problems actually. So here's one of the problems that Docker eliminates and is very good at fixing. So one of the problems is that if we have a package that we need, so we need the same package, but in different versions for different libraries, for example, that could then be a problem. So if I'm on macOS and I have these three models that I want to work with, and style.tts2 requires PyTorch 2.6, this one requires 2.3, and this one requires 2.2. If I then have one environment, I can only install one version of this library with pip at a time. So I can install this one and this one and this one. It just doesn't work that way, so I'll only be able to run one of these, otherwise I'll have to change the two others to use the same package version. And that is obviously super annoying, but that's just the way it is. So if you have a shared Python environment, so just a single operating systems, you can only have one version per package. But instead, if you use Docker and create a Docker file for this one, a Docker file for this one, and a Docker file for this one, it's actually like having 3 different operating systems at one time. Because what they are is just isolated environments. So you can take style.cts2, put them into a specific operating system, install the package that needs. You can do the exact same for this package, for this model, and also this model over here. Then you can take these 3 Docker containers, ship them over to another computer that has a bunch of different setups basically. You can then run those same Docker containers, and it will work because it's just an isolated environment that'll run the exact same regardless of what parent operating system it has been running on. So that is what we can use Docker to fix. So inside Docker, you first of all specify a base image. So this is what I mean by Linux. So it always run on Linux, a Docker container, but you can specify specific Linux base images. And based on which one you choose, it'll pre-install drivers, dependencies, such as PyTorch, for example, and a bunch of different things. So you can install a Docker container. You can create a Docker container with a base image that is perfect for setting up a Node.js server. You can also set one up that is perfect for training an AI model with PyTorch already installed. So there's a bunch of different base images that you can use to install the exact dependencies that you'll need for your specific use case. And then if you work with Python, for example, you can list all of the dependencies you need inside one file, so requirements.txt, and that is just going to be all the different pip packages you will need for the Docker container to run successfully. And then whenever you run the Docker image or build it, you specify that it must install all of these different requirements whenever it's been built, and then it'll do this automatically for you instead of you having to do it manually on the computer that you wanted to run it on without Docker, for example. And then because you have this Docker container, which now has a specific base image and Linux, and then also all the dependencies installed from a specific file, you then have an isolated environment that'll run the same on all computers, because these dependencies and these drivers and dependencies will be there regardless of what computer you're running it on. So that's why I wrote, when a Docker container has been built, it can run on any system with Docker installed, your local PC, a PC in the cloud, such as an EC2 instance, or maybe even your friend's PC. So that is the power of Docker. You can then also specify what resources the container should have available. So you can say, it must only be able to have this much gigabytes of memory allocated, for example, or it shouldn't be able to use the graphics card, or it should be able to use this many graphics card. And then also, if you mess up a container badly and break everything, so if you destroy the operating system, you can just create a fresh new instance and it won't hurt your operating system at all. So everything has been isolated, and you can specify how much resources the Docker container should have available. And then another thing that is very important is that you can scale very easily. So imagine you have a Docker container running an API for some specific computer program. If you want to be able to handle twice as many calls to that API, you can just create another EC2 instance and then just put the exact same Docker file on that EC2 instance, and then you'll be able to handle twice as many API calls. So you can see the power in being able to scale this way, because you have to find everything and how this API should run. You can just recreate that entire setup on another computer and just do that as many times as possible, basically. Or you can orchestrate it with something like Kubernetes and then scale very easily with that. So in our specific use case, the reason it's very smart for us is that we can define how a training job should work on our local machine. So we set up a Docker container that starts up a training job. And then because our local machine won't have any graphics cards available that are strong enough or powerful enough to train these or fine-tune these models, we can then take that Docker container, ship it up to an EC2 instance, so we send it to a computer in the cloud with a powerful GPU, and then we'll knowingly know that the Docker container will work because it's an isolated environment. So that is why we need Docker containers in specific. So now that we know a little bit about fine-tuning and then also how we use Docker to accomplish some of this fine-tuning, we can then take a look at how we're going to deploy the API once the model has been fine-tuned and we're ready to test out the API. So as I wrote over here under EC2, we'll need an instance for training, and that is just going to be a one-off job where we do the fine-tuning and then shut down the instance. We'll also need an instance for actually deploying the model. So that is an instance that'll just host the API, and that is what I'm talking about or referring to right over here. That is that instance. So because we need a powerful GPU to run these inferences on the model as well, we'll use the same instance, so G5.x large. And then inside this instance on EC2, we'll run something called Docker Compose. So for each of the models we would like to be able to access through the API, we'll create a Docker container with an API so you can reach that model and then run inference with that model through an API. So we'll take this model with the updated fine-tuned model path, model file, wrap that in an API so you can make a HTTP request to it, such as get and post, for example, and then we'll wrap that inside FastAPI so we can then access that model and run inference on it through a specific port. So we'll do this for each of these models. So this one will need some specific versions of packages, the same for this one, and the same for this one. That is why we package them up as 3 different APIs. And then instead of starting up these Docker files, Docker containers manually, we can use something called Docker Compose. And that is also another product made by the Docker people. And this allows you to specify which Docker images you would like to run. And then this will then orchestrate the starting up all of these Docker images simultaneously and keeping them alive, etc. And also managing the logs for them. You can then also control things such as injecting environment variables into each of the containers and a bunch of different stuff that you would expect from a service that orchestrates different Docker containers at the same time. So we'll expose the API for the StyleTTS2 API on port 8000. For this one, we'll expose the API on port 8001, and for this one 8002. So we'll have 3 different APIs on 3 different ports, and we'll then expose these ports over here. So right here under EC2, we'll create the deployment instance, and I'll allow TCP from anywhere, so anyone who might want to connect. And then we will expose the ports 8000 to 8002. So 8000, 8001, and 8002, allowing us to connect to the API. So that is how we're going to connect to the APIs once we actually do the deployment. Great. So that will run the backend for us. And then what we'll do is build a front end and run it on Vercel in a Next.js application. This is going to be a Next.js application right here. This will then be able to connect to the EC2 instances EC2 instance through its public API. So any EC2 instance will have a public API, which we'll be able to use to send requests to it. And then if we connect to it through port 8000, we should then be able to reach the API right here, which will be text-to-speech. We'll then be able to do the exact same thing for voice conversion by sending a request to that API through 8001, and the same for text-to-sound effects through a IP at 8002. So that is the basic setup we're going to use to deploy the backend, as well as the frontend with Vercel, and then reach the backend. So with the backend and then also the frontend deployed, I'll just want to talk about how we're going to set up the flow for actually doing the text-to-speech in the deployed applications or in deployed application. So this will give you an idea how it works in production environment when it's fully deployed end to end. So I have a column right here for everything that will happen in the front end, and I also have a column over here for anything that will happen in the backend. So that is why it's divided up in this way. So the first thing the user will do when wanting to run text-to-speech is probably go to the front end and enter the text. So the user might say, I would like text-to-speech on hello, my name is Andreas, etc. And then the user might select a voice as well, and then press a button called generate. We'll then make a request from the front end to the backend. So an HTTP request. Now the arrow turned around. So we'll make this HTTP request from the front end to the backend. So from Vercel over to the API that's deployed on the EC2 instance. And then because it is text-to-speech, we'll reach the API on port 8000 right here. The backend will then receive this request and run model inference through this StyleTTS model based on both the text and also the voice that has been selected. Both of these things have been included inside this HTTP request. I'll just copy this arrow down again. After doing the inference, the model will obviously generate an audio file with the speech that has been generated, and the program will then take this audio file and upload it to an S3 bucket. So this is a generated VAV file like this. So we take that file, upload it to an S3 bucket right here, and then what we'll be able to do is return a response. The arrows are getting a little bit messed up right here. So we'll then return the response back to the front end. So that is just the HTTP response. And then this will contain a link to the S3 item, which we've just uploaded over here. So every item in an S3 bucket has a specific link to it, which you can use to access the file. So we'll return a response back to this one which will then be able to fetch that same item from the S3 bucket through this link that has been returned to it from the backend. So we can then also take that audio file and play it from the S3 bucket back here in the front end. So that is how the simple flow is going to work in the text-to-speech function with text-to-speech functionality. Great. So moving on to text-to-SFX. It's SFX right here. What we'll do is first of all insert text. So you might say a roaring tiger and its cubs, for example, and then you'll insert that in the front end, and then you would like an audio file to be generated with those sounds, and you can then press generate to have that sound produced for you. So what we'll do now is then also take that information, so basically just the text, send an HTTP request back to the backend. This will then be port 8002 because that is where we host the voice conversion model API on, right there. Going back over again, the model will then run inference with the text-to-SFX model, generate this audio file, upload it to S3. S3 will then return information about the file back to the backend right here, and the backend will then be able to send the link as an HTTP response over to the frontend containing the link to the S3 item, so the generated audio file. And the frontend can then take that audio file and play it from S3 by downloading it from S3 and down to the frontend right here. So that is going to be the workflow right here instead. So this will be pretty similar to the text-to-speech because you enter some text and then an audio file is being generated for you. So the last thing I would like to talk about is the voice conversion. This will be a little bit different. So in voice conversion, you upload an audio file and then the service will then convert that voice to another voice. So first of all, you need to take your audio file and upload it. So whenever you upload that audio, it will put that audio into an S3 bucket. So that's why I've made an arrow over to the S3 bucket right here. So that's going to be the first step. You then select a voice and press generate. Whenever you press generate, you'll send an HTTP request from the front end over to the backend. You'll then reach this voice conversion service on port 8001. This backend service will then first of all download the voice that was uploaded over here down to the backend instance. It'll then perform inference with the voice conversion CVC model. So it'll take the the audio that the user uploaded, convert it to another voice, and then generate this VAV file and then upload this to the S3 bucket. Again, we'll then just send that link to the S3 bucket item back to the frontend, which can then download the item from the S3 bucket and then play that audio sound. So that is how it is going to work with voice conversion. So we have this another step of uploading the audio, which will then be fetched from the backend over here as well. So these are the three different features we'll do and the basic flow of how they'll work in production. And then you might think, well, how do we store each user's history of generated clips, for example? So one option you have is that right here on the front end, you can send an ID of a user over to the backend, and the backend then associates that user ID with the specific generated audio file over in the backend and saves that in a database. That is one option. But another option that's a little bit more simple is what we'll do right here instead. So if we actually take a look at Next.js and how it works, Next.js looks something like this. We have a Next.js client. We then have a Next.js backend. So that's the Node.js backend, like this. And then lastly, we have our API backend on EC2. So whenever you talk about Next.js, you actually talk about these two things. So Next.js does contain both a frontend in React and also a backend. So we actually have to manage both our own backend with Python and then also this Node.js backend, which we can use to do some things that the user shouldn't see in the background, basically. So what we'll do is whenever a user generates an audio clip, a spinner is shown, we'll then send a request from the frontend, so the client right here, to the Node.js backend, so the Next.js backend. We'll then make a request from the Next.js backend to this Python backend, so the service over here. This will then do the model inference and then generate the audio file, upload it to S3, and then it'll send a response back to the Next.js backend. And none of this logic right here will be seen by the user. The user is only able to see the client over here. So what is this box? So we can then take that audio that has been returned from the Python backend, save it to the database in the Next.js backend, and then return the reference to that audio file to the frontend right here, so the client down here, and play that for the user. This means that we'll both hide the request to the EC2 instance from the user, making the instance less likely to be abused. So if we just took the front end right here, made a call directly to the API on EC2, the user would be able to to see the request on the network tab. So if you press F12 and then press network, you'll be able to see any requests being made by the website from this website to any external APIs or image fetching, etc. So you'll be able to see where we call from, so the website, and also where we call to. So you'd instantly be able to discover where our API instance is at, and then also make it less secure because more people know about it. So we can kind of conceal this API by just running inference on the API, and then also just calling the API from the backend instead of the front end. And we'll also be able to take this reference to the audio file, which has been returned by the Python API, and associate with the user in our Next.js backend instead of having to do it on this EC2 instance, because that would mean we would need to install some way or some library to interact with the database on this EC2 instance as well. So it's much easier to do it right here, or do the database calls from the Next.js backend where we have installed it already. So that is the basic flow we'll use to store the user's history of generated clips whenever the user wants to see a list of previously generated clips. Great. So this was a small demonstration of how the project works, and then also the things you can expect to see within this video and the project you'll build. So to work with these models, before we get started, you should install Python, because that is what we'll work with AI with. So for a lot of these models, if you just install the newest Python version, which is 3.13, I think, you will be able to, or you'll get some errors because these models aren't fully compatible with the new models yet. Also, to be more specific, stuff such as PyTorch might not be able to work completely fine with the newest Python models, or newest Python versions. So what I do usually is just install Python 3.10, because that works perfectly fine with at least all these models. So you can either go to Python install, and then you can download Python. So in this case, you would download Python 3.10 right here, for example. So scrolling down to a specific release, 3.10.15, you can then press download and then follow some installation guide to then install Python. If you are on Mac, you might be able to just use Homebrew. So if you hop over to Visual Studio Code or any place with a terminal, and then just open up a terminal like this, you can then say Homebrew install Python at 3.10, or I believe it's actually brew install Python 3.12 or 3.10 like this. And whenever you have installed Python or a Python version such as 3.10, you should then be able to create a new virtual environment. So right now I'll press Shift Command P and then say Python create environment, and then V in V like this. And then I should be able to, whenever I open up a new folder or new repository, I should be able to see the specific Python versions I've installed on my computer and create an environment with that specific Python version. So that's what we'll do in just a second. But before doing that, I'll just close down this terminal, hop back over to my browser, and then just search for style.tts2 over here. So I'll search for style.tts2, and then I can find the specific repository. So this is the one. And then we can just check out exactly what the repository contains and see if there's any useful information. And I'll just show you how it works in general with looking at these AI repositories. So scrolling down, it says style.tts2 towards human level text-to-speech through style diffusion, adversarial training with large speech language models. And then what you often have is a link to a paper like this, where you can say view PDF. And then you'll be able to see how the model works. So if you scroll down, you can see the entire model architecture. So these models are quite complex and does take a long time or a while to understand, and even longer to be able to build yourself. So that is why fine-tuning these models is often a better option than training these from scratch, because you won't be able to redo all of this logic without being an expert within the field. So hopping back over to this repository, I'll just zoom in a second as well. We can then see a couple of other things. We can see some audio samples. So often when you have these, for example, text-to-speech repositories, these researchers have done some benchmarks. So when you just want to look through a bunch of different models and see which ones fit your use case the best, you can often find some audio samples, which are just like samples from what have been generated with the model, and that way you can kind of find out whether it's good or not. So down here you can see single speaker, and then you can see ground truth.
After the construction and
then you can see style.tts2, so that is how it would sound if this was generated with style TTS2.
After the construction and action of the machine.
So this sounds pretty good. Natural speech.
After the construction and action.
Jets.
After the construction and action of. After the construction and action.
So all of these sounds pretty good, but for some different types of models, such as the text to sound effects, for example, some of them often sound pretty bad. So you'll pretty easily be able to identify which models are good and which models probably aren't worth working with. So that is another thing you should check out when looking at these AI repositories. Great. So scrolling down to prerequisites, we can see that we require Python in a version that's newer than 3.7. So we install 3.10, which is perfect. And it then lists out all the different things we need to work with this model and this repository. So we can then see we are able to do some training. So we can say accelerate launch, train first, and then do a couple of commands to start the training. And then it has a bunch of information, which is very useful whenever you do the fine tuning. So this is training, and this is fine tuning down here. And then when you want to run inference, there's this example right here. So inference, LJ speech, which you'll be able to open up. And then you can run through this notebook and actually do some inference yourself, just to try it out and see if it works well on your computer. Good. Then you can see some license, and that's about it. So we have everything we need. We have some fine-tuning scripts. We then also have inference, and we'll be able to just clone down this repository in just a second and then work with that. Another thing that's important for the style TTS2 model in specific is if you go into discussions and then press notes on fine-tuning, this is a massive discussion right here with a bunch of different people talking about how they fine-tuned the model the best to their specific use case. So if you want to work even more with the style TTS2, you'll be able to learn a ton from just reading through these notes on fine-tuning along with all its comments down here. So one of the things that's especially useful inside these discussions is the VRAM usage right here. So if you take a specific EC2 instance, you'll know exactly how much GPU memory you'll have available whenever you rent the EC2 instance. And you can then see different strategies right here, and then also how much GPU it uses. So instead of having to trial and error your way forward, you can just take one of these existing setups and then see how much VRAM it uses, and then use a setup that's right under the amount of VRAM that you have. So this is very useful. If you encounter specific errors, you can often find them right here under errors and crashes. And if you find something that's not here, you might be able to scroll down all the way to comments, and then you can see different errors that people had and also how they solve these errors. So this is the first model we're going to work with. It is very well documented and used by a bunch of people. So that's why I chose this one. Great. So hopping over to Visual Studio Code, this is the code editor we're going to work with. I'm going to go ahead and say open folder, hop into documents, and then repositories. In here I'll say ElevenLabs clone, and then create. I'll then first of all just press open, just so we have some folder to work with. Great. Now the first thing we're going to do is actually not clone down this repository, but instead another repository that helps us fine tune this model right here. So if we search for, and just delete this, if we search for style TTS2 fine tune, we should be able to find this repository with 206 stars, which is the exact one we're looking for. And as this repository says, this repository provides a guide for how to prepare a dataset and execute fine-tuning using the style TTS2 process. So if we press code and then copy to clipboard, hop back over here, open a new terminal, and then say git clone, like that, and press enter, we should be able to clone this repository down and get the fine-tuning ready. So this will just take a second, and I'll come back in a minute. I'll then just hop back over here and go to style TTS2, so this one, and just clone down that repository as well. Right click over here, open integrate terminal. We can just use the same one actually. Git clone, and clone this one down as well. So now we have the repository for helping us prepare the fine-tuning dataset, and also the repository for actually doing the doing the model inference itself. And now that it is done cloning, I can then say file, open folder, go into ElevenLabs clone, so documents, repositories, ElevenLabs clone, and then I'll just go to style TTS2 first right here, press open, And then we can just test out the model itself to see if it works fine on our computer. So the first thing you should notice is that we have a requirements.txt file right here. So these will be all the requirements we need to install with pip. So we basically need to say pip install and then do all of these to be able to use this model. So we'll first of all say command, shift, and then print. And then we should be able to see this Python create environment right here. If you are not able to see that, you might be able to, or you might have to go under extensions. And then we can just check out my installed Python extensions just to make sure that your VS Code reflects how mine looks as well. So for Python specifically, I have installed auto pip 8. I have then installed Pylance, Python debugger, and that should be it for Python. So if you install those 4 or 5 extensions, which you can just do like this, so you can just search for Python, and then you can install the different ones right here. You should then be able to run the exact same commands I do. So I'll just going to open the command palette. So maybe I need to say command palette right here. If you don't see that, then you can see the shortcut at least for where it is at. And then press command palette. You can then say Python creates environment, v environment like this. And then you can pick your specific Python installation. So I installed 3.10 under homebrew. So this is where my reference is to that installation. I'll then just press enter. I can then select requirements.txt, which will automatically install all these requirements under requirements.txt, and then just say OK. If you aren't able to select requirements.txt, you can say open integrated terminal, pip install -r, and then you can say requirements.txt and press enter. This should do the exact same for installing these requirements right here. And then we'll just wait for these Python requirements to be installed for us. We should now be able to see the environment down here, 3.10.16, so our Python version, and that is the environment we're currently in right now. It should also have created a .venv folder over here containing the installations of all the different Python packages. So now we have our environment, and we then just need to do a couple of more installations. So first of all, if we hop back over to style.ts2, right now we do not have the model files, we only have the architecture of the models. So this defines the shell of how the model should look, so the architecture of the model, but we still need the model files, which is the files that has been trained on all this data by the researchers, so we can actually run some inference with the files. So we should be able to create a new folder called models in just a second, and then put the files into that. So scrolling down, we should be able to see some link to Hugging Face. So inference, under inference, we should be able to use libretts. So the model we would like to fine tune on is libretts. There's also one called LJ Speech. We'll not use that for now. So we'll just use libretts. So the pre-trained style.ts2 model can be downloaded at. So we'll just take this and open it up. And then we can say models, libretts2, and then just download these two. So I'll just say clone repository. And then first of all, just install git lfs. So this is git for very large files. So I copied this command, hop over here, go under terminal, and just paste that in. Then I'll just take this right here, copy it, paste it in right there. And this can take a while. And then lastly, we can just close down this, hop back to our repository. We'll actually also just take this reference audio and install that. So maybe I can say download right there, and then just download that and just put it into this folder right here as well. So I'll just go ahead and do that. So it just finished downloading this large file. It took about half a minute. And then I also took this reference audio.zip and dragged it from my downloads folder and into the style.ts2 repository right here. I'll then just go ahead and say unzip and then reference audio.zip. So I'll just copy this file name, put it in right here. This should unzip it, and then I can just delete the zip file. And now we have some reference audios. So maybe if I press on amused and then press play.
That's what Carnegie did.
This is just a reference audio for when you sound amused. So maybe you want to generate some voice or do some text-to-speech and then have the voice sound like an amused voice like this. And then you can then use this reference audio right here to generate that exact voice. So the voice you would like to generate, you'll have to provide a small clip from. This is only about 3 seconds. That is all it takes. and then you can then run some inference with that. So let's just take these downloaded models files as well and just use them for something. So if I take models right here and just drag models into the root of the repository like that, move, and then under style CTS2 LibreTTS, I'll just go ahead and move this to the trash. And now we have models, LibreTTS. We then have a config file for running inference, and also the model file itself. This model file does take up quite a lot of space. I think it's 700 megabytes or something. So just so you know, this is a quite a large model file. Good. I'll then also just take a reference audio, so maybe Anchor.
Her face.
Or 3, for example.
This is where that line.
5.
Be rational.
He never informed.
So this sounds pretty normal. So I'll just take this and copy it into models, LibreTTS. And then I'll just say woman 1, like this. And now we can use this for running inference, just so we have a single one to use when testing it out. Alright, so now we can actually try and get this model to run, because we both have the model file, the model architecture, and also the demo up here with LibreTTS. So what I would like to do is just create a Python class. So instead of having this notebook, which we can't really execute as an API, we'll need to create a class using all of this code. So we'll need to create a new file. So hopping under, I'll just right click down here in the root, say new file, call this libreinference.py, like that. And inside this, we can then create the model. Create the inference class. So I'll first of all just make this on the right side, and then take this LibreTTS and keep it on the left side. So first of all, I would like to take all of the imports from this demo. So I can say import torch, import it over here, import random, import numpy as np, like that. Scroll down, we have a bunch of imports right here. So I can say import all of these, not import this though, it's not an import statement. That works as well. Scrolling down, I'll just search for import as well. Scrolling down, we should be able to see a couple of more. So down here, that was the one we were already at. We have a phone miser like this. We'll just take this phone miser. It seems like it hasn't been installed, so I'll just hop into the requirements.txt and put it in right there. Press save, and then we can just open up a new terminal. Say pip install -r requirements.txt and just have it install the packages that hasn't been installed yet. So phone miser right here. And I'll just wait for that to finish. Cool. Now that's done, I'll just close down this again by clicking twice right here. Scroll down even further. We have PL birds. And then what else do we have? From collections, order dictionary. We'll import that too. This sampler right here. Let me just see. Do we have anything else? Phone miser, order dict. Yep. Python display. We won't really need that because we won't really need to show anything. Yeah, those should be all the imports we'll need down to the step of basic synthesis. Cool. So hopping back up, we can just start to implement some of the actual logic. So first, I'll just say class style TTS2 inference like this, and just put in an init, so a constructor, so init, and I'll just pass in self as the only thing for now, and just say pass. Okay, cool. Now we have the class. And then one thing we need to do as well is just, if we hop back over to the repository and then hop into prerequisites, we have the repository, we have installed the requirements. We just need to add all of these as well. So what I'll just do is just press copy right there, open up the terminal once again in the root and just say install right here and just wait for this to install as well. Then what I can do is just take this one, so phone miser. So this was the one we just added to requirements, and then also sudo apt-get speak ng. So if I just take this command and just paste it in right there, and then I'll just install it like so, we see that we get apt-get command not found, and And that is because I'm on Mac and not Linux. So what I can do is just take this speak, search for style TTS2 speak Mac like this, and then you can take one of the links, and then if you scroll down, you'll be able to solve errors like this. So you'll need a speak, that's for sure, to use this phone miser package right there, and then you'll need to export something to run inference locally. So first, what I'll do is just use Homebrew to install this speak. If you are on Windows, you'll need to install it in one way. If you are on Mac, you'll need to install it in another way with Homebrew, for example. And on Linux, you should be able to just install it like this. So first of all, I'll just go in here and say brew install and then speak. And then let me just see which one I need to install. So brew install speak like that. And then that should be installed already. And I'll return when it's ready already. So I'll say brew info and then speak. Oh. And now I should be able to see the installation of speak. So right here is the installation of speak. If you're on Windows, you might need to install it in another way. So I would urge you to search for style TTS2 speak Windows, and then you should be able to see how you can install style TTS. Speak. Maybe it's installed by default on Windows. If you do install Phone Miser, I do not know because I'm running on Mac. But if you do get an error with speak missing, you will want to search up how to install speak on Windows. Great. So to use this speak library on Mac as well, you'll need to export a couple of things. First of all, you need to, I think it was on this link right here, you'll need to export this. So if you take the following one right there, and then just go into, I'll just close down this terminal. What I can do is up here, say os.environment, and I can then pass in this. So I'll say phone miser speak library like this. And that should then match my path to where it were locally on my computer. And then hopping back, we should be able to see if we have all the prerequisites. And this is just a dataset you can use to fine tune the model. And we won't really need that right now because we will use our own dataset basically. So hopping back over here, we can then start to fill out the class with the code from the notebook. So first of all, we'll create the constructor right here. And then scrolling down, we see a couple of things. We'll first determine whether to run on CPU or GPU. So I'll say self.device, save this as an instance variable so we can always access it in the other methods. Then I'll say torch.device, and we can then say CUDA, so GPU, if torch.CUDA is available. So if there is a GPU in the computer, we'll then use the GPU to train. Otherwise, we'll use the CPU, and that is what we do with this line right here. Cool. Next up, we have these two lines right here, toml and mean. So inside the constructor, like that, I'll just say self.toml, and then also self.mean, like this, and also self.standard deviation, like that, and just save those as instance variables because we'll need them further down. Then I'll take these methods right here because they'll be needed as well. Put them in as methods. So I'll go ahead and do that. And then also here, correct the indenting. And then right now we have .toml. So I'll say self.toml because we saved it in the instance right there. So right now it says self is not defined. So we'll need to pass down self to these methods because we are now inside a class. We also are missing the preprocess. Device we do have, and model we do not yet have. So scrolling down, we have device right there. That's what we did as the first line. And then global phone miser, we can then hop up to the constructor. I'll just put it in right there. Say self.phone miser is equal to phone miser backend, blah, blah, blah. And then scrolling further down, we see we have this config file. So under models, libtts config.yml. We have this config file which is used for inference. So when you do run inference, it's just a forward in the neural network. So you still need to set all of these different configuration values. So that is what is being done with this configuration file. So we'll just need to load that in. Let me just open back up the demo right there and open that on the second screen like this. Good, so scrolling down to the configuration file, I'll just create a new line right here, say self.configuration, so we could use it multiple times throughout the class, and point this to the config path. So I'll just take this config path and pass it down right now as a property for the constructor. So right here I'll say config path, and then just set a default value like that. If you do not supply the parameter, I'll pass this in right here, and then that should be good. Cool. And then we can create a method down here under the constructor called load models, where we'll pass in self and also model path like this. Inside this method, we'll load the different models. So right here, we are loading all these different models. So I'll just paste these in. And then we can access config by saying self.config right there and right there. And I'll just do the same for this model and also for this model right here. And then I'll say self.config, self.config. And then I would like to, instead of defining it with this many lines, just say self.config like this. And then just pass in the key directly to the dictionary. And then self.config as well. And then instead of ASRPath, we'll just pass in the key right here and just delete these two lines. And I'll just go ahead and do the exact same down here. So this will be F0 path, delete this line. And then I can do the exact same down here as well. And just delete that. Cool. So I'll just fix this typo, pass it down from the constructor as well. So I'll say model path. And then in here in model path, what does it say? I'll just remove this. So make it not optional actually. And then I'll pass model. So you can, when you construct this new inference class, you pass the model path into the constructor, and then it should load the model by passing it down and calling this load models. So what we'll do is under self.config right here, we'll say self.loadModels, pass down the model path. So when you instantiate this class, it'll load the model for you automatically. The next part is model params down here. So if you just search for this, we can see that it's used a lot of places throughout the code actually. So we'll just go ahead and make that a class, an instance variable as well. So under config, I'll just say self.modelParameters, and we can then just switch out this self.config, config with self.config. So like this, and then we can grab the model parameters. Now we can take the model parameters and use that to build the model down here. So I'll take the model, and down here under load models, I'll say model equals build models. The model parameters will be self.modelParameters, and we should store the model on the instance so we can access it in multiple methods as well. So what happens over here next is that we build the main model right here. Then the build model are not containing the weights, it's just the shell of the model basically. Then we move it to the CPU. So if you are doing this on a computer with a GPU, this will be done on the CPU. We'll then move it to the GPU if the device is GPU, and then all the models, all the weights are then being loaded on the GPU. And then we also set the weights to evaluation mode. So what is a better practice is actually loading all the stuff on the CPU and then moving the model plus the weights over to the GPU. Also, this evaluation thing is done, or setting it to evaluation mode, so inference mode, is done twice, and we'll also be able to just do this once. So let's take this build model, and then we'll use that as the first thing. So first we build the model, and then what we do next is just take, let me just see, we have parameters whole. So we'll just load the weights. So this will just build a model shell, Then we load the weights like this. And then we need to use the model path as well. And then the map location is just going to be CPU because we load the weights on the CPU and then move them to the GPU afterwards. Now there's another line down here, which I'll just include there. Then we load all the weights. So I'll just take this entire thing. So right there, paste it in. Just fix the indentation. This will be self.model, of course. Self.model, no errors right here. Then after loading the weights on the CPU, so both loading the model shell and also the weights, so shell and weights down here, we can then take the entire thing and move it to the CPU or to the GPU in a single operation. So I'll just go ahead and say for key in self.model. So what we do with for key in self.model is that we take all the components of the model and loop through those. So the model contains a text encoder, style encoder, predictor, a bird for example, and also a decoder. So we take all of these different components and then we want to set them to evaluation mode. So you can set them to training mode or evaluation mode. And we would like to set them to evaluation mode to prevent any training from happening because that is not what we want to do. So I'll say first of all self.model key. And then we'll set that to evaluation mode like this. And that is the same thing they do right here. We'll also want to move all of these weights to the device. Or the component, sorry. So I'll just say self.model key.to device. And the device will just be self.device, which we defined further up. And that is going to be the CPU whenever you move to a Docker container and move it to the EC2 instance. Scrolling down further, we can then see this diffusion sampler right here. So we did fix the imports. So let me just copy this piece and then just paste it in right here. And just call this self.sampler instead so we can access it in different methods. So basically what we're doing is that all the things we need in other methods than just this single one, we'll just prepend self2. So we'll be able to access it through the class instance. So for example, up here in the constructor, we define self.device because we won't just need it in the constructor. We'll also need it down here in load models and probably also in some of the other classes, which we're going to define later on. So that is why I prepend self to some of the things that we're going to need. And then moving on, we can go down to the actual inference part. So if I just take this entire method and copy it in, we should be able to see how much works already and which parts need some a little helping hand. So first of all, preprocess, we'll just need to prepend self.preprocess. Same for model. Let me just see. Mean, standard deviation. Perfect. And now the error should be gone. Great. Moving down here, I'll just paste in this inference. And let me just see if I can fix the indentations. So I'll copy this entire thing, indent it once by hitting tab. And now we have self.fomizer. We just need to pass in self as well. We are missing the text cleaner though, so we just need to find that. So right here, text cleaner is being defined all the way up there. So if we can import text cleaner from text utils, so we'll just import it right here. We should be able to access text cleaner. So I'll say text cleaner equals text cleaner. Just create a new instance of that and just pass it or just use it right here. Great. Now I can say self.device and just fix this all the places we need to fix it. Model. The sampler, let me just see, we already have that as well. Model. We do have device right here as well. Model parameters, we do have model, device, model parameters, and model. And then I do not see any problems right now, so that is great. Cool. So now that we have the class written out, we can try and go ahead and instantiate it, pass down a configuration path and a model path, and then see if we can get any meaningful output out of it. So initially we just want to be able to run libreinference.py on our local computer. So we can go ahead and just make this file runnable by itself. And we do that in Python by saying if name is main. That means whatever happens whenever we run this Python file, so Python inference.py is what is being defined in here. So I'll just go ahead and say synthesizer like this equals style TTS2 inference. And then for the config path, I'm going to go ahead and say models. So we have models TTS, and there was the config. So I'll just say copy relative path, paste this in, and now we can say model path, and then paste in the model path, which is the relative path as well, right there. Now I'll just say ref style. So this is the audio file we're trying to replicate in the inference. So we pass in the text, but also a piece of audio which we're trying to recreate or trying to get the audio file to sound like. So I'll say synthesizer.compute style, and then I can pass in woman1, for example. You can use anything you want basically. We just define this woman1 or just put it in this folder just so we have something to use. But you can take any of these from the reference audio or just use a clip of your own audio voice if you want to, just to see how that sounds. Cool. So under this compute style, we'll just say generate speech. And we'll do this by first defining the text. So hello, how are you doing today? We can then say audio equals synthesizer.inference. We can then pass in the text, which is just equal to text. So let me just copy this basically, we don't need that. So text, we can then also say reference style equals the reference style. We can then just pass in the alpha, beta, diffusion steps, and embedding scale. And hopping into this, these have already been set actually. So going all the way down, we can just remove these parameters because when they're being set in the following way right here, we don't need to pass them in, they are optional. So removing that, we should be able to run this file and then get an output. And then the output of this will then be an audio wave, which we can save. So I'll say sf.write output.wav, and then we'll give it the audio and then also a waveform. So sf will just need to import. So going all the way up, we just need to say new import. And I'll just say import sound file as sf. And now when we do run this file, it should determine automatically that we are running on CPU because we have a self.device right here being determined by whether there's a GPU available or not. So we might see some errors when running this for the first time. Maybe we have a GPU or CUDA hard-coded somewhere in some of these files and it'll fail. So let me just go ahead and run this file and we can then see what works and what doesn't work, and then we take it from there. So if we open it in an integrated terminal, I'll just remove this, say Python, Libre, inference.py, and because we're in this folder style TTS2, we can just reference the file directly because that is in the root of the folder right here. So if I say enter, and then just wait for it to finish, we can then see what kind of output it gives us. So after running the code, I get this error right here. So let me just scroll up and see what is going on. Failed to load Python image extension. So it's kind of a weird error. See if we can find any information whatsoever. So we see load ASR model, and then it can't decode something. So ASR, if I scroll up, is right here, load ASR model. So let me just see if I go under Libre TTS and just compare how we load these two. So going down to ASR, we have ASR path right there and ASR config. Right here though, we have ASR config and ASR path. So we'll just take these and switch them around and just see if that fixes things. It should have a pretty big difference because you can't just swap parameters like that. So let me just go ahead and execute this again and just see what happens. So scrolling up, we did get an error again. So let me just see where we're at. waits only load failed. In PyTorch, we changed the default value of waits only from false to true, rerunning with or torch.load with waits only. So torch.load. We can then take this, say waits load equals false, and then just save that. Run it again. This is an error you'll often get where you have to set waits only to false. And let me just see where else it says something with waits only. Sorry, torch.load. So inside models, we might want to do that as well. Oh, sorry, it's not a string, it's a boolean. Great, so now we just get another error. So if I just, this comes from models.py. So let me just go ahead, and this is actually exactly torch.load. So if I just set waits to false here as well, and then save and run it again. Let me just see what happens. Okay, now it loads the components of the model, which is great. And then I'll just wait for this to finish and come back in just a second. Alright, so it just finished after about 10 to 20 seconds. Now I see this new output.vav file down here, so an audio file. So if I just try and play this.
Hello, how are you doing today?
We have a female voice saying, hello, how are you doing today? Which is exactly what we expected. So that is great. Now we can run inference locally on our computer. And now we just have to move on to the next part. Alright, so before moving on, I actually just want to do another test. So if I just delete this down here, find another reference audio, so maybe anger.
Her face was against his.
I'll just try and take this, paste it into LibreTTS, and just change this over here to anger. And I'll just run the command again, just to see if it does work with another voice than just a woman's. So it definitely should work, but let's just test it out just for fun. So now it finished already. We see output.audio.
Hello, how are you doing today? Hello.
So that's definitely an angry voice, I would say. So that is perfect. It does work with the different voices, references, audios. And now before we actually do the fine tuning, we can just test out how it sounds with the audio file we would like to fine tune it to, just so we can see if there's actually a need to fine tune it. Because if you have a voice that does sound like some of these voices are kind of the same, you might actually get great results if your voice has the same kind of intonation as the voices it has been trained on. If you do not have a voice that sounds like the voice it has been trained on, you might get bad results, and it might be a good idea to fine tune it though. So let me just try and find a little clip of my own voice, and then just try and test the model out on that to see if it actually works well already. So I've just put a little voice clip of my own voice into the clipboard, and I'll just paste it in right here and erase one. And let me just try and play this. We would like to use the credentials provider like so. So it's about a 6-second long clip. So if I just say Andreas1.vav like this, and just say Python libreinference.py, we should be able to see an output in just a second about how it would sound with my voice. And finish right there. The output will be,
hello, how are you doing today?
So that definitely does not sound like me, and I think that fine-tuning this model would be a great idea for my voice specifically, at least if I wanted to sound like my voice. Alright, so to move on, I'll just open up this other repository. So now we are able to do inference. So this file right here is just going to be able to be used in the future as well when we want to build out the API. Instead of writing this main method, we'll just use this class in the API, and we should be able to build the API from that. Cool. So going to File, Open Folder, and then style.tjs fine-tune instead. We can just open up that, and then just use this repository right here to build out the actual dataset we'll need to create the fine-tune model. So first of all, we can find the README, and then open it up like this, and then we can see how they want us to use this right here. So going all the way down, we just need to create a Python environment. So this is another folder, so we'll create another environment. You can also see that we do not have the venv file or folder up here, so we haven't created a Python environment yet. So I'll just say Shift Command P to open the command palette, create environment, v, and then just use 3.10. Install the requirements as well. And then they do say 3.10 right here actually. So that is perfect. So I'll just come back in a second when this is done installing. So it just finished installing, and then it says this Python environment has been selected, as we can see down here. So now to do the next steps, it says install PyTorch. So let me just go ahead and copy this command right there. Oh, I'll copy the command, paste it in right there, and just let it install. And then we also need to install WhisperX, which is a transcription library, as well as PhoneMiser, PyDub, etc. So I'll just copy the first command first of all, like that, and then just this one as well, which we can install right after. So now that it is done installing, we'll just take the second command, install these 4 pip packages. Oh, and then going down, we can see this new thing called data preparation, new headline. So change directive to a unpacked style TJS fine tune, and then we should see the make dataset folder, which we do see right here. Then we can run this to create the base directories. So this srt segmenter.py is inside this tools folder, as far as I can see. So we'll just open up a new terminal inside that tools folder, say ls, and we should be able to see srt segmenter right there. Cool. So now we can say Python srt segmenter, and it should create some folders. So now we see 4 more folders. Then we need the dataset we want to train on. So for my specific example, I have about 15 minutes worth of my audio from one of my previous YouTube channels, or previous YouTube videos, sorry. You can use any voice you want, but the cleaner the audio, so if you have a studio microphone, for example, the better it is. Another thing to notice is that you shouldn't just use any person's voice and then just use that program in production without they consenting to it. But for my case, I'll use my own voice because I have a lot of recording from that. So please find an audio file. It should be about 15 minutes long, not much more, not much less, and that should be perfect. So what I've done is that right here on my second monitor, I'll find this audio file, put it into audio, and it's actually an MP4 file. So this is just a snippet from one of my previous videos, sample.mp4, and that should load in just a second. So this is just going to be a video clip from one of my previous AI videos. Anyways, so we want to convert this first of all from an MP4 file to an audio file, so WAV, and I'll just write up a command in the terminal to do that. So what I'll do is just open up ChatGPT and then just say, how do I convert an MP4 file to WAV with FFmpeg in the terminal on a MacBook, like that. And then in the meantime, I'll just go ahead and open up this audio file right there in an integrate terminal, and then we'll be ready to use this command. So I have FFmpeg installed on my computer. So FFmpeg is just a library I use to work with audio, for example. And then you can use anything to convert between an MP4 file and also a WAV. But if you do have an MP4 file, you can use a library such as FFmpeg to do this. So if I paste it in, we see that FFmpeg, the library, takes an input, which is the input.mp4. So this will need to change to sample.mp4. This will become output.vav. I'll just run this, and we should see the output right here. So if I just play this audio, when training this multimodal AI model, we see that we have about 16 minutes worth of my audio clip. So that is perfect. Now we have added this VAV audio file to the audio directory, and then let me just see what else it says. Run the following command to generate all SRT files. So what I'll do is just take this for Linux and run it on Mac, and then if you're in Windows, you can just use this one instead. So it is important we are in the audio folder, because as you see, it hops one folder back, hops back into audio, then it takes all audio files inside this folder. So it's also possible to have 2 WAV files if that's what you want. It'll still be able to handle that. So put as many audio files in the audio folder as you want. I'll just use once because that is enough for me. And then we can just paste this command in right here. And what this will do is it'll loop through all the audio files. It'll then say do WhisperX, and WhisperX is the transcription library. So this will get out all the sentences from your audio. And what this will do is then just generate SRT files. So this is just standard transcription files. So it'll just generate the entire transcription for your audio. Now, if I just run this straight away, so if I just do this, it'll take a while to do on my computer, and I'll get an error or two, which we'll just talk about as soon as it is done. So I'll just come back when this is finished. Alright, so it just finished up, and the first error I get right here is the following one. Requested float 16 compute type, but the target device or backend do not support efficient computation. So let me just copy this, and as you can see, it is the Whisper model or library being used right here. So what I usually do when I see an error like this is trying to find out what library even caused this problem. So as we see up here, it's WhisperX, that is further up in the call stack. Then I take this error, and then I search for WhisperX, and then the error. And then we can see an error that matches exactly this. So your GPU does not support floating point 16 execution. So I don't even have a GPU on my MacBook, so this for sure makes sense. Then we can set the compute type to this one or int8. So let me just take this compute type, which is a flag. As you can see down here, it's a flag. Then you can paste it in as part of the command. So if I just take somewhere random right here, put in another flag, compute type, and then say int8, then I should be able to press enter and then just let it finish up and see if we get another error or whether it works or not. Alright, so it just finished up, and as you can see, it printed out a bunch of stuff on the way. So it's pretty verbose, and you can see every single sentence or paragraph it finds while doing this command. So one problem I've previously had when fine-tuning Style.js 2 is that when running this default command right here, some of the transcripts have been overlapping, which is obviously not great because you need very accurate timestamps for your audio to be able to actually fine-tune the model. Your dataset should not be the problem, at least if you're fine-tuning a model. So if I just go under output.srt, we can just check out how it looks and then see if there's anything that seems mysterious about this. Otherwise, we should be able to run another command I know and then fix this. So I urge you to just hop into the output.srt right here, which the terminal command just produced, and just look these through. Just like quickly look them through, see if there's anything that seems suspicious. You can also ask ChatGPT, if you take this entire thing and paste it into ChatGPT, whether there's any overlaps. It might say that there's overlaps of timestamps for about 20 milliseconds, but that doesn't really matter at all. But sometimes I've experienced an error where you see two timestamps starting at the same point. So it would look something kind of like this. So this error has occurred to me multiple times, where you have two timestamps with the exact same start and end time, and that is obviously really bad because you can't be saying multiple things at the same time. So if I just open up this output.vav, we can just test another thing. So hopping over to a random timestamp, I'll just say at 11:39, we can see because the transcript is the transcript of the video. So we'll just test that everything works as it should be. And we can do this by just opening up the output.vav and just verifying that there's no time shifting in the timestamps as well. So I should be saying this at this point. So 11:39. So I just opened up the audio file over here on my desktop. And then if I do play this, and because the transcript and the video is very related, because so what I said was, and because the transcript and the video is very related, so that is at 11:25. So this means that there actually is a problem with my dataset. I should be saying, I went to 11:39 and not 11:25. So it should be having this timestamp instead of 39. So that is kind of a big problem. So what I would like to do is just go ahead and delete this SRT file and then just open up the audio folder again and just run the command with the fix that I at least have found in the past. And by the way, if your audio file, dataset seems perfectly fine, there's no reason to do this because I'll just have to run the entire command again with a different flag. But otherwise, if you do have a problem with your dataset not being accurate, you should definitely do this, because if you train with a dataset that isn't properly aligned, so the transcript is not properly aligned with the audio, you'll get a model that sounds completely off. And the reason I found out this command exists is because I went and searched for WhisperX, and then SRT not aligned with audio, and I searched for something like this, and then just checked through all of the different issues under WhisperX. So you can find the repository right here that we use, go under issues, and then just remove this and just search for timestamped, or you can search for align. So sometimes you'll run into some issues that are kind of hard to fix because you depend on some external library. And this is just a great way to solve your problems. You go into the library, go under issues, and then find open or closed issues, and then just search for something that could result in finding your problem. So then you can look it up and then see what other people have done. So this one, for example, you might find something that relates to your problem. Of course, you need to sort in these, so transcription error, that sounds more right, and then you can find something that might help you solve your problem. So by doing that, I found that I could change some of these flags. So first of all, I'll remove line counts. So this max line count right here, I'll just remove that. And then under segment resolution, instead of sentence, I would like to say chunk. And then you should be able to just run the command, and you'll just have to wait for this to finish again. But then you'll hopefully get more accurate timestamps. And we'll of course just test these timestamps out in the SRT file after running this command again. So I'll see you in a couple of seconds, or a couple of minutes perhaps. Great, so now we are done here again, and we can hop over to output.srt and just check if everything seems alright. And right now it does seem alright, just by looking through it for the first time. I don't see any duplicate timestamps, so that is perfect. Okay, so if I hop down to, let me just find the random timestamp, 11:25, we do not train all the parameters. Hop over here. Quite a lot of parameters. We do not train all the parameters. It matches perfectly. So now it seems we have a dataset that matches perfectly with the SRT. So the audio matches perfectly with the SRT. So that is great for us. Cool. So the next part of this README is this will generate a WhisperX SRT file, place the SRT file in the SRT folder. So I'll go ahead and just drag this into SRT and say move. Then we should navigate to the main directory. So I'll just say cd, hop back to tools where we have all of these tools. Then we should run the segmentation script. So this one right there. I can just take that and copy it, say Python, run that. And that should segment all of our SRT and all of our audio from the SRT. So this will make small clips like this from audio, probably corresponding to the sentences or something like that. We can then run add padding.py. This will do another piece of processing for us. So it will throw array segments under 1 second and over 11.6 seconds. So the model has probably been trained to handle audio within this range. So that is why we see these constraints right here. So under bad audio, we see all the audio 16, 12, 1 second. So this is exactly what it did. It's throw array audio like it said. And then if I check under training data, we also have an output. So hopping down to the next steps, we need to run this script phonemized with the language defined. So I'll say Python, and I'm talking English US right there. And then this will create the train list and validation list. So under training data, this is the training data, so about 156 samples. And this is the validation data, which it uses to validate the trained model. And then you see, instead of the transcript, like we saw up here, the script has also phonemized all of our sounds. So instead of just having the text like it is right here, we have it phonemized. This means that it shows us, it represents all of the sounds instead of all of the letters. So take, for example, the word red. If you have this word right here, a machine or computer would have to determine whether you pronounce it as red, like this, or whether you pronounce it as read, like this. So there's some ambiguity there that is solved by using phonemizations, like we have right here, because this just gives the computer what sound is actually made So this is agnostic to any language you might have in the real world. So that is just a small explanation for why they use phonomizations for these text-to-speech models. Great, so scrolling down even further, this is not really anything we do need. Fine-tuning, we have already cloned down the repository. Let me just see. We did install a speak. Otherwise, you can say sudo apt-get install speak, like right there. We also prepared the data just now. We also downloaded the libcts model. And then we just need to take all of our training data, paste it into our other repository, and then just create the Docker file for running the fine-tuning script. So first of all, I would like to just open up another window like this. I'll just zoom in right here as well. And then hop into style.tts. So I'll say file, open folder, repositories, and then style.tts, the regular one. And then under data, we see that we have a training list and a validation list, but these are not ours. These are for previous training. So we'll just take these and delete those, and we keep OOD text as it is. Then under here, we'll say new folder, and then just call it waves. And then we can go ahead and take all of our segmented VAV files. So under segmented audio, we'll just copy all of these files. So I'll select the first one, press shift, select the second one, and copy those with Command C. Hop over here and paste them in. Then we'll also take the training list and the validation list, close this, and just paste them into data like so. And now we should have all of the data we need to actually go ahead and fine-tune this model. One last thing though is that we also have this config fine-tuning.yml file, which specifies how we are going to train this model. So hopping back over here and then just opening up the README like that. This is the exact same README as from the GitHub repository. If we then scroll down, oh sorry, this is not the one I would like to open. If I hop over here and then find notes on fine-tuning, so under discussions and then notes on fine-tuning, we should be able to see the different kinds of configurations and how many gigabytes it takes up. So what we'll use is the G5.xlarge on EC2, and then we should be able to see the specifications of this model. So hopping in under EC2 G5 instances, we can find xlarge. It has 24 gigabytes of GPU memory, so that is what we have to work with. Maybe a little bit less than that, maybe 22 or 23. Cool. So hopping in here, we can see that we have something called batch size, max length. We also have style diffusion and SML adversarial training. And then you can specify when you want to do style diffusion and SML adversarial training. So what you can do is, I'll just hop back in here. You can imagine a model as a series of components. So you have component 1 right here. And then you have component 2. And you also have component 3. This is just an arbitrary number. And then the model has input data that goes from component 1 to component 2. Component 2 is component 3, and then all the way to output. And we also have input right there and output right here. So in each of these components, there is a bunch of trainable nodes in the neural network. So there's a bunch of neurons in this component, there's a bunch of neurons in this component, and a bunch of neurons in this component. And when training the model from scratch, we would like to train all the neurons in both this component, and this component. But maybe this component isn't very relevant to us, or maybe it isn't very relevant for us for this one as well. So we only want to train this one. So what we can do is just lock down all the neurons in this one and allow all the neurons in this component right here to be modified. So if we just say, okay, we just freeze all of the neurons in this one, and then we only allow training on this component, this means that we'll use way less memory because we do not have to care about all the neurons in this component, in these components, only the neurons in this component. But it also means that because we aren't fine-tuning the entire model, but only parts of the model might also become less precise. So this is a trade-off you have. But because we don't want to upgrade to a massive instance that is super beefy, like this one, for example, this one down here that has 96 gigabytes instead of 24, we'll have to manage how we spend the memory we have available properly. So even if we upgrade to this model, which is pretty beefy, it's 16x large instead of x large, it still has the same amount of GPU memory. So that is why we have to be pretty careful about which components we allow to be trained and which ones we do actually train. But luckily, hopping into the notes on fine-tuning, this explains it exactly here. So one of these components are style diffusion, another one is SLM adversarial training. And you can actually disable both of these. These are just components. If you do have them enabled, it will take up much more GPU memory. If you have both enabled, it's 76 gigabytes of GPU memory, which is a lot. But if you just want to use a single NVIDIA graphics card like we have available, we can get away with around 22 gigabytes, which is around what we have available. So that is what we'll work with. Great. So the way you can adjust all of these different parameters is by hopping in under configurations. So right here under configs, we have configuration fine tune right there. And then we see all of these different parameters. There's a bunch of stuff you can tune. So this is the pre-trained model. So this is the model that has been pre-trained by researchers, which we will improve upon to our specific use case. The batch size is how many samples is taken at a time. You can have a higher batch size, but this will also increase the memory usage. The device is what you use. So CUDA means using a GPU with CUDA, so NVIDIA. And then CPU means you use the CPU, but that is obviously not recommended because it'll eat your CPU up alive. Then you can also define the max length, which will also have a massive difference on whether you get a good fine-tuning model or good fine-tuned model or a worse one. So going down, these aren't really very relevant to us except for these ones. So diffusion epoch and joint epoch. So this is when we allow the unfreezing of the different components. So one of these were diffusion, style diffusion, and another one was SLM adversarial training. So as you see, when we enable either of these, so this is with both disabled, with one of them disabled, but enabling one of these will just increase the VRAM usage. So we would like to be very careful with this. So what you can do is just hop in here and then you can define the starting epoch. So the epochs is how many times we run training data through the models. So let's say we do that 50 times as defined up here. So epochs. And then down here we say, okay, after epoch 10, then we unfreeze the diffusion layers and allow the model to use more VRAM and then start training with diffusion as well. And we can do the exact same for joint epoch. If you want to disable using any of these, you can just say 51 or 51 because we have 50 up here. This means that they'll actually never start. They'll just be disabled forever. So in our case, we would like to train with about 15 minutes worth of audio data, and we would like to train it on the G5X Large with the 24 gigabytes available. And a fine-tuning configuration that has been carefully selected for that specific GPU is the following one. If you set epochs to 75 right here, batch size to 2, and then max length to 225, then hop down to diffusion epochs. So diffusion epochs, set that to 29 and joint epochs to 76. So we'll never train the joint epochs like that. We'll never do that. Then we should be good to go for the training. This will keep our training job right under the limit for how much memory we have available, and also give us great results compared to other configurations with our current setup. So we can test this out by hopping into style.js to fine-tune, like this. And then in the bottom there was a command for actually running the fine-tuning job. So this is the command right here, accelerate launch. So hopping down to style.js 2, just opening up a terminal in the root. And this is just for testing before we move on. This is definitely not where we want to do the fine-tuning. I can just paste this in right here. We'll then need to set device to CPU. And then also under accelerator, which is one thing that is being used, we'll need to set the CPU to true. And also device placement to true, which will also keep things on the CPU right here. We can then just try and run this and see what happens. And this is quite a job. It is starting up, so it might take a while. But we did get an error, no module named pandas. So we'll just go ahead and add this to requirements because we'll need this even inside the Docker container. So pip install pandas. And we'll just keep doing this until we know we have all of the different requirements. We'll just run this again, see if there's anything it will complain about. So it just finished again, and now it says no module name TensorBoard. So we'll just add this as well. Say pip install TensorBoard, and then just run this entire thing again. And I got the following error right here. So it doesn't seem like a module is missing, because it's kind of a longer error. We did go further down in the code, so we loaded the different components. We see some decoder, parameter group, and then there's a problem somewhere in this call stack. So what I'll do right now is actually use AI to debug this. So I'll just open up here, and then I'll add the last terminal command along with the code base. Then I'll say, I got this error, running this, and then I'll just press up once, paste in my command, and then just see what it says. This is a great way to debug, giving it what you just got returned from the terminal, along with also the entire code base, so you can just look through. And I'm using GitHub Copilot right here, by the way. You can also put this into ChatGPT. You can take the entire thing right here, and this is something you should do often. So when you do see an error, you can first of all ask ChatGPT. Otherwise, you can go to GitHub issues and check if there's actually a solution for it right there. So yeah, this is a great way to solve your errors. Okay, so it says that something is not properly installed on my system. So I need to reinstall this with brew. So I'll take this, paste it into the terminal, and then I'll just try and reinstall this like that. And then I'll reinstall this sound file library up here as well from the requirements. Maybe it's not linked properly to this libs nd file. So we'll just try and do that and just see what happens. I'll just come back when this is ready. Alright, so this was just reinstalled. Now we can take this sound file, uninstall it, and then install it again. And then just now it's installed. We should also make sure it points to correct audio files. So hopping into config fine-tune, we can see the log directory is LJ speech. I would like it to be libretts actually. libretts. So under models, libretts. And then let me just see where these paths lead to. So these ones should be fine. Utils. Yeah, it looks fine. And then under the data, we have data training list, data validation list. But it doesn't look like the audio file folder is pointing to the correct place. So what we'll actually do is say data, and then point this to the WAVS, which contains all of audio files. So this might be a problem that was this might be the issue that was causing this problem. Then we also have this pointing to the correct thing as well. So yeah, this might actually fix the problem. Great. So let me try and run this again with these new fixes. I'll just run the entire command again and just see what happens. And I'll come back whenever this is done. Alright, so it just finished up and I see this. So we got an error again. So scrolling all the way up, we see that we came further than last time. We see the same printouts, but now we also see the audio files. So scrolling down even further to where the error actually is, we see the following. Device index must not be negative under modules discriminatory. So in here, we have get device. So for now, because we're doing this locally, what I'll do is just go ahead and change this to CPU. And then I'll hop up and run this command again and just wait for it to finish. So this is kind of an iterative debugging process, and probably how you'll work a lot of times when you work with repositories you haven't really worked with much before. You'll just run something, you'll see an error, you'll fix the error, and you'll just repeat that until it works. And then at some point you'll have something that works. And I'll just come back in a second when this is done as well. Great, so I haven't seen any errors on this for about 5 minutes, which means that it is working well as far as I know. What I would like to do though before we do create the Docker file and start the training is just add some printout statements to this train fine-tune accelerated py just to see if it works as we're expecting throughout the training. So I'll just go ahead and say control set to this one down here in the terminal just to stop this process and close down the terminal. Then we can add some statements over here, some print statements to just start start monitoring what is going on. Great. So the first thing I would like to do is right inside this main function, I'll just say print, and then I'll just add a new line, and then starting style.tjs to fine tuning like this. Then I would like to hop down to where we load the data. So down here, we should see somewhere where we load the data. So right over max length, I'll just say print, and then train data path. And I'll just put in, let's make this a formatted string by putting an F. And then I can say train path. We can also say validation path. And last we can say root path. And then we can say validation right there. Great. So next what we can do is just scroll down a little bit. So right here, I would like to just say print, and then I'll say data lists loaded. And let me just make this a new line as well. Under this, I'll just say training samples, just so we know whether it loads all the training samples in production when fine tuning. So I'll then just say length of training list, and I'll do the exact same for the validation samples. Validation list like that. And then if we hop down to where the model is loaded initially, that should be down here under or right over load checkpoint. So we have load checkpoint right there. Anywhere else? Yeah, right here we can say load. Yeah, it's already been printed. Then we can hop down to where the training actually starts. So that is right where, does it say for epoch? Yeah. So down here we can say print, and then starting training. Right under this, we'll just add in epochs as a formatted string. This will be epochs, like so. Under this, we'll say save frequency. This will then be save frequency like this, and that should be fine for this. And then I would like to just hop down to train right here and just add a progress bar for each epoch. So I'll say epoch, and then I can say epoch. We'll just need to add a formatted string like so, like this. And we can then say epoch plus 1 of epochs, like that. Under this, we'll just add another formatted string. We'll then, oh wait, we actually do not need to do that. We want to put in the progress bar. So right here at enumerate, we would like to just extract this out. So I'll just copy this enumerate and say train iteration equals tqdm, which is a library we can use. So we'll just have to hop up and import tqdm. So import tqdm, and this allows us to make progress bars in the terminal in Python. So hopping back down to right here, we can wrap this enumerate in tqdm, and this will automatically create the progress bar for us in Python. The description will be training. We'll then say total, so how much the total of progress bar is. That is going to be the length of the train data loader. And then we can say file equals system.standardout. And we just need to import system as well. So up here, we'll just say import system like that, and hop back down to, where were we? We're down here, perfect. And then right after file, we'll just say bar format. So we'll just format how the text should be formatted. So we'll put in L bar. I'll just go ahead and do this right here, R bar. And just say bar 30. So this formats the bar as the left bar content, the main bar, which is going to be 30 characters long at most, and then the right bar content. So a super simple bar that shows the loading. And then we contain this train iter down here, and instead of enumerate, we can just put in train iter, and we should see the bar whenever we run the script. Then we can also time how long an epoch takes. So we'll say start time equals time dot time, like so. And then it's already been done actually. Let me just see what this is used. Probably down here. Yeah, so it says time elapsed, and then this is how long an epoch took. And then we would like to also just know when the validation starts. So we'll say print, and then running validation right over here when it loads the validation data loader. And after that, we can show the total amount of epochs having been done. So the validation is been done already. And then go down, it shows saving. So yeah, that should be enough logging for us. So let me just try and go ahead and run this again. So I'll just start up a new terminal. I'll say open integrated terminal and just run the same command again. And we can see if we get some more verbose logging that will kind of give us an idea of whether we reach into the actual code or not. So it says module is not callable, and it says that at TQDM. So right now it comes from up here. It's the actual module, but what we need to do is say from TQDM, import TQDM. This is a class, and then it should work fine. So let me just try and run this again. And we quickly got this error right here. It says too many values to unpack at this exact location. So what happened right here is that we put in a trailing comma by mistake. So if you put in a trailing comma like this, it will create a tuple with only one element instead of actually assigning the value. So if I try and remove this, we should see that it looks better. Yeah, so we have a tuple with the tuple inside of it. And now we just have the tuple that we need. So that should be perfect. Let me just try and run this again and see if it works out fine now. So now the printout we see is the following. We see all the models or component loads. We also see the paths. We can then see epochs and save frequency. So every 5 epoch, we create a new model checkpoint. So the model checkpoint that was originally there was the following right here, made by the scientists. That is this .pth file that contains the state of the trained model. And then what we see is epoch. So we see how many epochs there is. And then it starts training. We get some random error right here where it fails to load a image Python extension. I'll just look into that, but it doesn't seem to affect the actual training. And then down here, we see that we have a printout of all these different outputs, which is also great. So it seems to work for now. So let me just go ahead and move on to the next point. So after just looking into this error for a second, I found out that the versions of PyTorch and PyTorch Audio probably aren't the same. So what you can do is just go ahead and uninstall the different packages that is related to Torch. So Torch, Torch Vision, and Torch Audio. So we'll just go ahead and uninstall those and then reinstall them afterwards to make sure that they have the same version. So if you just go ahead and do that, press Y, and Y again, and then just say pip install, and just try and install them to see if they are now the same versions that are compatible. We should then be able to run the training script again and hopefully see a difference. So I'll just come back in a second when it's started up. So now it's been running for about a minute. So what I'm seeing is that the error is gone. We see all the printouts from last time as well, but we do not see that weird error kind of signifying the version mismatch. So it looks like we're ready to get this ready for the Docker file and then get it up to EC2. So what I'll do is just first cancel this run right here. So we don't want to actually do the training right now. Then I'll press right there. And if we then hop back into this discriminators, we see that we move this to the CPU, which isn't what we want to do in production. We'll just move this to get device, press save right there. And then we can say config.finetuning. We'll just say CUDA right here again. So CUDA, this will move it to the GPU when it is available. And then lastly, I think we changed it up here under accelerator, we moved it to the CPU again. So we'll just go ahead and revert that as well. And then I think we have all the things we need here to be able to install this in a Docker container. So I'll just go ahead and remove that and that as well. Now we're ready to create the Docker image, which we can then use to run the Docker container on these two instances. So first of all, I would like to hop into data and then just see everything is alright. So we have the files, the training lists, everything looks good. Then I'll just say new file, and I'll call this Docker file.train. And then before we can use Docker, you actually have to have Docker installed on your PC. So if I just hop in here and search for Docker, you'll need to install Docker. So what I usually do when I have a computer and I want to install Docker is just install Docker Desktop. So you can then go to Docker Desktop and there should be an install button right here. You can run this on both Linux, Windows and Mac, it doesn't really matter. And then when you start up Docker Desktop, you should be able to, it should just start Docker for you. So right here I have Docker running because Docker Desktop is running. So I can then go ahead and say go to the dashboard and then see where, or see if it's running or not. And also see a list of all my different containers. So since I've worked with this repository before, I already have a Docker container for running the training. So I'll just take and copy line by line from my existing Docker file until we have the fully working Docker file, so we can try and build that. So first of all, we have the base image. So remember how I talked about the base image? Well, that's what you said when you say from up here. So from, and then we have this PyTorch base image, which includes CUDA, so we'll be able to work with the NVIDIA graphics card that is available right here on the EC2 instance. Great. Next, we'll set the working directory, so we can say workdir app. So under /app will be where we store all the files we'll work with inside the Docker container. We can then install system dependencies. So these aren't Python dependencies right here. These are the actual system dependencies. So since we are using Linux, we can use apt-get. So first of all, we'll update the apt-get package manager to make sure it's up to date. We'll then say apt-get install and put in the flag -y. This means that if any of these install commands ask the user to press Y or N, so yes or no, it'll always just default to Y. This means it won't really block the installation, but just keep on going, even if there's anything that requires the user's feedback from the keyboard. Next of all, we'll need to copy in the requirements. So I'll just go ahead and do this. Indent it back. So we'll say copy requirements.txt from my computer to the root path of the Docker container. So what I'll do is I'll take this one right here, requirements.txt from my computer, copy that into the Docker container or the Docker image, and it'll be done with this command right here. Then we'll say run. So this will run a command in the terminal inside the Docker container, and this will all be done in order, by the way. So first we set this, then we run these commands, then we run these commands, etc. And this will also be cached all the way down. So the base image will obviously have to be pulled and built, etc. So this will take a long time. So because this is something that is being used all the time but not changed more than once, we'll just have to set this as the first. This means it'll be cached as the first element. So if you do decide to change the base image, it'll have to rerun all of these commands after it. So you'll need to set or place your order of your commands in the order of which ones you're going to change the most. Because it doesn't really make sense to place these system dependency installations as the last command, because then you'll have to do these every time you want to build the Docker container, and they can take a while. I'm just saying. Then we'll install with pip install. So this corresponds to just opening a terminal, saying pip install, and installing the requirements.txt we just copied into the Docker container. We'll also install accelerate, and then we would like to copy all of the code from our repository right here into the Docker container as well. So we'll say copy and then dot. So this is the from on our local system, and this is the to inside the Docker container. So we'll just take everything. So this is from the root. So we'll just take everything and copy this into the root of the Docker container, such that the Docker container contains all the code we are able to run locally as well. We'll then just need to set some environment variables for Python. So we'll say env. So when you say env in a Docker file, you inject this environment variable into the environment, so into the Docker file into the Docker container in this instance. So if we go under train fine tune, maybe we can say env. Anyways, what you can do is you can say import os, and then you can say os dot get environment variable, so get env, like this, and then you can go ahead and just fetch an environment variable. So this is an environment variable that has been injected, if I do this, into the Docker container. So this will then be accessible inside the code, inside the Docker container. So this means that you won't have to hard code any secrets inside these code files. You can just inject them in through the Docker file or through the Docker compose, which we'll also use later on. So that is why we set these environment variables. And these ones are actually used by Python, so we'll need to include these. The first one is Python path, which is going to be app. So that is the same as the working directory. Then we'll also need to say torch home, like this. And this will be app/models, like this. Then we can go ahead and create the script that will be run whenever we want to run a training job. So all of this sets up the Docker container so it's ready for the training script. So we will obviously need to install things such as Speak, because that's what we used whenever we want to train. So we also said brew install Speak, for example. So we'll need to install the same library just for Linux. And then we'll also need to set up stuff such as this libs.nd file for audio processing. We also need to install the requirements to make Python work with its dependencies. We also need to copy in all of the code so we know the model architecture. So all these things just sets up the Docker container for us. But then when you do run the Docker container, this run right down here, which is the last command that has been executed, will then set the stage for what happens next. So what I want to do is run this accelerate launch, which is going to run this train fine-tune accelerate script and then just start the training. And then whenever the training whenever the training stops, the container will just exit and stop. And what we can then do is just go into the Docker container that has been stopped and then just upload that updated model file or fine-tuned model file to an S3 bucket. So this will just start the fine-tuning whenever we do run the Docker container. And then the entry point should be set like this, entry point.sh2. So what happens here is that we run a command in the terminal. So this just corresponds to opening up the terminal and running something. The command we run is that we want to create a new file, entry point.sh.shell, that contains the following content. So we take all this content and then put it into this file via this operator right here. And then we make that file executable by saying chmod plus x and then entry point.sh. So this ampersand, these two ampersands corresponds to running two different commands. The first one is this one right here. And the second command is this one right here. So we create a file that can be executed, and this is a shell terminal. So this is just a command that runs something in the terminal for you. Then we make that executable. So if you put in the shell file into the terminal, it will execute what is inside of it. Then we set the entry point for the Docker container. So this is what happens whenever we do start the Docker container to just running this file. So whenever the Docker container is started, it'll just run this file automatically and start the training for us. So that is basically how the setup works. Whenever we build the Docker image, all of this will be done. And then whenever we start a Docker container, this down here will be done. Or sorry, more specifically, this right here will be done. So the entry point will be set and ran. And now we should then be able to actually build this Docker image. So we'll hop over to open an integrated terminal, and you want to make sure that your Docker is actually running. So if you haven't opened up Docker Desktop, go ahead and do that. And then you should be able to see running in resource saver mode. If you do run a Docker command and it is not started, it will tell you Docker is not started. And then you just have to go ahead and start it to make it work. So what we'll say is Docker build, and then -t, so we'll tag it, so give it a name basically, style tts2 fine-tune, and we'll also like to specify the specific Docker file, so -f dockerfile.train, and then just press enter. And we were just missing one thing, we were missing a dot at the end, so this dot right here signifies the build context, so where we want to build it from. Great, so we'll just go ahead and press enter now. This will create a Docker image called style.tts.ft fine-tuning. This is the tag. It will use this Docker file to build it, so -f, and then we'll use this as where it should build it from. So we'll just go ahead and press enter, and then just see if it builds it correctly. So let me just go ahead and wait for this to finish. This might take a while, just so you know it, and then I'll see you in a minute. So the installation just finished, the Docker image build just finished. So let's go ahead and check out the logs just so we can see what actually happened. So we put in this command, and then it ran through all of these different layers. So you see how This is one different command, this one command, etc. all the way down. And then it caches these on the way down. So you can see how it says cached right there, for example, or cached right there. So whenever you do run this Docker container again, if you have placed the layers correctly, so they are cached as efficiently as possible, it will take way less time to build it next time. So first of all, we just ran this system command that was cached, probably because I've built an image like this before that is named the same. Then we copied the requirements into the file, into the container. So that is exactly what happened here. We then ran pip install requirements and accelerate, copied all our file contents into this Docker image, and then we ran this echo creating the shell. And then whenever we do the shell file, whenever we do run this Docker image as a Docker container, we'll then just enter into this shell file which is created, and then just start the training like that. So what we can then do is just paste in the following command. So we can say docker run -it, -it, and then we can say style tts2 fine tuning like this. Wasn't that style tts2 fine tuning? And then just try and run the Docker image just to see what happens. So this should then trigger the following point right there, which should then go into the following file and run that. Because we haven't set this up to work with CPU, but reverted back to CUDA, this should not work. But in theory, this should start up the Docker container, and that is exactly what we'll do on the EC2 instance. So just hopping into the configs and fine-tuning, I just wanted to make sure that we have actually set this to CUDA, and we have. So let me just see what happens now. It should probably give an error because it is set up to work with CUDA, which does not exist on my computer. At least we do see some printouts knowing that it starts up correctly and runs the file it is supposed to do. So I'll just come back whenever we get an error. Alright, so I just left this running for about 5 minutes, and it seems like it has gracefully fell back to running on the CPU instead of actually failing because it's not being set to a GPU like I expected. So in here we did say CUDA, but because we do not have a NVIDIA graphics card available on this MacBook, we do not see any errors because it gracefully defaulted back to CPU. So that is nice to know, even though we won't train with the CPU. So this is how it's supposed to look when we run it on an EC2 instance as well. We did get a little cue though, or clue, that we aren't running on the proper platform. So the requested image platform, Linux AMD 64, didn't match Linux and then ARM 64, which is this MacBook operating system basically, or the M1 chip. So otherwise it loads the things it is supposed to load, the components, and then also just start the training from scratch. So it looks like it is supposed to look, and then we'll just go ahead and get this ready for training on the EC2 instance. So the first thing we're going to do is hop over to AWS. So if you open up a new tab and search for AWS, you should be able to find a place to log in. So sign in. So I'll just go ahead and sign in and then see you in the dashboard. Alright, so now that I'm logged in, you see the dashboard right here. And the first thing we're going to do is apply for being able to use the specific EC2 instance we would like to use. So we have a hub under service quotas. Then under AWS services, we can search for EC2. So this one right here, and view quotas. Now I'll just open up another tab and search for EC2 G5 instances. And then we can determine what we need to apply for. So scrolling down, we would like to use the G5.x large, which is the cheapest model with this many GPU gigabytes. So as you see right here on the vCPUs, this is what we're going to be applying for. So if you do apply and get 4 vCPUs granted, we'll be able to use this model right here, but also any other G5 model that would have 4 vCPUs. If we wanted to use this model, for example, we would have to apply for 8 vCPUs, etc. So now we know what we need to apply for. So searching for on demand, we want to find this right here. So running on demand G and VT instances. So we'll be applying for the G instances right here, G5. So you'll have to find it right here and then press request increase at account level. And then you can put in 4 and press request. This request can take up to a day or 2, depending on when you apply, etc. So I would advise you to just do this as quickly as possible, just so it can wait for you while you do other stuff in the meantime. Now, the next thing we're going to do is hop over to S3, which is the next service. If I go back to Excalibur, we can see exactly what we're going to set up. We'll need to create a bucket called ElevenLabs clone or something in that likes. So hopping over here, we can say create bucket and then say ElevenLabs clone. I'll just hop down and say create bucket. Like that. And now we have this bucket right here, which we can use as a file system within the cloud. So back in the Excalibur file, if we just look at IAM, before we create the EC2 instances, we need to attach an IAM role to that EC2 instance such that we can do the things that requires permission by the instance. So we'll need to create this role down here, which we can attach to the instance, and we need to give them the following permissions. So we'll call this role ElevenLabs clone EC2. So if I hop over IAM, this is to manage permissions and security for all the IAM resources, all the AWS resources. We can hop under roles. In here, we'll say create a new role. And then under this, we'll just go ahead and say EC2. And then I'll say next. And under permission policies, I would like to choose the following one right here. So we have access to pull the Docker image from the container registry, ECR, Amazon S3 full access. And I'll then press next. And then just hop down and say create role. I'll just call this ElevenLabs clone EC2, like so. And then create role. Now, if I just scroll down to my role, we should be able to see in the last page right there. I just want to add some permissions as well. So I'll say create inline policy, and I'll say JSON. And what I'll then do is just paste the following JSON in. So the same as before, just where we switch out the statement in here. So I'll say allow, and then action should be S3 put object, get object, and list object. And we then specify the specific resource we would like to be able to do this for. So this is of course the S3 bucket, but we would like to specifically be able to do it for the ElevenLabs clone bucket. So hopping back over here to S3, we can then get the resource identifier. So under properties, you will be able to see the Amazon resource name, the following one right here. So that is what you copy, and then hop back over here and insert under resource. And when you put /*, that means you can also do the same commands for all objects that are within the bucket. So this should allow us to upload stuff to the bucket, such as the fine-tuned model files whenever we're done with that in the EC2 instance, as well as pull from the bucket if we needed to. So we'll then press next, and then policy name we'll call ElevenLabs clone EC2 policy. And then I'll just say create policy. And we then have all the permissions we need to be able to attach this to an IAM instance. So next thing we're going to do is just set up ECR. We might as well just create all these repositories right now, so we have them whenever we need them. So I'll head over to ECR, Elastic Container Registry, and then say create, and then we can just create namespaces as we want. So first of all, we're going to need this one, style.tjs 2 fine-tuning, and then create. We're going to need one for the API as well. So I'll go ahead and say create again. We're going to need one for seed.vc fine-tuning. So I'll put this in, say create, seed.vc API. And lastly, make a sound API. Or this is actually called make an audio. So make an audio API. And then I'll say create. So this will store the Docker images in the cloud, such that we have a central place to store them. And this means we can pull them down to an EC2 instance whenever we want to run them, for example. And now that we have already built our Docker image just before, we can actually just take that Docker image and push it to one of these repositories. So we built the style.tjs 2 fine-tuning image. So I'll go ahead and click this, say view push commands, and then copy the following command right here. I'll hop back into my repository, open a new terminal, and just input this command into the terminal. This should log it in for us. And the login succeeded. Then we can say docker build, which we just did. We can then just take the Docker image and tag it like so. And now we can say docker push and push up our image to the cloud. So this might take a while depending on your internet speed. It might have to push something between 2 and 5 gigabytes. Or it'll actually push up to 7 gigabytes, which is quite a lot. So just stick around and let this happen in the background. In the meantime, we can go ahead and create some of the other things we do need as well in AWS. So under IAM, we also need this user right here. So the role of this user is to be able to use it locally whenever our program needs to upload to an S3 bucket. So we need, with the voice conversion, to be able to upload an existing voice or an existing audio file to an S3 bucket, which we can run voice conversion on. So to be able to do this, we of course need permissions. So we need to create a user and not just a role. Then we can get some authentication credentials from this user, which we can use locally to do this. So we'll just go ahead and copy this username, StyleTJS2 API, hop under IAM, go under users, say create user, and put in the username. We'll then just say attach policies directly, and say create policy. We can then say JSON again, and paste this thing in again. So this just allows us to be able to put objects into the S3 bucket for this ElevenLabs clone and everything that is inside the ElevenLabs clone. So that is exactly what we want. We only want to be able to put stuff into the S3 bucket and list objects if we do need it. So let's press next and just name this. So we'll say StyleTJS2 API policy. And this is actually not for StyleTJS, this is for seedvc. So we'll go ahead and say seedvc and press create policy. Going back under create user, we can then say refresh over here and search for seedvc right there. We can then press next, create user, and now we have a user as well. So going back into Excalibur, we now have the user, we have the role for the EC2 instance, we have the ECR repositories, we also have the S3 bucket, and you have applied for the service quota for being able to use the instance we want to use. So now we just need to be able to create the EC2 instances. You will be able to do this whenever you have had this approved. And then going over here, as soon as this is pushed, we can go ahead and actually create the EC2 instance and pull the Docker image in that EC2 instance and try and run it so we can do the actual fine-tuning. So it just finished up here. As you see, everything was pushed with no errors, so that looks perfect. Great. If you go back to just AWS somewhere, you should be able to search for EC2. I'm just going to open this in a new tab and then hop into this tab. I can then say launch instance. This I'll call StyleTJS2 fine-tuning. I'll then pick Amazon Linux. Under the machine image, so AMI, I'll say PyTorch. This will pre-install PyTorch and NVIDIA drivers for us, such that we can more easily work with what we need. Great. Going down to the instance type, I'm going to search for g5.xlarge, like this. And then under key pair, you can either create a new key pair or just select another one. I just have a test key pair, for example, I use. It's required. It's just so if you want to connect to your instance and do it in your terminal, for example, you can do that. I'm just going to use the web terminal, so I'll just pick a default one that I've just created a long time ago. Great. So we have the name, this machine image, PyTorch, g5xlarge, the key pair. I would like to configure storage. I'll set it to 100 gigabytes because this image takes up a lot of gigabytes in itself and will even generate a new model file which we need to push, and we'll have checkpoints for every 5 epochs. So trust me when I say it really sucks to be halfway done with your training and then the EC2 instance runs out of space just because you put in 50 instead of 100. That really sucks. So it's better to be on the safe side, and storage isn't really that expensive here on AWS. So going under advanced details, I can just find IAM instance profile, press select, and then press ElevenLabs clone EC2, which is exactly what we created just a second ago. We'll make sure that the number of instances is only 1, and then we can say launch instance. And now the instance has been created. This particular instance is about $1 per hour, so it's not that bad, but it's very important that when you do stop using it, you go in, press right here, and say instance date and terminate. Stopping the instance is not enough if you don't want to pay, that'll just stop the computer, but it's still rendered out to you in theory because you get started at any time and still have the state. So it's very important that you press terminate or delete instance. This will make sure it's completely deleted from AWS and you won't be billed from that point on. So hopping back to the instance or instances right here, what you can do is say connect, and then you can just press connect right there. And we should then see the instance right here. So the first thing I want to do is make sure Docker is installed. So we can say Docker just to see if it's installed like we expect it to be. Next up, we can create a new Docker group. So I can say sudo user mod -a or -a-g docker ec2 user like this. And this of course needs to be sudo. So super user do. I can then say new group docker. So what this does is that it allows us to run Docker commands without prefixing all of these commands with sudo, because we have added the user ec2 user to this Docker group Docker. So it'll just simplify things a little bit for us in a second. Next we can say AWS ECR. We can then say get login password region US East 1. That is my region up here. And then we can say pipe symbol docker login -- username AWS -- password standard in. And then we'll need to pass in the Elastic Container Registry up here. So if I just take the following without the postfix of the actual repository, just this right here, we can then take this and paste it in right after and just say enter. And now we are successfully logged in and able to pull images from this repository right here. Great. So the next thing I want to do is pull the specific image. So hopping under style TTS-FT, we can just copy this right here, go under instances, say docker pull, and pull this specific image, and then this will just have to download for a couple of minutes. Now the Docker image has successfully been pulled, as you can see right here, and what we'll do is just go ahead and run it. So we can say docker run --gpus all -d -name style tts2 container, and then we'll just take this thing we just pulled, so the following one right here, and append latest to that, and then that should allow us to actually run the Docker image. So here's what these flags mean as well. So Docker run is just running the container right here, the one we specify, and then GPUs all gives the Docker container access to all the GPUs in our system. So that is the GPU that we talked about from the G5X large instance right here. And then we also put it in detached mode. This means that it runs in the background, because if we don't do this and we close the terminal, the Docker container can also stop running, and that is not what we want. We want it to just be able to run in the background, then we can check the logs whenever we want to. We then also assign a specific name, so style TTS2 container, to this Docker container, such that we have a custom name instead of just an auto-generated one. And this of course is the image we want to run as a container. So let's try and go ahead and press enter and just see what happens. So it just started up. It took about 5 to 10 seconds, and now we have a specific printout. So this is the Docker container or reference to that. What we can then do to check the logs inside the Docker container is say docker logs -f style tts2 container, because we put it in detached mode, so it is running in the background, but we can then get the logs from referencing its name like this. So let's just press enter and go ahead and do that and see what's going on. So this kind of reminds us of what we saw locally. So we have the training data path, validation, root. It loaded all these samples like it should. We also see that the training has started, so it's about 13% done training the first epoch right now. So something is at least happening, which is great. So what I'll do is just leave it as it is right here, and then in about a couple of hours it should be done training, and then I'll come back and take a look at the results with you. Training just finished and the file has been saved, as it says right here, saving. I just want to note one thing. If you do close your computer or leave it too long, it can close the connection. So right here, for example, it stopped after epoch 5 and you don't see any further logs. And this isn't because it isn't running in the background. It is simply because it just lost the connection to the instance in some case. In some way. So if this happens and you don't see any logs anymore, and it just freezes, what you can do is just take this URL, open up a new tab right here, paste in the URL, and it should still be running in the background. And because we started the Docker container as a detached container, what we can do is just go ahead and just pull the logs again. So if you run this command once again, it should then just pull all the commands since you started the Docker container. This obviously isn't something we're going to do right now because I've already done it, but you can just do that in case it freezes. Great. So this is after doing that actually. So you can see all the different logs. So you can see the different epochs. This is epoch 73 out of 75. And then all the way down to epoch 75 out of 75, which is the following one. And what I want to do now is just take this, I'll just close this, is just take this file that was just saved, the newest one at least, and then put it into the S3 bucket. So first of all, I'm going to go ahead and find S3 right there. And find the buckets right here, yeah. So I'll go back into my EC2 instance and then just say docker processes -a like so. And now we can see that it exited 5 minutes ago. So that is when the Docker container stopped running. I'll then just take this container ID and say docker starts and start it up again. And now it should be started. So we can then say docker exec -it, and then you can take this one right here again and finish with bash. This allows us to enter the Docker container. So now we're actually inside the Docker container. So any command will run right here, will show us what is inside the Docker command. We'll execute that command inside the Docker container basically. So if we just do ls, for example, we can see all the different files that we added to the Docker container whenever we built it for the first time. And then where the model was saved is inside the models folder. So we'll do change directory, models, ls, change directory, libre tts, ls, and now we can see all the different checkpoints. So the checkpoint we're currently interested in is the newest one. So that is checkpoint for epoch 74, or just like the latest one, which is the one right here. So it's actually epoch 75. So we want to take this and upload it to the S3 bucket. Great. So right now, if I do AWS and run this inside the Docker container, we do not have the AWS CLI installed. So we'll first go ahead and say apt get update. And we have to say apt, not API. And just wait for this to finish. And now that that is installed, we can say apt get install -y AWS CLI. And this will allow us to use the AWS CLI as soon as it is installed. So we just need to do a couple of configurations. So I'm just going to go ahead and choose Europe number 8 and Copenhagen number 14. And then it should install the rest. And now if I go ahead and say AWS, we should be able to use the AWS CLI like so. Good. So we can say AWS S3 and then copy. And we'll want to copy a file from our local computer, so that is inside the Docker container, and all the way into this S3 bucket. So we'll go ahead and say, I'll just start out with saying ls. And this right here is what we want to do, or what we want to copy. So we'll say AWS S3 copy. And then we'll say dot like so. And we'll want to copy it into the S3 buckets. So under properties, we'll just copy its ARN, or at least its name. So S3 ElevenLabs clone. So we'll go ahead and do this. And just instead of these two dots, we'll just go ahead and do that instead. And then I want to put it into a folder called models. I'll just call this style TTS to models like that. Then if I press enter, we should see it being uploaded to the S3 bucket, and we can just verify this in a second as soon as it finishes. And now it is finished uploading, so let's just go ahead and check it out in the bucket itself. So if I press reload over here, we should be able to see the style TTS2 models folder, or file, sorry. And this is just the file we would like to download to a local computer as well. So right now I renamed this, I named this in the wrong way. I mistake this for a folder, so it should actually just be style TTS2 model or something like that. Cool. So now that we have this, we can just go ahead and download it to a local computer. So we know its path, that is the one right here. We can say copy URI. We can then see the path inside the buckets. So if I go to right here, we would like to copy this from S3 and then into our local computer inside the libretts folder. So right now we have the one made by the researchers, which is at checkpoint 20, and the one we are interested in is at checkpoint 74. So we'll go ahead and say AWS S3 and then copy S3, and we can actually just paste in this right here. Then we can say to our local computer, so that is at models, libretts, and then we'll just call it epoch second 00074.pth, like so. And then if I run this command, we should see it starting to copy down into our local path right here. So downloading now finished, and we see that it downloaded right here, as well as the actual model file over here. So let's go ahead and test it with the fine-tuned model, and then see if it actually works with my voice. So under Libre inference, which is the inference file we made, we can go down and just select the model path. So going all the way down, if we put in our model path, the new fine-tuned one right here, and then just put in Andreas again, we can then just go ahead and say, hello, my name is Andreas, and I'm now testing with the new fine-tuned model. Cool. So if I just go ahead and do that and try and run Python Libre inference.py, we can check out the result in just a second. Great, so let's try and check out this output.vav. So just had an issue loading, but let's try to check it out now. Hello, my name is Andreas, and I am now testing with the new fine-tuned model. So it sounds much more like me compared to if you do it with the old checkpoint. So we can just go ahead and check that as well. So this is I'll just call this fine-tuned output, and then I can just do the exact same for this other checkpoint, which is without the fine-tuning, so you can really hear the difference. And this just has to be epochs, not epoch. So now it just finished up, so let's just find the output.
Hello, my name is Andreas, and I am now testing with the new...
So that does not sound like me at all, so you can already see how massive the difference is between the fine-tuned model and the model that is not fine-tuned. So that is exactly why we fine-tune, and this really proves and validates that fine-tuning was the right decision in this case. Good, so with the model fine-tuned and then downloaded down to a local computer, we really have everything we need for setting up the API with this particular model. So going back to Google Chrome right here, I'm just going to hop into the EC2 instance and just close this down. We don't really need it anymore. We do have the product of the fine-tuning, which was the model. So we can just go into instances, instance states, and then delete or terminate this instance right here. So I'll just say terminate, and then this might take 5 or 10 minutes, but it'll terminate, and then you won't get billed anymore for this. Another thing I just want to point out as well is that if you scroll over to the launch time, it says 8:51, and right now it's 11:48. So it's been about 3 hours. So the training for this model costs about $3, which isn't a lot compared to the results we got out of it. So this just gives you an idea about the results we got and how much it's going to cost you. When you see terminated right here under instance state, the instance should be terminated and you won't be billed at all anymore. So it should be perfect after this. Great. So let me just go ahead and close down EC2 and also this buckets right here. Or I'll just leave this open and then hop back into the code. Then what we want to start working on is the actual API itself. So if I go ahead and say new file and then api.py, we can start working on the API for actually exposing this model which we have trained, and then building an API which we can deploy to an EC2 instance around that. Alright, so let's build out the API. The first thing we're going to do is just install FastAPI, which we're going to use to build the API itself. So down here I'll search for, I'll put in FastAPI, and then also say pip install FastAPI like that, and now it's installed. So going back over here to API, we can say import FastAPI, or we can say from FastAPI import FastAPI like this. Now we can start out by configuring the logger. So since we're running this inside an EC2 instance, we want to see some logging at some point whenever we want to check how the program is doing. So first of all, I'll configure logging. So I'll say logging, and then we'll need to import this as well. So I'll say import logging. So logging.basicconfig, and we'll just set this to info. And then I can say logger, which is what we're going to log through, equals logging.getLogger name. Then we can create some global variables which we'll need in different endpoints. So these are variables, kind of like instance variables in classes. We can use them in different places in the code. So we'll first of all say global variables. Then I'll say synthesizer equals none. Reference style, which is the audio clip we want the text-to-speech to sound like, we're going to set that to none as well. And we can now define what happens whenever the server is started for the first time. So first of all, I'll say async def lifespan. I'll pass in the app FastAPI. And in here, we'll define what happens when the application starts up. So right now I'll say pass, and then create an app down here. So I'll instantiate a new instance of FastAPI. I'll pass in the title. That is just going to be style TTS2 API. I'll put in a lifespan as well, which is going to be lifespan. So the one from right up here. Great. So this will instantiate the app, and this will define what happens when the app is instantiated. So first of all, we would like to be able to reach the following variables out here. And because they're global variables, we need to say global, synthesizer, comma, reference style, like so. Then we can just do some logging. So we'll first of all say logging, loading, style TTS2 model. So this we'll be able to see whenever we run the logs in the Docker container. Now I would like to try and load the synthesizer. So I'll say synthesizer equals style TTS2 inference. So that is the model, the class we made right in here. This one. So I'll just take that and create a new instance of this. We'll need to import this though, like that. And then we can say config path equals, and this should come from an environment variable. So we'll just go ahead and say import OS, and then we can go ahead and say os.get environment variable. So this one should be called config path, and we'll also pass in a default value. This will be models, libretts config.yml. Good. Then we can pass in the model path too. This is going to be model path instead of config path, and we'll pass in models libretts2, and then this specific checkpoint, which we fine-tuned. Now after this, we can just go ahead and say logger.info, and then model was successfully loaded. Like this, just so we know it if we do check the logs. Cool. Then if this does not work, we'll catch this in an exception. So we can say catch exception as E, and then we can say logger.error, and then fail to load the style TTS2 model. And we'll then also raise so we actually get the error. Then we can say outside of this, after we did load the model, we can then say yield. So this is where FastAPI runs and serves all its requests within this yield keyword basically. So where we define this yield keyword. And then we can also define what happens whenever it has run and it is shutting down. So we can say logger.info and then closing style TTS2 model, or simply shutting down style TTS2 API like that. So this is what will run the server and what will happen whenever we do decide to run it. Cool. So we want to define a couple of different endpoints. First of all, I would like to see that the server is running as it is supposed to be, and then whether we did load the model or not. So basically a health check for the server. And then one thing I forgot over here was just the async context manager like this, and we'll need to import this from FastAPI right there. Or this actually doesn't have to be from FastAPI. We'll just import it again. We'll import it again from context lib. So we'll need this to make sure that this is only happening once whenever we start the application, and then all of this will be ran whenever we start the application, and control will then be handed over to FastAPI, and then FastAPI is done controlling the application. We'll then execute the code after the yield statement. So that is basically what this one does. So let's try and go ahead and create our first endpoint. So down here we can say app.gets and then define the route. So this is going to be health. We would like to just define a new function. So if health check. So I'll then say if synthesizer. Then I'll return status healthy and model loaded. Otherwise, I'll return status unhealthy and model not loaded. Good. So let's try and get this to run. So to run it, we'll need another package called uvcorn. So I'll say pip install uvi-corn. And then just add this to the requirements as well. So I'll say uvi-corn. Good. And then we'll go ahead and start up the server. So we can say uvi-corn API app -- reload. This will make sure that if we do make any changes to this file and save it, the server will also reload, keeping the server up to date with what is actually in this api.py file. So let's run this. And now we should be able to access the application on this URL. So we'll go ahead and open up a new terminal. And now we actually see the logs from the server. So this is info API loading style TTS2 model. So that was what we see up here whenever the server starts up for the first time. This is of course only executed once. So whenever this is ready, we should be able to, and it says application startup complete, we should be ready to go ahead and curl into this server and actually check out this endpoint. So let's try go ahead and say curl http and then 127.0.0.1. So this is just localhost. And then we'll say port 8000 and we can then say health, because that is the endpoint we defined right there. We can now see status healthy and the model is loaded, so that is exactly what we wanted. Next up, I would like to define a list of voices you can pick between whenever you do call this text-to-speech API. So I'll say target voices equals, open up a new dictionary, then I'll say Andreas, this will be models, Libri TTS, Andreas1.wav, and then I'll just do the same and call this woman. And if the woman is the one we call, then we'll just use this woman file right here. This allows you to dynamically pick between voices whenever you do call the API by switching between these reference styles. And we can then just create an endpoint as well for getting these voices such that you can show the voices that are available from the front end. So we'll go ahead and say app.gets and we'll call this voices. And we can then just define a new method right below this. So async def list voices. And we'll just return a list of the voices that are available. So we'll just go ahead and do this. So now if let's just see if the server reloaded. So it's just waiting for the server to start up again. So now that it is started up, we can go ahead and curl and just say port 8000 add voices. And now we see Andreas and women are the possible values we can use. So now let's define the actual endpoint we're going to use to generate the speech. So we can go ahead and define a new one down here. We'll just copy this, call this generate under this we'll say async def generate speech, and we would like to pass in a request to this function right here. And this request parameter, or these request parameters, will define with a library called pedantic. So we'll say pip install pedantic, like so. And we can then also take this library and add it to requirements. So I'll say pedantic in case it is not already there, and it is not. So now we can define how the parameters should look for this request. So I'll go ahead and create a new class, text only request, and I'll pass in the base model, which we'll need to import. So we can import this from pedantic, then say we would like to receive a text, which is a string as part of the request, as well as a target voice, which is also a string. So the text is what should be synthesized to an audio file, and the target voice is one of these options in the target voice dictionary. Then we can say that this must be a text only request, and therefore verify that we receive these two at all times, otherwise we reject the request. Cool. So then we can say if length of request.text, because we can also fetch the parameters from this request now and have it typed. We can then say if the length is more than 5,000 characters, so which is quite a lot of text, we'll then raise an HTTP exception. Like this, which we'll just need to import from FastAPI as well. And we'll send the status code for 100, which means bad request. And then we'll just say something like text length exceeds the limit of 5,000 characters. So this is just a guard statement basically to make sure that people don't send requests more than 5,000 characters, so we don't really overload the server. Then we can say if not synthesizer. So if this didn't load up here, if the synthesizer is none, then we'll obviously have an error because we can't do the speech synthesis. So we'll say raise HTTP exception. We'll say status code 500 because that is an internal server error, and we'll just return model not loaded. We can then also say if request dot target voice not in target voices. So if you send in a target voice that is a string, but it says Donald Trump instead of Andreas or woman because that is the voice you want, well then it's obviously not inside this dictionary and we should throw an error. So we can go ahead and say raise HTTP exception. We'll pass in status code 400, so bad request again because it is the user's fault. We can then say target voice not supported, and then we'll just make this a formatted string and say choose from, and then we can join together with commas right here, the target voices.keys. Great. So now we'll take the requests and actually process it correctly. So we'll say try, and then I'll just say reference to the audio path, which is going to be equal to target voices. So we take the request target voice right here, uses it to index into this dictionary, and then if you say Andreas, you'll get this path out right here. So that is what we store in this variable. Then we can say compute style for requested voice, and we'll then use current style equals synthesizer.compute_style. So remember that is a part of the class we created inside the librinference.py file. And then from that we can pass in the reference to the audio path, and we'll then just say logger.info just to let us know if we check the logs that something is being processed. So we'll say using voice and then request.targetVoice from reference to the audio path, like that. Great. Then we can say generate a unique file name, because we'll need to store this file that we generate somewhere on the disk and also upload it to S3 later. So if you have the same file name for multiple requests to the same S3, to the same EC2 instance, you can have conflicts with saving the files. So we'll need to generate unique file names for each request. So we'll say audio ID equals string, and we'll import a library called uuid.uuid4, like this. So let's just see if we can import this, and we could, so that's perfect. So now that we have the ID of what we want to call the file, we can actually construct the file name itself. So we'll say output file name equals a formatted string where we pass in the audio ID .wav like this to signify that it's an audio path. Then we'll say local path. So this is just the file name with the file extension as well. Then we can say local path equals format a string. We'll put this into the temp folder because we'll have to delete it pretty soon after doing the request anyways. And then slash the actual audio file name. So that is where we're going to store the file which we generate with the model. Then we can say split text into manageable chunks. So what I want to do here is split the text into chunks that the model can process. So let's say, for example, you send a bunch of characters that are way more than the 10 seconds that the model is able to handle. So let's say you send a piece of text that's maybe 30 seconds long. Well, then of course we want to split this into multiple segments that are between the 3 to 10 seconds that the model is handled to work with. Otherwise we'll get audio that doesn't make sense at all. So we'll need some way to split the full text from the parameters up here into some chunks that we can then run through the model in a loop and then concatenate all of these text pieces into, audio files into a single audio file, which we can then create an audio file from and send back to the user. So if I go up and create a new method up here, calling this the text chunker, we'll pass in the text we want to chunk and then also a max chunk size. We'll just pick 125 for now. And then we can go ahead and say if length of the text is smaller or equal to the max chunk size, because then we won't really need to chunk the text. We'll then just return the text. So that's just a guard statement. Then we can create a list of the chunks, or the list that is supposed to contain the chunks, the current position, and also the text length, which is just length of the text. So we won't have to do that all the time. We would like to go through the text chunk by chunk or sentence by sentence, and current position is what allows us to track which position in the big sentence we're currently at. So which position in the text we're currently at. So what I'll do is create a while loop, say while current position is less than the length of the text, like this. So we would like to search for sentences from current position to current position plus the max chunk size. Therefore we can say chunk end equals current position plus max chunk size, and we can then say search text. So the specific piece of text we would like to search in is going to be equals to text, and then current position, and we'll cut off at chunk end. So the chunk position is an index and the chunk end is also an index. So we'll take the text, which is just a string, and cut that text into a piece based on these two indexes right here. This will give us a subpart of that original text, and it is still going to be a string. Now within this chunk that we just created, or this search tag we just created, we would like to find out where sentences end within that text. This way we can chunk it into sentences, which is very structured. So we'll say sentence ends equals, and I'll say m.end for m in regex.findIter. So I'll just import regex up here and scroll back down. And we'll put in a regex. So this regex we'll look for sentence ends. So a sentence could end with a dot, an exclamation mark, a question mark, or might even a couple of these. So this is what this current regex here will find, and then this find iterable will then return an iterable to us, which we can loop through. So I'll then pass in this and also the search text right there. So now we should have a list of integers, which is a list of where the sentence ends has been found in the text, which we created up here, search text. Then we can say if sentence ends. So if it did return something, that must mean it has found one of these. And if that is the case, we can then say last sentence end, which is just going to be the last sentence, because if there's multiple sentences within our chunk, we would like to just take the last sentence end. So the last question mark, for example. This means we'll keep all the different sentences within the search text. Good. Then we can say chunks.append, and we'll then append text. We'll cut out from current position to current position plus last sentence end, because this is an index. So we'll take from the start current position to where we found out the sentence ended, and then add that to the chunks array. Good. Else, so if no sentence ends was found, we'll then find the last space within that chunk. So we can add a space between two words instead of within a word. So we'll then say last space equals search text.rfind, and we'll just search for an empty space like this. We can then say if last space is larger than 0, then we'll say chunks.append, and we'll append from current position to current position plus last space like this, and we'll then just also add last space plus 1 to the current position. So with a proper sentence like this, with an exclamation mark, for example, with the sentence ending in an exclamation mark wasn't found, we'll then look for a space within the chunk, and then we can see if a space actually was found. And if a space was found, we'll just take the chunk from the current position to where that last space in the chunk was, and then we'll take the current position, so where we start next time, and then add last space, so that index, plus 1 because last space is just the index of where the space is, and then plus 1 will give us the position after this, so where the next sentence might start. And if we can't find either in a sentence end like this or a space, what we'll do is just cut off the chunk. This is obviously the worst possible scenario, but we'll have to do that as well. So we'll say chunks.append, and then text, and we'll append from current position to chunk end. So we'll just take the full search text right here, and then append that to chunks. We'll then say current position equals chunk end, like this, and then we'll start from where the chunk ended next time we run this while loop iteration. Good. Then we can hop out to this level of indentation right there, and then say while current position is less than text length, and text current position dot is space, like so. Then we'll say current position plus equals 1. So what this does is that if we, after having found the chunk up here, what we do is that we check whether there's any spaces, so any spaces like this, after the sentence or after the chunk. So if there is a space, we'll then get true from this is space, and we'll then just append 1 to the current position. So let's say a sentence ends in 3 spaces, for example. This is a while loop, so it'll just loop 3 times because is space will be true all 3 times. And then the current position will skip all those spaces and make us ready to process the next sentence without these spaces. So we'll basically just skip any leading white spaces for the next chunk. And then one thing we need to handle as well is all the way up here in the start of the while loop. So if this while loop has run a couple of times and the current position is pretty close to the end of the text right here, then there might only be half a sentence left. So if the remaining text does fit within a chunk, we'll then just add that to the chunks array and then just break out of the while loop because we have ran through all the chunks that are within this text. Cool. So we'll just go ahead and say if current position plus max chunk size. This will give us an index, and if this index is larger than the length of the text array, text string, so larger than or equals to text length, then we'll append that as a final chunk, like this, and then just break out of the while loop, and then we should have all the different chunks within this chunks array right here. And we can then just go ahead and return the chunks, and we should then be able to call this text chunker method down whenever we need it. So I think I made a little mistake as well. I'll just go ahead and close down this terminal. So right here in if a sentence ends, we'll need a way to append or to increase the current position. So we'll say current position plus equals last sentence. So last sentence end actually right there. So what we did down here is that every time we hit one of these statements, we'll then append a little bit to the current position, and then we'll move throughout the entire text string right here. But we didn't do that if the sentence ends. So this means that we will maybe just get stuck in an infinite loop because we would never hit this statement up here. So this will just fix that, and then it should actually work now. And we should also be able to go back to generate speech and continue down here. So we want to split the text into manageable chunks. So we'll say text chunks equals smart, or just text chunker request dot text like this. So we split it into chunks and get the array back right here. Then we can just log this as well so we can see it, logger info. And we'll just say text split into chunks, and then we can just format it like this. Format a string, so the length of text chunks, like that. Cool. Now we can create a variable called audio chunks, or we just call it audio segments, equals a new array. So whenever we process one chunk, we'll just add that result of the audio processed, chunk processed, and then audio produced to this audio segments. And then we'll have a bunch of different audio segments which we can concatenate in the end, and then have the full audio. So we can then go ahead and say for I and chunk in enumerate and we want to enumerate text chunks like this. So this gives us both the chunk as well as the index of the chunk. So that's going to be an integer, this is just going to be a chunk, so a string. Cool. Now we'll just log this as well. So we'll say logger.info. We'll put in a formatted string, say processing chunk I plus 1 divided by, not divided by, of length of chunks like this. Cool. Then we can go ahead and actually do the inference. So we'll say synthesizer.inference. We'll pass in the chunk, so that's going to be right as the text. And then we'll also need to pass in a couple of other things. So we need to pass in the following variables right here. These ones have been set by default. So we'll just pass in the text as well as the reference style. So the reference style we'll get from up here. So we can say ref style equals current style. And then we'll just put this into a variable called audio chunk, like that. And now we can say audio segments dot append audio chunk. And then we would like to add a small pause between these different segments. Because we're processing segments in chunks, we want to make sure that the final audio clip sounds nice. So we'll just add a little bit, so 0.3 or something, a bit of empty audio between each chunk, just so it sounds like there is actually a pause between the sentences, like you would speak normally if you were to speak. Cool. So we'll just say if I is less than length of text chunks minus 1, then we'll go ahead and say silence equals numpy, and we'll just need to import numpy as well. So we'll just go ahead and go into requirements and put in numpy, so it's not there already. We can then just open up a new terminal. So open integrated terminal, say pip install numpy, close down the terminal, and then say import numpy as np, like that. And now down here we should be able to use the numpy package. So we'll say numpy.zeros, and we'll just use 24,000 kilohertz, and we'll say times 0.3, so 0.3 seconds of this wavelength. And then we can say audio segments.append silence, like that. So we would like to add this silence between all the different text chunks except for the last one. So that's why we check if the current index is the last one, so the length minus 1. And then I also made a small mistake. I said this was the wavelength. It is actually the sampling rate. So this sample rate times this many seconds will give us a large array of empty zeros, which means no sound, no sound for this amount or for this duration, which will just add the silence basically. So we just add this to the audio segments as well, and then we can move on. So lastly, we'll just concatenate all the audio segments. So I'll say if the length of audio segments is larger than 1, because if it's only 1, we won't really have to concatenate them, just use that last one. We'll then say full audio equals, and we'll again use the numpy package, numpy.concatenate the audio segments. Else, what we'll do is just say full audio equals the first element, which is just going to be that single audio clip within the array. We can then just go ahead and save this. So we'll say SF, and we'll need to just import SF as well. And it's just sound file, so we can go up and say import sound file as SF, hop down, and then just save this audio to our local disk. So we'll say SF dot write. We'll write to the local path. We'll write the full audio in the sampling rate right here. What we can then do is just upload this to an S3 bucket. So we'll say upload to S3. So this saves it to the local storage, and this is where we upload from this local storage to the S3 bucket. So the S3 key can be determined with this formatted string, the S3 prefix. So that is just something we'll need to define. So we'll just say S3 prefix, and then we'll also need an output file name like that. And we can then also create an S3 client to actually upload the file. But first, let's go ahead and define this S3 prefix. So we'll just hop up here somewhere to where we have defined these other variables and say S3 prefix. And we'll get this from an environment variable and then just set the default value as the following, audio outputs, like that. And we'll also just create a variable storing the name of the S3 buckets. And this will also just be an environment variable, and this should be called ElevenLabs clone if the environment variable is not set. So this means that it'll fall back to a specific value if that environment variable is not found. And then while we're up here, we'll just implement a method for getting the S3 client as well, so we can communicate with the AWS API. So we'll just say import boto3, and we'll need to install this boto3 as well. So under requirements, we'll just add that to, open up the terminal, and say pip install boto3, and that should install now. Great. Then we should be able to just create a new method. We'll call this define get S3 clients. In here, what happened there? Well, in this method, we'll say client kwargs. We'll create a new dictionary. First, we'd like to set the region name, and the region should come from an environment variable as well. So we'll say os.get environment variable, AWS region, which will just default to US East 1. And then depending on whether we have the access key and secret key or not, we'll just append those to this dictionary as well. And then just use that to instantiate the boto3 clients we can communicate with the AWS API. So I'll say if os.get environment variable, access key ID, and os.get environment variable, AWS secret access key, like this. Then what we'll do is just append these to this dictionary up here. So I'll go ahead and say client kvargs.update, and then I would like to set the AWS access key ID and also the AWS secret access key, both of which we'll get from this environment variable. So this will have to be this one, and this will have to be this one. Great. Now we can instantiate the boto3 client. So we'll say return boto3.clients, and we'll pass in S3 as well as all these arguments which were created in the dictionary up here. We can then just take these, I'll just move them down here actually, and then also create a new instance of this S3 clients, which we can use throughout the methods. So clients equals gets S3 clients, like that. And we should be able to use this down here to upload it to the S3 buckets. So we'll say S3 clients dot upload file, and we can specify the local path, the S3 buckets, as well as the S3 key, and that should do it for us. We'll then also generate a pre-signed URL, and this is a URL you can use to access the file. So this URL will be valid for a specific duration, so we'll just set this to an hour, and then when you return this URL to the front end through the HTTP response, they'll be able to click the link and then have the file downloaded immediately. So that's what we'll do. So we'll say pre-signed URL equals S3 clients dot generates pre-signed URL. We'll say get object. The bucket which we would like to generate the URL from is this specific S3 buckets, and we would like to be able to access this specific key, so the file name which we just created and uploaded, and then it should expire in this many seconds, so that is an hour. Then after having generated this pre-signed URL, we can actually go ahead and return whatever we need as the HTTP response. But a good thing to do would be to just delete this file from a local file system, because otherwise it'll just stack up and then take up all the space in the file system, and then at one point the API will just not work anymore. So we'll just say background tasks, and we can add this up here as a parameter to generate speech. So we'll say background tasks, and this will be of type background tasks, which we can just import from FastAPI. This allows us to just do specific background tasks as part of the API endpoint execution. So we'll then say add task. This should be os.remove, and would like to pass in this parameter to the following method called right here. Then we can just do the actual HTTP return. So we'll say return, and would like to return at least the pre-signed URL. So we'll say audio URL equals the pre-signed URL. I think we should also return the S3 key. So S3 key equals S3 key. And then because we put everything within a try up here, we'll need to just match that with an except in case an error happens. We'll just say except exception SE. So that is the variable containing information about the exception. And we'll then just say logger.error failed to generate speech, and then we'll just raise an HTTP exception with status code 500, failed to generate speech, like that. As the API though is right now, everybody can just call all of these endpoints. Anyone could just find these two instance IP and just call /generate and have this generate and use the resources on our instance. And that is not very secure, so we would like to implement a solution to secure this with some authentication. Authorization. So what I'll do is create an API key, which you need to use to call our API. I'll call this API key as a variable, and I'll store this in a environment variable. I'll call this API key, like this, and I won't really let it fall back to anything. Now I can just say API key header equals API key header, and we can import this from FastAPI. Name should be authorization, and auto error should just be false, like this. So this is the header that should contain the API key, and this auto error equals false means that it won't automatically reject any requests not containing the API key, this header right here. So we'll just handle that ourselves. So we'll say async def and then verify API key. We'll say authorization, which would be a string, equals header none. And we can just take this and import it from FastAPI as well. So this right here extracts the authorization variable from the headers from the request, and FastAPI will automatically do this. And if the header is not set authorization, it'll just default to none within the code. So we can then say if not authorization, so if it's none, right there, what we'll then do is say logger.warning, no API key provided, and then we'll raise an HTTP exception with the status code 401 unauthorized. We'll just say API key is missing. So otherwise, if we do have authorization, we'll then just check if that authorization key is actually valid. So we'll say if authorization dot starts with bearer, which is what you usually do, and then you can say token equals authorization dot, and we'll just say replace bearer with nothing. This means if an authorization code, if an API key looks like this, and then the API key, it'll then just remove this part, so we have the actual API key, which we can compare against the API key from up here. So that is what we're doing. Now, next, what we would like to do is just say else token equals authorization. So if bearer has not been sent with the request, we'll just have to not do this part basically. Cool. Then we can say if token is not equal to the API key, we'll then say logger.warning invalid API key provided. So it did provide an API key, but it was not valid. And then we can just raise this exception again, invalid API key. Otherwise, what we'll do is just return the token, signifying that it was successfully validated without any errors. And this is how we actually use this method right here. So if you copy the name and hop down to an endpoint you would like to secure, so generate, for example, you can say pass in another another parameter called dependencies equals, and you pass in an array depends, which we'll need to import from FastAPI, and we can then pass in this verify API key as a parameter. So you can take this entire thing and copy it down to the voices as well as the health. And now we should have all of our endpoints secured, such that only us with this API key is able to access it. So if you want to test this out locally, we'll need some way to actually set these environment variables. So I'll go over here, click on api.py and just create a new file in the same directory. I'll call this .env, and here we'll say AWS access key ID. We'll also set the secret key, the AWS region, which is just going to be US East 1, as well as the S3 buckets, like this. So we can then just hop into right here, go under IAM, then just open it up in a new tab, and then we'll actually also need to get the bucket name right here. So ElevenLabs clone, we'll just put this in under S3 buckets. The region will be the same as this one for me at least. You can check a region up here. Then we'll just hop into IAM, find the user we would like to use, style TTS2 API. We can then create an access key, and we'll just say other, next, and create access key. We can copy the access key right here, paste it in under AWS access key. We can also copy the secret key and paste it in under AWS secret key. If we then close down this environment variable, now we have the file, but we also need to actually load it into the server whenever it's running. So we can just go ahead and open up the terminal again. So terminal, and I'll just install a library called .env, like this. And we can then import it up here. Import, from .env import load.env, and we'll then just load the .env as one of the first things we do. So we'll just do that right here. So this means whenever we do run the server, the first thing that happens after the import statements is that we load all the environment variables from this env file into our environment, so we can actually get them down here, right there for example, or anywhere else where we use os.getEnv. Good. And then for the API key, we actually also need to set that. So under env, we'll just set the API key to 12345 for now. And this is just for local testing. Whenever we do deploy it, we won't really need the env file. So this .env thing is just for testing it locally. So let me just check if we need any other environment variables before moving on. We have the API key, region, these keys right there. We do not have the prefix. This will default to audio outputs though, so that is fine. The S3 bucket we do have. The config path and the model path will be defaulted as well, so that is fine as well. Cool. Now I want to do two things before actually spinning up the server. First of all, I would like to change this audio output to style TTS2 outputs, just so we know it in the buckets, because this is going to be the folder the audio clips will be stored in. And then going down, I would like to also make this a post instead of a get endpoint. Now we can go ahead and start up the server. So if I open this up in an integrated terminal, we can say UV icon, API app, and then -- reload. And this should start up the server for us and just load the model file as well. So in the meantime, while this is loading, we can just fire or put in the first command. We'll say curl -x gets. So this is a get request as we defined down here with a get. And then what we would like to get is the following URL. So http localhost 8000 health. Let me see if it finished loading. It did. So we can just try and run this now. And the API key is missing, so we'll just need to put this in as well. So we'll say -h and then put in authorization. And this will just be 12345. And now we see that the request actually works. So that is pretty nice. The verification actually works. Good. Next up, we can try and use the voices endpoint. So this works as well, Andreas and woman. And now let's just try and use the generate endpoint, which is the large one. So we'll say generate, and then we do pass in the authorization key. We also need to pass in another header. This is going to be the content type, which is going to be application at JSON. And we also want to pass in another one. So this is going to be what is within the request. So we'll pass in this JSON body. So we'll just go ahead and say a new dictionary with text. The text we want to synthesize is going to be hello world. This is a test of the style TTS to text-to-speech API. Good. And then we want to also pass in the target voice. So I'll say target voice. That is going to be Andreas, like so. So I'll just go ahead and run this. And now it says method not allowed. So we just need to make this a post instead of a get as well. Like this. And let's just see what it says. So we can see what is happening in real time right here. We did receive the request. And now we see the actual URL that was returned to us. So we can go ahead and open this up. I'll press Command. You might have to press Control and then click the link at the same time. Then you can say Open. And it downloads the file for us. So let me just go ahead and open that up. So I just opened it up and here it is. So let me just try and play it. Hello world, this is a test of the style TTS2 text-to-speech API. Good. So we see that it works end to end basically. So this is on our local machine and we just need to put it into a Docker container such that we can deploy it on the EC2 instance now. We'll use the existing Docker file as a starting point. So I'll go ahead and just say dockerfile.train, copy this and call it dockerfile.api instead. Inside this Docker file, we'll need to make a couple of changes. First of all, I don't want to copy everything. Let me just close this and this. First of all, I don't want to copy everything, so I'll just remove this copy everything command right here. And also accelerates, I remove that. Work directory still needs to be set. And then also we need to set some environment variables. So Debian frontend, non-interactive. And also TZ, time zone, should be etc. And then UTC. This means that whenever you do build the Docker image, instead of it getting stuck in the terminal where the user has to input something such as their time zone, it'll just automatically fill these out and then skip it such that the Docker image build does not get stuck. So this is just something you need to do sometimes when you get specific errors. And because I've built a Docker image like this before, I know that I need to set this to avoid getting this infinite loop where it just gets stuck. Now, after installing these Python requirements, we'll need to run a Python command as well. So I'll say run Python -c, and then I would like to say import nltk.download, and I would like to download .tab, and then I would just copy this command right here 2 times, and I would like to also download and CMU dictionary, like that. And I'll just make this uppercase as well. So inside Libre Inference, we use this library called NLTK up here. So this will download something to your computer automatically the first time you use it. But for some reason, this gives an error unless you do this manually within the Docker container when you build it. That is why we run this command right here. You can try running it without, but then you'll get a command then you get an error, about something missing, and that it advises you to download these following packages. So that is why I do exactly that. Now, moving on, I would like to copy a couple of directories over. So first of all, I would like to, let me just close this and this. I want to copy over utils.py. So I'll say copy utils.py to the current directory. And then I would like to also copy models.py from down here. Then we can just copy it again and copy modules to modules. We can then also copy utils to utils inside the Docker container. We then also want to copy text utils .py. and also to the inside the Docker container root, and then copy Libre inference. We can then say copy API.py to inside, and then also copy models Libre TTS to models Libre TTS to maintain the folder structure within the Docker container, like that. Now we should then copy only the things that we should then have copied only the things we needed to run the actual API. So for example, when training, we wanted this data folder as well with all the audio files, but it wouldn't really make sense in the API to also include these data folders, these audio files, because we won't need them. They are only for training. So that's why we inside this dockerfile.train copied everything, and then inside this dockerfile.api only copy what is necessary for inference. And that is exactly what I did right here. Then we can set some environment variables. So I'll say Python path and torch home. That's already been done. And then we can just say environment variable config path. And the config path, if I go down to the API, it defaults to the following one right here. So I'll just go ahead and paste this in right there. And then we also need the model path. So I'll say model path, and that should just be this one right there. And right under this, I'll set the AWS region to US East 1. I'll also set the S3 buckets, and this should be ElevenLabs clone, if I remember correctly, right there, ElevenLabs clone. So I'll just put this in as well. Then we can put in the S3 prefix, and we'll just remove this to keep it the same. S3 prefix, that should be the following one here. And then the API key. We just need to say env before this as well. API key we'll just set this to 1, 2, 3, 4, 5 for now. You can always change this, and you definitely should change this, but just for testing, that is what we'll set it to. And then to be able to actually run the API whenever this Docker container runs for the first time, we'll need to say expose 8000, so the ports, and then also command uvcon API app, and then also host, which we'll set to 8 or 0000. This is important for it to work inside the Docker container. We'll also need to specify the port, so it'll listen to port 8000 on TCP, and then handle requests from that port only. Now we can also just scroll up and see we have eSpeak being installed, but we also want to we have eSpeak ng installed, but we also want to install eSpeak only. And then under API, we have this .env. This is only for local testing, because when we're inside the Docker container and run that, the variables will automatically be injected like this. So we'll just save this as well. And then if we hop into Libre inference, we can also comment out this one. This is also for local testing as well, to reference where we have our eSpeak installed. But it is going to be installed automatically on Linux right here, so we don't need that as well. Cool. One more thing is that if you don't have an NVIDIA graphics card installed on your computer, like I don't, for example, I own a Mac, you'll need to run another base image than this if you just want to test it locally. So I'll just say from Python 3.9 Slim. And the reason is that because this is installed, it might try and use a CUDA graphics card, so an NVIDIA graphics card. And if it's not available inside the Docker container, it might fail in some cases. But if you do use this, it should work on all devices, also your Mac. And then whenever we want to ship this Docker container to the ECR, so to an EC2 instance, after that, we'll just comment this out and then just go back to this CUDA runtime or CUDA base image. And then this should install all the correct drivers that the EC2 instance will need for it to use its graphics card. But first, let's just test it locally by doing this. And then you can open up a new terminal by clicking right down here. Open integrated terminal, and we'll then just build this Docker image. So we'll say docker build -f dockerfile.api. We'll tag this Docker image as style TTS2 API, and then also just add a dot after that. So let's just go ahead and build this. And now it has finished building, so it looks perfectly fine, no errors or anything. So we can go ahead and say docker run, and then forward the host port 8000. So this is the host port, and we forward that to the container port 8000 because that is where we handle the requests as specified right there. And then we can just go ahead and put in the tag for the Docker image. So that was style TTS2 API, and press enter. And this should spin up the Docker container for us that we just built. And now it is starting up. So we have loading a style TTS2 model, and it should start up in just a second. And now it should be all ready to receive requests. It says model loaded successfully. We can then go into a new terminal and then just find our previous commands by pressing up. We can then try and run a voice command, for example, or a health command if I can find that. So voices right there, that gives us the voices from the server, and in the server, in the Docker container, we can see that the request was handled correctly. Good. Let's just try and run a generate command. So this will take a while probably because it has to load things inside the Docker container for the first time. So we get a failed to generate speech. So it failed to locate the credentials. So what I think we have done, or what I think is the culprit here, is that we have forgotten to put in the credentials for AWS. So the AWS access key ID and also secret access key. So let's just try and go ahead and do that. So if I just put this in right there, and also this secret access key right under this, we can just go into the env file and copy these. And this is not what you should do in production, because these will automatically be injected into the instance environment by EC2 when we attach the role, but this is just for testing locally. So if we just close down this Docker container, build it again, this should take way less time because it is cached now. We can then just run the Docker container again. It is already allocated, so I'll just go into my Docker desktop and close it. We can also just do it in the terminal here, so we'll just say docker ps, docker processes. We can find the container ID and say docker stop, like this. This should stop the old one, and now we can say docker run again. And this should allow us to run the new container. Good. So if we open up the new terminal and just run the generate command again whenever this is ready. And now it loaded successfully and it is ready. So we can just go ahead and run it over here. And then see what happens inside the logs of the actual Docker container. So we get this printout now. We get 177, so that's what we got whenever we ran this command locally, so that's fine. We also get 200 OK. And we see this URL right here. So if I just click this, it downloaded to my local machine. And here is the clip, so I'll just play it.
Here is a quick test.
So it says here is a quick test, so that is perfect. Great. So now we know that it works inside this Docker container. To be able to make it work with a CUDA GPU, we will need to use this other base image. So just paste this back in, and then you can remove these two as well, because we won't really need these in production. And then we can go ahead and build the Docker image again. So docker build. And then we'll just leave this running. And then whenever this is ready, we can push it into the ECR registry. So what we need to do that is just go into repositories, find the style TTS2 API, then say view push commands. We can then use these to push the build image up into this repository. So we'll just go ahead and do that in just a second. So I'll come back when this is done running. So it just finished up here and it looks fine with the build. So we'll just copy this authorization command first of all. Paste this in right here. Go ahead and find the next one. So we just built the image, so that should be fine. So we can go ahead and tag it now. So I just had a small issue where I had to go into AWS and then under security credentials find my root access key, because that's how I do it, and then hop in here and say AWS configure. This means I set up the AWS console to use my root user instead of using the style TTS2 API user. So if you get an error, you'll probably want to do something like that by saying AWS configure and then using an access key from either a user that you create or from the security credentials page right here, where you can see the root access keys. Great. So now that I just fixed my little AWS CLI issue, we should be able to just say docker tag and then do it like that. And now we can just say docker push and then go ahead and push the Docker image to the ECR repository. In the meantime, while this is pushing, we can go ahead and set up the next repository which we'll need. So we can go over to GitHub and then search for seed VC, and we'll find the following repository right here. We can then say code HTTPS and then just copy that. So what this will do is help us build out the feature zero-shot voice conversion and singing voice conversion with real-time support. So we wanted the feature over here called voice conversion. So that is basically what we're going to start on now. So first of all, I would like to open up a new terminal, a new window. So I'll say new window over here. And then I would like to go to open folder, documents, and then find my repository. And then just open up the root of that. So this is where we both have the fine-tune repository and the style.js2 repository. So I'll just go ahead and open up a new terminal right here. So I'll say open integrated terminal. Then I'll say git clone and paste in what we just copied. This should just take a couple of seconds, and then we should have the repository cloned down. And now that it has been cloned down, we can go ahead and open it up. So we'll say open folder, ElevenLabs clone, seed VC, and then open. And now we see this new repository right here. The first thing I would like to do is just go to Shift Command P and then say create environment, venv. I would like to use 3.10 again. And then we can use requirements or requirements.mac. I'm using requirements.mac because I'm on a Mac. Otherwise you will need to use the other one. So you can just select that one and then press OK. So this will just install for a couple of seconds, maybe a minute or so, and then I'll return once this is done. So now the installation is finished and the environment has been selected. So I can go ahead and close this down. I've also zoomed in a little bit for you guys so you can see better. Perfect. So going back to this GitHub repository, if we hop down under usage, here's what we can see. So we just installed these requirements, which is fine. And then it says checkpoints of the latest mod release will be downloaded automatically when the first inference is ran. So we can go ahead and try out this command line inference and then just see if that works straight out of the box. So I'll copy this right here, hop back into the seed VC repository and open up a new terminal. I'll just paste in the command straight away. And then we can see that we need a couple of different things. So first of all, we need a target, an output directory, a path to a checkpoint, and a path to a configuration file. So if we just go ahead and find examples and source, these are the different sources, and these are the different references. So if we first of all just remove this checkpoint right here, and also config. So I'll just go ahead and delete that and that. We can then just go up. And then for the source up here, I'll just delete this placeholder. And then under examples, source, and then I'll take this one for example. We can just play this.
They can't order me to.
So we'll just take this and right click it and say copy relative path and paste it in right here over under source. And then I'll just reference where it is by putting a dots and a / like this. Good. And then the target, so what we want to convert it to. So this is the voice we are converting from and what they're saying. And this is the voice we're converting to down here in the target. So the voice we want to convert to should be something like this maybe.
You don't know how much trouble you've got.
We can try this out. So we'll just say copy relative path again. Say dots / put this in. And then under output directory, we'll just say .forward, and then we'll say reconstructed. Like so. And that should be fine for us. I'll just press enter and then just see what happens. So as you see right here, it is downloading something. It's downloading about 400 megabytes and it's a PTH file. So that means it is the model file it is downloading right here. And that is because we're running the first inference. So after downloading this, it should start the inference and it might take a while, and then we'll see a file over here when that is done. So the command executed, but we got an error. So it says command not found, and then it lists out all the different flags. So we'll just press up once again, and then just see if we can fix this. So first of all, I just want to remove these comments just to make sure they aren't causing any problems. So I'll just remove this as well. And then there's another one right here. And right below that too. Now what I now want to do is just press delete ones to make sure they're on one single line. So delete space and then just do that for every single one. And I can then press enter again, and then hopefully it works this time. So now it finished up and we see this folder reconstructed. So if I go under that, we should be able to see something that works. So let me just try and play one of these.
They can't order me to stop dreaming.
So let's just check out the source again. So for the source, we were using the following one right here.
They can't order me.
And then we were trying to transform it to the following voice.
You don't know how much trouble.
And let's just see how that goes.
If you dream a thing more than once, they can't order me to.
So it sounds pretty much like the new voice. So what I now want to do is just try and go ahead and test it with my own voice. So I'll add my own voice to the targets over here, or the references. So I'll just go ahead and go back to the following repository, style.ts2, and then under models, lib.ccs, we see the different ones we tested with earlier. So I would like to fine tune it to my own voice, for example. So I'll just press Andreas1.vav here, go back, and then under reference, I can just put it in my own voice. We would like to use the cool. And then down here under target, I'll just say reference / Andreas1.vav and just press enter. And this should create a file and reconstruct it in just a second. Cool. So it just finished up. It took about 10 to 15 seconds. And now this is the finished file.
They can't order me to stop dreaming.
So I wouldn't say it sounds exactly like me. So let me just try and play this raw audio clip from me. We would like to use and this is me.
They can't order me.
So I think we can do better. So let's try and fine tune that and just see if the voice sounds even more like me. So since we have already fine-tuned the other model over here, style.ts2, we can just take the same data and use that to fine-tune seedVC as well. So if I hop under data and then go to VAVVs, just copy this folder right here, hop back over to the root folder, so I'll just press right here and just paste. We now see VAVVs. I'll just rename this to the dataset, and this should allow us to just use this folder to fine-tune the model with. Now going back to the browser, we can check out how fine-tuning actually works with this model. So scrolling down to fine-tuning or training, we see that we only need to run this command basically. So what it says up here is that file structure does not matter. Each audio file should be between 1 and 30 seconds. Speaker labeling is not required, so we don't need transcription. And the training data should be as clean as possible. So this means that using a studio mic like I'm doing right now is obviously a great thing if you want to use this model to fine-tune on your voice. And then also we should pick one of the following for fine-tuning. So this model right here, or this configuration, is for real-time voice conversion. This is for offline voice conversion, so that is going to be our use case. But there's also singing voice conversion if you want to do that. So we'll just use this one for offline voice conversion. And we'll do this, or point to this in the config parameter or flag right here, whenever we run the train.py command. So what I would like to do is just reuse the Docker file from the style.ts2 repository. So I'll just take this Docker file.train and copy it. And then I hop over to seedVC, press in the root, and then just paste it in. Now in here we just need to make some modifications, and then that should allow us to put it into an EC2 instance and fine-tune this model as well. So I'll just take this terminal and shut it down. And then I first of all just want to remove speak and g from over here because we don't really need that. Also accelerate we don't really need. We still want to copy the entire directory from right here, including our dataset, into the Docker container, so we'll do that. And this models folder is not really existent anymore, so we'll just remove that as well. I'll then add a new environment variable called hfhubcache to tell Hugging Face libraries where to cast it, or where to store the cached downloaded models. So I'll say hfhubcache, and this will be /app, and then I'll just need to say env. This will be app check points, and then Hugging Face cache runs like this. So you might see this being referenced other places inside the repository. So inside inference, for example, we see the following right here again. So this will be HF cache like that. And this corresponds to the checkpoints, HF cache, and then models right here, which are downloaded automatically. Now all we really need to do is when we go over here and find this train command is just to take this and paste it in instead of the existing command. So I'll just take all this, paste this in instead, and then we can just add some backslashes to make it know the difference between the lines. So I'll go ahead and do this. And then the path to the configuration file, that should be from over here. So we wanted offline voice conversion. So I'll just take this path and put it in. So, it was over here. So going down, seed VC repository, the config should be the following right there. The dataset should be dot or just dataset like this. The run name will just call training run. The save every will set to 100 instead. Max steps will just set to 300 instead as well. And then we'll just leave everything else as it is. This again, when we run the Docker container, we'll take all of this and put it into this entry point.sh, or when we build the Docker container, we'll take all of this and put it into an entry point.sh file, so an executable shell file. It'll make it executable with this command right here. And whenever we then start the container, it'll just run that shell file to start the training process. I just want to make sure that two folders specifically exist as well. So we'll go ahead and say run make directory like this, a link command, and then -p, and then the first one is checkpoints, HF cache, and the second one is runs. So we're referencing checkpoints, HF cache a couple of places, and then also over here, all the runs will be stored on the runs, all the checkpoints will be stored on the runs. So just want to make sure that this folder exists as well, just so we don't get any errors. This probably will not cause any errors, but it is just in worst case if we haven't done this. So I just want to make sure that it exists, so it just runs perfectly the first time. We can then just create a new terminal right there and say docker build. We'll then reference by saying -f the docker file .train and tag it with seed vc fine-tuning and just start this building. We'll just need to add a dot after that as well though. And now this will start to build. And over here in our style.js2 repository, we see that everything has been pushed. So that should be perfect. And now that should be ready to start it up in an EC2 instance whenever we are ready to do that. So over here in the Elastic Container Registry, if we do a refresh, we should be able to see the latest image that takes up about 7 gigabytes. So that is perfect. Now we will just wait for this to build, and then we can push that as well, just to the other repository right here, seed vc fine-tuning. So if I just go in here, we should be ready in just a second to push it up. And the image just finished building, so we can go back, take this authentication token, paste it in seed vc, and just sign in with that. So login succeeded. Now if we go back, we can take this docker tag command because we already built it, paste that in as well. And lastly, we can run docker push just to push it up to the ECR registry. So this should take a while as well. Over here it's finished. It's about 7 gigabytes, so that is perfectly fine. We can just close this terminal down, this window down now, because we won't really need that anymore. And then we can let this new one upload to ECR. Now the image has successfully been uploaded to ECR, so you can see it right here on the latest. So what I'll do is hop into EC2, open that in a new tab, and then just go ahead and launch a new instance. I'll call this seed vc fine-tune, like that. And then I would like to pick the PyTorch AMI. And then for the instance type, I'll pick g5.xlarge. Oh, that's the AMI. For the instance type down here, g5.xlarge, like we did last time as well. Then scrolling down, we'll choose a key pair. We'll leave the security group as it is, set the config storage to about 100 gigabytes, and under advanced details, we'll select an IAM profile, so we can use this role right here with the permissions to upload to an S3 bucket. Good. Going over to launch instance, we'll just wait for this to finish, say connect to instance. We can then just connect again. And then go ahead and pull down the Docker image whenever it is ready. So we just got this error right here. So I'll just go ahead and refresh. I don't think the instance was ready yet. So we'll just wait for a second for it to be ready. And now that we're ready, we'll follow the exact same procedure as last time. So we'll say sudo usermod -a-g docker ec2 user like this. So it's -a. And then we'll go ahead and say new group, Docker. We can then say AWS ECR, get login, password, --region, US East 1, pipe symbol, Docker login, --username, AWS, --password, standard in, so stdin. And then we'll just go over here to our repository and just copy one of these. And then I'll hop back in and paste it in. And that should log us in, so we'll be able to pull down from the Elastic Container Registry. Now, what we want to do is just pull down the image that we just uploaded. So we'll just go to view push commands and just copy this real quick and close this back again. Hopping back in, we'll say docker pull and just paste this in. And this will just pull for a couple of minutes. Now that the image has been pulled, we can go ahead and run the Docker container. So we'll say docker run -- GPUs to give it access to run with the GPUs, all -d --name, and we'll just take this entire thing and paste it in. Or actually, we'll just say seed vc container, and then we'll paste this in right after, like this. That should allow us to start the container in a detached mode, so it'll run in the background, and then we can go ahead and fetch the logs as soon as it is started up. So this should just take a moment. And we can then say docker logs -f, and then it'll be seed vc container like this. And we'll then just wait for this to start. The model is now training, so what you'll see is printouts like this where it saves, and then you'll see some printouts during the steps in the epochs. So I'll just wait for this to finish and then come back after this is finished. This should take a shorter amount of time than when training Style.js 2, just for your info. So after only a couple of minutes, the model file stopped training. So what we'll go ahead and do is the exact same procedure as last time as well. We'll say docker processes -a. We can then find the Docker image, which exited a couple of minutes ago. 1 minute ago. We'll then just copy this container ID and say docker starts and just paste it in right there. We can then say docker exec -it. Paste this in again, and then just say bash. This allows us to enter the Docker container. We can then just say ls just to see what's going on, and then we have all the different files and also the model files somewhere inside this directory. Now let's go into the runs folder, so cd runs, and say ls to list the files. We can then just find the folder training runs, which we'll also change directory into. Check what's in here, and then we see a couple of different things. We see all the different models. And then we also see the printout up here right after or right before exiting, where it says final model saved at runs, training runs, fine-tune model.pth. So this model right here is what we would like to upload up to the S3 buckets and then download down to a local computer so we can test it out. So right now, if I just say AWS, it won't work because we need to install that. So I'll say AWS get and then update. apt gets updates. So updates like that, and then just let that run. And then we should be able to install the AWS CLI right after this. So we'll go ahead and say apt get install -y AWS CLI like that. And then, so we just got an error. So let's just check out what actually happened. So if we just say apt get, it seems like it couldn't find the command apt get. So we'll just try and write that again. And let me just see if we're even inside the container, which it seems like we are not. So I'll just say docker ps -a, and then it exited 2 minutes ago. So we'll just say docker start again. and hop back into the container. So docker exec, like that. Then say ls, change directory to runs, change the directory to training runs again. And then I'll just see if we have the model file still, and we do. So if I now say apt get, and then install -y AWS CLI, hopefully this will work. It did not. It can't find the package, so we'll just say apt get update, and then just wait for this to finish. And we're still inside the Docker container, I can see, so that is perfect. And now we should be able to run the apt get install -y AWS CLI. So this will just take a while. And here I'll just use some area codes again. So I'll just say my area, like that. And just wait for it to finish up. And now that it is done, we can say AWS and see the command line working. So now I'll say AWS s3 cp to copy. I would like to copy from the following folder. So this, let me just say ls. I would like to copy this model right here. So I'll say AWS s3 copy. Copy, and then say // to pick from our current folder. And then I would like to copy into the s3 buckets. And this will be s3 : / ElevenLabs clone models. And let me just see what naming we're doing. So this is going to be style.js2 models. We'll just say seed vc models, and that should be it. Let me just press enter and wait for this to copy into the s3 bucket. So in a minute we should be able to see the folder, and we do see the folder now, and we'll just wait for the entire file to copy into the folder. And that should be done now. So heading over here, pressing seed vc models, we should see the model right there. Good. Hopping back into our seed vc directory, we can go ahead and open up a new terminal in the root, and I would like to copy this file from S3 and down to my local computer. So I'll say AWS S3 copy, and we'll copy from the S3 buckets, and then ElevenLabs clone, and then seed vc models, and then ft model.pth, and we should use an underscore instead of this dash right there, like this. And then we would like to copy it into our local folder system. So that is going to be runs, training runs, or training run, and then ft model.pth, and then press enter. So it can't find the model file in the S3 bucket. So I think we just need to say s seedvc models, like this. And then it should find the model like this. So now that the model has been downloaded to our computer, we should be able to see it under runs, training run, and then right here. To run the new model, what we can do is follow this guide from inference up here. So we can actually just call the same command line inference prompt like we did right here, but just define the new path to the checkpoint, and then also the path to the config we used when we did train the model. So going back here, we just need to change a couple of things. If I paste in the command we used earlier, this is how it is going to look. It is the exact same command as we used whenever we tested out the model for the first time. But we have just added these two properties as well of flags, checkpoint, which points to runs, training run, fine-tune model.pth, and also the config flag right here, which points to configs, presets, and this is the one that is for offline voice cloning. Now, if we hop into the inference.py file, like this, and then check out how it works, this load models method is ran whenever we run the inference. So going down here, in main, load model is the first method that is run whenever we run inference like this. So if we just check out how it works, if we see the arguments, we can then see that the checkpoint and config flags that we define down here are only actually applied if the f0 condition is false, or true. And right down here, we have just set the f0 condition to false, and it is not going to work. This f0 condition, if we hop under the documentation right here and just search for f0 condition, it says set to true for singing voice conversion, and that is definitely not what we're trying to do. we're just trying to do some offline voice conversion. So we don't really want to set this F0 condition, we just want to keep it false. So I'm not sure why they only want to load in, or the authors of this library only want to load in the custom checkpoint and config path if this F0 is set to true. So we'll just go ahead and change this a little bit so that we can use our custom checkpoint and config file, even though we keep this at false. So what I'll do is just press down a couple of times and say if args.checkpoints is not none. If that is the case, we'll just copy these two lines up right here. So if they're set, we'll just set these, and then we'll put in an else statement, else, and else, then we'll just take this, copy it down, indent these a little bit, like so. Also remove the following line right there, remove the else statement, and then down at the same indentation level as the if and else right here, we'll just go ahead and say if not args.f0 condition. We'll just set this to none, and then else we'll go ahead and do the following lines right here. So this should allow us to actually just use the checkpoint and also the config path whenever they're set down here. And then if they're not specified, it'll use the custom models, or sorry, the models from that is made by the researchers, so the default models basically. And then what I would like to do is just say print and then loading fine-tuned models, just to make sure that we can actually see it when we run this command, that it is running as it is supposed to do. So if I just open up reconstructed, we shouldn't see anything right now. And then I would like to convert my voice from the source S2.
Some call me nature.
To my own voice, so Andreas 1. We would like to use and I would like to do it both with the fine-tuned model and without, just so we can see whether there's a big difference, a small difference, and whether it was worth it or not. Because if we hop into the documentation, it does say zero-shot voice conversion, so it should be pretty good at just predicting my voice and creating an audio clip with my voice without any fine-tuning, but we'll go ahead and see whether the fine-tuning made a difference or not. And before moving on, what I'll actually do is just take the EC2 instance and shut it off. We won't really need that anymore. So we'll say instance state and terminate, and then just leave this to shut down. Great. So first I'll run it with the checkpoint. So the checkpoint is set, and also the config right here. So if you haven't written this in yourself now, go ahead and just pause and input this command right here. Make sure to specify the source file you would like to convert from, and then also the target right here, which you would like to convert to. So I'm just using my voice, but you can use any voice over here. You can use the Trump voice or any voice you would like to. Great, so I'll just go ahead and press enter and wait for this to finish. And it just finished doing the inference. So I'll just say fine-tuned 1. And I'll then just run the exact same command again. So going back to terminal, I'll just press up once. And then I'll remove the two flags, so config and checkpoint, like this, and press enter again. And then in the meantime, we'll listen to the fine-tuned clip.
Some call me nature. Others call me Mother Nature. I've been here for over 4.5 billion years. 22,500 times longer than you.
So it sounds a lot like me, to be honest. But now that the unfine-tuned version is ready, we'll just say old, or we can call it default 1, and then just see if we can hear a difference between the defaults and the fine-tuned version. So let's just go ahead and play the default one.
Some call me nature. Others call me Mother Nature.
So let's just try and play these from the start, just the first couple of seconds. So the default one.
Some call me nature. Some call me nature.
So the only difference I can hear is that my voice sounds a little bit less shaky in the fine-tuned one, but they're actually pretty close. So I'm not even sure the fine-tuning made a massive difference. Although, even though it did only take about 2 to 3 minutes for it to fine-tune, so it might have been worth it just for a couple of percentage gain that we achieved from doing the fine-tuning. So again, just to list them out side by side, I'll just skip to second 10, just so you can hear the difference.
22,500 times.
And the fine-tuned version.
22,500 times longer than you.
So as you can hear, the difference is not massive, and that is because the model is pretty good at it already as it is. But we have now done some fine tuning to at least see if it would make a difference. And the difference is pretty minuscule, but it didn't take a lot of resources to do it, so it's probably fine we did it anyways. So with the fine tuning done and the inference file already being set up, we can go ahead and just create an API.py file over here. So I'll say API.py, and we can use this to build out the API. I'll first of all just create a new window and then open up the repository right here. So documents, repositories, ElevenLabs, and then find style.ts2, because we already created an API once, so we can take a lot of this and just reuse it, to be honest. So I'll go ahead and just paste this in right now. And then first I'll scroll all the way up. So I'll just save. And then we first would like to remove this right there. Install Boto free, so go ahead and add this to the requirements.txt. Then we would like to make inference something we can call from within the API.py. So we have load models, which we can already import. We can just go ahead and say from inference, import load models. But we don't really have any method to do the inference. We only have a main method down here. So a main method. So we want to convert this to a function, which we can just call. So first of all, I'm going to say def process voice conversion. I want to pass in the models, a source path, a target path, and then also an output path, like this. So I'll just call this source actually, because it is called source down here as well. And then I'll call this one target. And then I'll just go ahead and see if there's anything called output down here. Any path like that. So args.output. So I'll just call the argument up here output as well. So output. And now we can just go ahead and add these different parameters. So F0 condition, auto F0 adjust, this semitone shift. We'll just call this pitch shift. I just want to make sure that all the names do match. Source and target name we did define already. So target name and also output. Diffusion steps we are missing, as well as length adjust. We're also missing this one. So I'll just go ahead and add a semicolon right there, or colon, sorry, and then just press save. And then we should be able to remove these about now. Great. And then we can go ahead and check out what default values these actually have. So hopping back into this repository right here, if you go under usage, you should be able to see the following default values right there. So diffusion steps, for example, is going to be 25. So I'll just, 25 is going to be. So diffusion steps, I'll just set to 25. Length adjust, that is going to be 1.0. And then F0 condition is going to be false. Auto F0 adjust is going to be false as well. And then pitch shift is going to be 0, so semitone shift. We can then see that inference CFG rates is 0.7. So we'll just go ahead and say 0.7 right now. And this way we can fill out all the default values. Output should not be a default value, by the way. Also not target name or source. Great. So let's just try and say args dots and see if there's any places where the arguments are used. So output, we can just simplify to this. Same down there. And then going back up, F0 condition, we'll just simplify right there as well. Like that. And then also up here. And then the checkpoints. Oh, sorry, this is the wrong method. This is the load models method. So we'll just do that in just a second. Anyways, the args should be all fine down here in this method. So these are all the load models method and not the inference. Great. So this inference method should be about done in just a second. So hopping down to process voice conversion, scrolling all the way down to where the file is saved. We both saved the file right here. So we'll just go ahead and say we only save the file if the output is provided. So if output, then we indent the following lines right there. And then in any case, what I would like to do is just return the waves. So VC wave, like that. And then we can go ahead and say .cpu and also SR. So if you click this right here, hop all the way up, we then have the sampling rates and also the audio waveform. So with this, if you do not provide an output path, the function will at least return the VC waves, so the audio waves, and then also the sample rate, so you can determine what to do with it on your own, sorry. Then hopping into the API.py, we can go ahead and import this as well. So process voice conversion, and then we can clean up this API.py just a little bit. And I just forgot we need to hop back into load models and just handle these args as well. So instead of these arguments, I would like to just find everywhere this is used, and then we see FP16, for example. We also see F0 condition. So we'll just copy this from here. We also see a checkpoint. We see a config. Let me just see what else we have. Maybe that is it. So if we can remove FP16 right there. Also checkpoints. Oh, sorry, args in front of these. And lastly, this one. The F0 condition is going to be false. The checkpoint, if not defined, will just default to runs training and then the fine-tune model. So we'll just find runs fine-tune model. So I'll right click and say copy relative path and paste it in right there. I'll just add a // to it as well. And then for the config file, I'm just going to use configs up here and then presets and then the following one right there. So this is the one for offline voice conversion. So I'll just copy that relative path as well. And then just set that as the default value if no value is provided. Like this. Great. Hopping back in here, we would like to determine FP16. We'll just make that not a parameter, but just define it right here. FP16. And right now it is defined just as false. So we'll just define it as a true if CUDA is available. So we'll say torch.CUDA is available. So if you do have a GPU, this will be true. And this is because floating point 16 can increase computational speed on GPUs that do support it. But it isn't as optimized for CPUs as for GPUs. So we'll just go ahead and set it if the graphics card is available. And we then just need to see if we how to return anything down here. So right now we seem to return all the things we need, so that is perfect. This means we can just call load models in here and just use it in conjunction with process voice conversion. So first I'll remove this first one and then rename synthesizer to models. That's going to contain whatever is being returned from load models up here. And then scrolling down to the server startup down here, what I would like to do is just say global models and then loading seed VC model. We'll then just go ahead and say models equals load models from up there. And then we can say seed VC model loaded successfully, and then fail to just load model like that. And then we'll say shutting down seed VC API. And this one we'll just call style.js, seed VC API as well. Now for the target voices, we'll just reference the files under examples up here. So we'll say Andreas1 as Andreas. So I'll just go ahead and copy that relative path right there. And then we would like to use this one as well. Number 2, for example, or just number 1.
You don't know how much trouble.
So we'll just copy that path as well. Right there. Add it right here. Say woman. And then we can just add Trump as the last one. So we'll say Trump 0. And this will just be Trump. Great. So now we have the target voices nailed as well. Now this text chunker method is not really needed because it is voice conversion. So we'll just go ahead and remove that. Scrolling into inference, if we search for chunk, we can see that a lot of chunking is already done actually. So it'll chunk automatically for us as far as I can tell. Split source into chunks, generate chunk by chunk and stream the output. So all of that dirty work has been done for us. That is everything we did ourselves with Auth.js 2. So that is very nice that we don't have to do that basically. And then for this request, we'll just call this voice conversion request. And we would like to receive a source audio key. That is for the source audio in an S3 bucket. And then also the target voice, which is of type target voice up here. So either Andreas, woman, or Trump. We'll just call this convert instead of generate instead as well. And then just use this correct name for the request down here. Now, first I'll just say if not models, then we'll go ahead and say model not loaded. And then this text criteria up here is not needed anyways, so we'll just go ahead and remove that. And again, if the correct voice is not specified, then we'll just throw this error again, target voice not supported. So this ref audio path we'll just call target audio path because it is the audio path over to the target inside this folder right here. So the references. Now we can just remove this current style. We don't need to compute that. And then we can say converting voice, and that is going to be request dot source audio key to, and then we'll just go ahead and say request dot target voice as well. So now that is done, and then we still need to generate a unique file name so we can put it on the local machine, and then also whenever we want to upload it to the S3 buckets. We want to remove this chunking work as well, so we'll just go ahead and remove that. And also this entire for loop, we won't need that as well. So I can go ahead and at least remove down to this part right there. And then we might need these other things, so I'll just leave those as they are. Now we can prepare an example. So if we hop into examples and sources, we can just take one of these and upload them to an S3 bucket. So hopping into the ElevenLabs clone, and then ElevenLabs clone right there, we can say create folder. In here we'll say seed vc, and then if I just check out Excalibur, we can see what we want to call the folder. So under S3, we call it seed vc audio uploads right there. So we'll just create this folder, just put in this extra hyphen, and then just say create folder. Now we can go into that folder, just upload a new audio clip, just so we can test, add files, and then we can hop under repositories, ElevenLabs clone, seed vc. We can find examples, and then source, we'll just take source 2.
Some call me.
Perfect. And then we'll say open, and we can then upload that right now. So this should just set us up for an example we'll do in just a second. So what happens whenever the user calls this in real life, remember, is that the user uploads it's right over here. The user uploads an audio file to an S3 bucket, and then the user does a call to this API, which will then download this audio file from the S3 bucket and do the voice conversion. So first we need to do this download from the S3 buckets. So hopping back over here, we can just go ahead and do that. So we'll say logger.info, and then downloading source audio. Now we can say source temp equals named temporary file, and we just need to say suffix equals .vav, and then just go ahead and import this from temp file right there. Now we can say try, and we can use the S3 client. So remember the S3 client we created in the other API. So from this method right there, we can just go ahead and use that again. Of course, we need to just change a couple of things here in a bit, but we'll just go ahead and do that afterwards. So we can try and say S3 client dot download file object, and we would like to download from the S3 buckets. We would like to use the following key, so we'll say key equals resource.source audio key, and then we'll say file object like this equals source.temp or source temp. So we'll store it in this file object right here, which is just a named temporary file. Great. Now what we're going to do is say source temp.close. And then if this fails for some reason, we'll say accept exception as E. And then we can say os.onLink. And then pass in this source temp.name right here. So this just allows us to download a specific file to the system, and this will then delete the file if any exception happens. And what I just want to return to the user is just HTTP exception 400 is source audio not found. So this would for sure happen if the source audio key is wrong. So we'll just go ahead and say 404 because the source audio file is not found. I'll just go ahead and delete this line as well, and then say process voice conversion. I'll put in the models. I'll also put in the source path. So that is going to be source temp.name, and then also the target path. So that is going to be target path. So, and that is going to be target audio path up here. And I'll just name this as well. So I'll say source, and then also models equals models, and the rest of the parameters should be optional. Perfect. We just need to define the output though. So we'll just set that to none or not even pass it in. So we'll just say output to none, just so we can return, have the wave returned. So VC wave and the sample rates, and we can then use this to generate the audio file ourselves whenever we do need it. So the file was downloaded up here by S3, but the file wasn't deleted. And then we used the file to to process the voice conversion with the model and generate the waveform. So now that we have the waveform and the sample rate so this is the converted voice, we can then just go ahead and delete the original file up here. So we'll just copy this line and just do this right after. And then we can go ahead and say torch audio, like this. And we'll just add this import .save, and we'll save it to a local path. And we need to pass in the waveform and also the sample rate. And I just want to make sure we have torch audio installed already from the requirements, and we do. So that is great. This S3 key should be exactly the same, and also this command for uploading the file. What I'll then do is just return the pre-signed URL. So the URL with the link, so just the link to the file up here in the S3 bucket basically. And then also the S3 key, so you can save it in the Next.js backend and track the history of the user's created files. Down here, I'll just change this to error in voice conversion and just do this both of these places. Down here, we can just check if models instead of if synthesizer, and these two methods should just be the same. Good. So this should actually work out of the box. I'll just go ahead and press Shift, Option, and O to clean up all my imports. This should remove NumPy, for example. We don't really need that. RE, sound file, didn't remove that though. So I'll just go down and check in problems. Main is gone, so we'll just comment out main because we didn't, we removed it. And then we should be ready to go. So let's open up this new terminal right there and then see UV icon, see if that's installed. We just need to check inside requirements as well. It is not, so we'll just go ahead and add it down here and then go back into API.py. So we'll say UV icon, API app, and then just run that. And this should boot up the server for us. And now it just need to load the model, and then we can go ahead and create a request to it in just a second. So I'll just open up, it's ready now. So I'll just open up a new terminal and then say curl, and I'll say HTTP and then localhost port 8000, and then I'll say health. So API key is missing obviously, so we just need to add that as well. So what I would like to do is just generate these curl commands. So I'll open up a Copilot and just generate them while we're talking, and then you can just copy the commands if you don't have Copilot. So I'll just say generate curl commands for each endpoint to test it out, like this. And then of course we just need to change a couple of things as well. I'll just close down this for a moment. I just remember that we need to change these prefixes down here. So we need to change the output for the buckets. So going back to our diagram, we can find the S3 bucket over here. So that's going to be seed VC outputs right there. And we then just need to say pip install .env, close down the terminal once again. And then up here, I'll just say from.env import load.env, and just run that as the first thing. And then we can just take the env file over here and paste it into this other repository. We don't need to change anything as far as I can tell, so that is perfect. Good. Now let's serve it again. So we can go ahead and say uvcon API app, and then just pass in the reload. Great. And now we can open up Copilot again, and then just run this prompt. So we'll say generate curl commands for each endpoint to test it out. We'll then just attach api.py, just so it knows the endpoints. And that should generate in just a second. So it seems like it just generated, so we can go ahead and open up a new terminal, put in the first command. That is going to be the following: curl -x get, and then we put in the localhost, and then also an H flag, and then authorization, bearer, your API key, and my API key is 12345. So go ahead and test out this command. It says healthy and model loaded. We can then check the available voices. That's just going to be the voices endpoint, still with 12345. It looks fine as well. And then we can just convert the voice. So we'll convert it to Andreas with the API key 12345. And the path to the source audio will be the following up here. So we'll just find the ElevenLabs clone, copy the S3 URI, and then it's going to be this URI right here. Great. So I'll just paste that in. So right there, and then just press enter. And then it says error in voice conversion. So down here, it got an unexpected argument models in process voice conversion. So it's pretty good we actually caught that. So it is being called down here, models equals models. And it is being called model right there. So we just need to call this models, and then it should work. So instead of model or load models, we'll just say models, because the models are being passed down. Sorry, the models come from up here. So models equals none, and this variable is then being set whenever the server starts up. So it should be reloading down here because we passed in the reload flag. And now we can just try out the command once again. And then see if the server says anything else. So it seems like it is generating, which is fine. And then I'll just wait for it to finish. So it should return a response in just a second. And it just returned a response right here. So it says it processed the request with the response 200, okay. And we do see a link over here as well. So I'll just press command and then click this, say open. And this should then download it straight to our computer. And I'll just open it up over here. And here's the results.
Some call me nature. Others call me Mother Nature.
So that is what was generated by the server. So the server seems to work fine with these new modifications. And I'm glad we tested it out. That is why you do it. If we hop into this folder right here, and then just look for seedvc outputs, we do see the exact same file up here. So it has already been uploaded to these two, it has been uploaded to the S3 bucket as well during the processing, which is perfect as well. So I'll go ahead and remove this .env because we don't really need that. And then we can build a small Docker file around this, just like we did in the other project over here. So we can serve it. So I'll go ahead and copy the dockerfile.api. Over here, next to dockerfile.train, we'll just copy this. And then we just need to change a couple of things, and then we should be ready to go. So first, I'll just remove a speak, because we don't really need that. Also, the following command right here. We need to remove this model path and also config path. We can still keep these, we just need to change this to seed VC outputs, just like we did inside this API folder. Seed VC outputs. The API key should just stay as it is, and this one should just stay as it is as well. We just need to change a couple of things. First of all, we need to check if FastAPI is being installed. It is not. So we will just say install FastAPI 2, because we do use FastAPI up here. Good. Going back, we just need to change these folders. So we'll need to, first of all, copy inference.py. So we have to think about what do we need to run this in a Docker file in another environment, like which ones of these folders and files do we need, and for sure we need inference.py. So we just copy that to the root of the Docker container. We also need modules, the folder, we'll copy that to modules. We then need configs, we'll copy that to configs. We need HF utils, so HF utils as well, and that is .py. Yep. And then we also need API.py. API.py right there. We also want to copy in runs. So we can say runs from right there. That is our fine-tuned model. And we also want to copy in the examples. Examples and examples. Torch home should be set to app/checkpoints, like that. And then Python path should be app, like that. And then we'll also just set HF hub cache. This is going to be app, checkpoints, and then HF cache. So checkpoints and HF cache right there. Cool. The API key will just leave right there as it is. And then we can try and build this Docker container and just see if it runs on our local computer right now. So I'll just open up a new terminal and say Docker build. And I'll actually just hop in here to container registry and just find the seed VC API, view the push commands, and then just find the Docker build right there. So then I can go ahead and just paste this in and just press enter. We just need to start up Docker though, so I'll just do that. I can do this by just opening up the Docker desktop app, but just so you know, if you do get this error, you just need to start Docker by opening up Docker desktop or doing it in the terminal. So with Docker open, I can go ahead and just do this again. I remember I need to specify what file I would like to do, so docker file.api. And it's because we are in checkpoints right now, it doesn't work. So we just need to open it from the root. And we just need to do a couple of things first, just a small injection right here. So first of all, we need to go into the style.js2 repository and then just grab these two environment variables from the environment file. We'll then hop into the dockerfile.api and then go down to env and just add these two as environment variables like that. And that should make sure that we are able to access the AWS secret access key right there, and also access key ID, since we aren't loading them from any environment variable files, environment files, like this one for example. So that should make sure we don't get an error as well. Also, I forgot to save over here the requirement file, so I'll just go ahead and save that, and then hop into the dockerfile.api, save that as well. If I go back here to style.js2, you might remember that we used a slim Python image as the base image when testing locally, since my MacBook does not have a GPU available, just so we could get around an error that happened. So we might want to do the same just when testing, just before we ship it to the ECR registry up here. So let me just go ahead and comment this out, and then just add another base image up here instead. So we'll say from Python 3.10 slim like this. Then I'll just save. Say Docker, make sure you're in the root folder, say Docker build -f, and we'll reference dockerfile.api. If we go over here to seed VC API, view push commands, and then find the following one right there, we'll just use that as the name. So we'll say -t to tag it, and then finish up with a dot, and then press enter. So if we just wait for this to finish, it should work once we start it up afterwards. It might take a while to build though, because it has to install all these requirements from requirements.txt, but it might take a while. It might take a while, so I'll just see when it is done. With the image built, we can go ahead and say docker run -p and forward port 8000 outside to 8000 inside the container, and then just reference the container name or image name up here as well, and press enter. This will just take a second for the model to load, for the server to load the model, and I'll come back when it is loaded. So with the server up and running, we can go ahead and just find the curl command. So we'll just run convert right here, and we'll run it to localhost because it is still localhost in the Docker container, to port 8000 as well, because we're port forwarding from 8000 outside the container to 8000 in the container. We'll do the regular things like we did when we were testing without the Docker container, and then just press enter. This should allow us to see the event being accepted in here in the server logs, and then hopefully being processed, and then return the URL over here in just a second. So first of all, we do see that the voice is being converted, which is great, and then we should hopefully see a response over here in just a second. So the request was just successfully handled, so we see that it was fully generated, and we see 200 as the request response. Over here in the simulated client, we can then press command and click the URL, and this should then download it to our machine. So I'll just go ahead and open up the results, and this is the final result.
Some call me nature. Others call me Mother Nature.
So it seems to work just fine. So now we have verified that it also works locally in a Docker container. So let us, as the last step, just go ahead and delete this, or just comment it out. And we can then just comment in this CUDA runtime again to make sure we can access the GPUs on the EC2 instance. And one thing I forgot was to remove the secret key and also access key down here before we build the image. So I'll just go ahead and remove these and press save. Open up the terminal again and say docker build -f dockerfile.api -t, and we would like to find the ECR registry over here. So seedvc API, view push commands, and find this name seedvc API. I'll just paste that in and press start, and then let this build. And of course we just need to spell this correctly as well. So dockerfile and build it. So now that everything has been built, we can go ahead and retrieve the authentication token and authenticate like this. So we'll just paste that in as well, wait for it to log in. And I just got this error right here because I tried to use the StyleCTS2 user to do this login. So what I did was that I just put in the same thing, but I just added the profile default flag, which points to the root user, so the one you set up with AWS when you did AWS configure. Or if you haven't done this, you can do this and set up a default user whenever you use the AWS CLI. So now the login succeeded, and I can go ahead and continue with this. So I already built the image. I just need to tag it now, and then just push it to ECR. So I do this and just wait for it to push. While the seedvc API image is being pushed, we can go ahead and take a look at the next feature. This is going to be the last feature backend-wise, and it is called make an audio. Right there. And then we would like to pick the following one right here, which is just called text-to-audio make an audio. So going down, first of all, we take this repository and just clone it. So I'll hop over here and just open up a new window. And then inside this window, I'll open a new folder, go under Documents, Repositories, and then find this folder right here, ElevenLabs clone, and open that up. This is the root of all our folders, so we'll just need to open up this new terminal. I'll just open up a one from the beginning and say git clone and paste this in. So now we have make an audio opened up. So we can just say open folder and open it up in a instance of Visual Studio Code for itself. Great. So going back over here, scrolling down, we see that we need to download the pre-trained models. So we need to download these three right here. So I'll open up Google Drive and also this link from Hugging Face, and just download these. So first of all, we need May1 full, so this one right here. So we'll just take this and download the file. So I'll press download and download anyways. And then I'll also download BigVan, unless it's over here, which it is not. So we'll download BigVan as well. And then just, if I can select this in some way, I can just press download right there. And now these two files should download. Over here, I'll just download the collab weights too. So I'll say clone repository and just make sure we have git large file installed. So I'll open up a new terminal and just paste this in. Paste in the next one right here. And just wait for this to clone. It is downloading a large file, so it can take a while, but we'll just leave this as it is. Great. So this will just take a while to download as well. But while this is downloading, we'll just create these folders we need. So useful checkpoints, for example. So I'll hop in here and just create a new folder. Oh, it's already there. So once this file or these files right here have been downloaded, I'll come back to you. All 3 downloads have now finished, and I've gone ahead and pasted in the zip file from BigVan and also this checkpoint, both into this useful checkpoints folder, as well as let this download finish as well, so ms-clap, and we just need to take this and just create a folder in here as well. So we have clap already with a configured YML, and we just need to, let me hop in here, we just need to put in a clap weights.pth file. So we'll just say clap weights, ms-clap, and then we'll take the 2023 model file and drag it into clap, say move, and that should be that. Lastly, I just want to unzip this file right here, since it doesn't say anything about the file being zipped. So I'll just hop in and open up this folder, useful checkpoints, in a new terminal. I'll then just find the name of this one and say unzip, and just let this unzip for a second. And now that that is done, we can just delete the zip file and just keep BigVan right here. And then we can go ahead and try out the actual model, see if we can get that to work. So hopping over here, what we can do is just find inference with pretrained model. We can copy this command, and I'll just switch around the panes for a second. We can copy in the command, and right now it's just a bird chirps, and this should be fine. So I'll just go ahead and paste this in. So right now it can't find Python, so we obviously need to just create a Python environment like this, and then just select 3.10 in my case. Install requirements.txt and just let this install. So the installation just failed. So going into requirements, and then we can see the same thing right here. If we just scroll up or down, we should be able to find the error. So right here it is. This thing doesn't look correct. So this definition of what version it's supposed to be. So what I'll go ahead and do is just actually remove these version specifications. I'll just keep librosa and numpy, but delete all the other specifications. We should still have our environment. Sorry, it actually didn't create the environment. I thought it did create the environment. We'll then just create a new environment, say delete recreates 3.10, and install the requirements again, and see if it works better this time. So the environment was just successfully created, and now we should be able to open up the terminal again, and then just run the same command. So it still can't find Python. I just need to restart the terminal and try and run it again. So we get an error right here when running the inference script. So we'll just copy this and do a full solution-wide search. So it was specifically within this file where it can't find this. So if we say rank 0 instead, it should work. Then doing the exact same thing over here. And in the other files where we expect this error to happen again. Right there. And then press save. It didn't save over here, so I'll just try and do it again. Save. And let it save as well. And also in main. And now I'll try and run it again. Now we do get another error, and this is the one we have gotten a couple of times already. That tells us we can load with weights only true. We do get the error right here, so we'll just need to find where the error happens. So right here at torch.load, we can go ahead and just add weights only false, like that, and just run it again and see whatever we get now. Alright, so now it says torch not compiled with CUDA enabled. So up here it says CUDA, so what we'll do is just say, replace this with CUDA if torch.CUDA is available, otherwise we'll use the CPU, because right now it'll default to the CPU, because that's what we have available on our MacBook. And then I'll just press start again. And now it just finished running after 1 to 2 minutes, and it says it generated a new audio file and saved it in results i.vav. So over here we can see results 0 and just try to play that. And that pretty much sounds like birds chirping, so that is a pretty good sign for this model so far. Good, so now I want to make this model an API. We aren't going to fine tune this model at all, because as I explained earlier, it doesn't really make sense. So we can just go ahead and close these down, and then the first step I would like to do is just create this file, api.py. So I'll just say new file, api.py. In here, I'll just go back to the seedvc repository and find the api.py. I'll copy all the contents and paste them in this api.py. Now to actually launch the server, we just need to add Bodo free as well as FastAPI, Pydantic, and also UVCon to the requirements.txt file, and just open up the terminal. Right there, say pip install -r requirements.txt and just let these install. Then we can just close down the terminal again and just remove this import from inference, because we don't need that. Going into the generate vav.py, we can just go ahead and find where the model is used. So down here in main, this is how we use it whenever we call the main function, call this file with the terminal. So we'll then just go ahead and copy this right there. And just instead of what we currently have in here, we can just load that in. So first of all, we'll need to initialize the model. So I'll just comment this out. And right now, we just need to import the following right here. So I'll just indent it back once more and just see if I can say add genvav from initialize model. That should import it up here like that. And now we should be able to actually use it down here. Cool, and so next up we are going to need the vocoder, so we'll just import that as well. And the device will need to just determine up here. So what I'll do is just say under, or right over global variables, maybe right under, I'll go ahead and say device equals CUDA if torch, and we'll just need to import torch as well. This way we can determine whether to use CPU or GPU based on whether you have one available. And now we have the vocoder ready as well. And then we'll just define these as global variables. So instead of models, we'll say sampler equals none and vocoder equals none. And that should make us able to access them down here by saying sample and vocoder after global right there. So sampler and vocoder. And I'll then just change a couple of things. So I'll say make an audio right here, so we know it in the logs. And also right there, and right there. Now we don't need any target voices anymore, so we can just go ahead and remove that, as well as the voices down here. Down here we can say vocoder and sampler. And the only thing you really need to generate an audio is just a prompt. So we'll say prompt string. And this will be generates. And we'll just need to use the correct request name. And then instead of models, we'll just go ahead and delete this target voice as well. Instead of models, we'll say if not sampler or not vocoder. And then we'll say models not loaded. Now we just need to take this from up here. So we only need this gen VAV call, and we can just paste it in the start of this try statement and uncomment it again. Now we just need to import this gen VAV, and then we can define the prompt that is going to be request.prompt. The DDIM steps you can find inside this gen VAV. So scrolling all the way up, DDIM steps default is 100. I'll just make this in a right pane like this. So DDIM steps default value 100, duration that is going to be 10, scale is going to be 3.0, and the samples is going to be a single one like that. And now those should be available as well. I'll just go ahead and remove this target voices too, and then hovering VAV list, we can see that it is a list. So going inside the method, we can just see how it was called in main. We see that they enumerate all the different results. So we'll just do the exact same. I'll go ahead and do that. And I'll just remove this logger and just paste this in. So I'll comment this out, and now we have it enumerated. So we can go ahead, I'll just call this I instead of ID. We can go ahead and first of all create this audio D, which is already done. We'll then just indent everything we need to make sure. So when thinking about it for a second, if we go back into gen VAV, why the reason that they even enumerate and the reason this gen VAV even returns a list is because you can define samples. So if you set samples to 2, for example, it'll return 2 different samples to you, so you have 2 to pick between. But because we just set it to 1 as the default up here, what we'll do is just go ahead and say results, or just audio, equals VAV list 0, because it'll always just be 1. So we'll just take the 0th element, aka the first element. And then we of course do not need to download the source audio, so we'll just leave this out. We'll also remove all the following things right here. And then check out how they wrote the file. So they use sound file that write. So we'll just do the exact same. Sound file, we can just add it up here. So we'll say import sound file as SF. And this should then be sf.write. And the save name we'll set to local path. And we'll just go ahead and remove this. And actually just keep this as the only parameter right now. This audio is going to be the VAV. And then lastly, the sample rates. We'll go ahead and import from gen VAV. And that should be it. Great. Now down here, I'll say error generating audio. And I'll do the exact same down below. And then just make sure we don't have anything that we shouldn't do. So VC outputs, for example, should be make and audio. Outputs. And then the rest of the environment variables should be fine as they are. We have the API key, the AWS specific ones, and then the bucket will be the same. So with everything in place, we can go ahead and just open up the terminal and say uvcon API app -- reload and just run this. And this should just start up the server and load the model for us. And then I'll just open up a new terminal, which we can use in just a second. I'll say to ChatGPT, generate a curl command to test out the generate endpoint on localhost, and just let it do that like this, and then I'll come back whenever this is ready. So the prompt has now been generated, and I'll go ahead and just paste it in right here. We'll need to set the API key, and I'll set the API key to 1, 2, 3, 4, 5. And then if we hop back into seedvc, we just need to do one more thing. We need to take the environment variable file and paste it in right here, just so we have the following environment variables ready to load into the context. So that means we also need to say pip install .env. And then up here we'll say from .env. And then we'll just say load.env as the first thing. And we should then be able to just run it down here. So since we put in the reload flag, when we ran it like that, it should reload the entire thing now because we just saved it. And now it is loaded successfully, so we can just go ahead and try out this command. So right now it says detail not found. I just had to do some debugging for a couple of minutes, and here's what I found. I'm just in a new terminal, so I found that I need to specify the port to use that specifically. So I say uvcon API app, but then I also specify the port flag. So just run the command again, just with this flag as well. So I'll just go ahead and press enter, and then open my new terminal. And then I'll just wait for this to finish. So the model loaded successfully. And in here, I just wrote lion roaring in the desert. And then I'll press enter. And inside the server logs, we can then see that something happened inside here. So that means that the request has probably been received and it is being processed as we speak. So the request was just processed and it says 200 OK, which is perfect. And then in here we see the audio URL. So I'll just open that up. And this should download the URL. So I'll just open up the results. And here is the final results. So that sounded pretty much like the result I was hoping for, which is great. Now I just want to build this into an API inside a Docker file, so we can actually ship this to the EC2 instance and get all 3 APIs up and running as soon as possible. So I'll just close down all the tabs and then hop back into seedvc, find dockerfile.api. And by the way, seedvc did upload or did push, so hopping into the repositories, seedvc API, we can see right here, it was pushed. So that should be all good. Now going into the seedvc again, taking the dockerfile.api, we can paste this in over here in make an audio and change a couple of things so we can test it out first locally and then push it to ECR afterwards. So I would like to just comment this out and use the following base image so we can test it locally. And then I'll just remove all of these copy commands down here except for one. So I would like to copy configs to .configs. I would like to copy LDM and I'll copy this to LDM as well. I would like to copy vocoder to vocoder. I would like to copy gen vav.py and just to the root. So like that. And I would lastly like to copy api.py to root too. Now I can just say copy and then just take useful ckp.ts checkpoints and just copy that into useful checkpoints like this. And then if we hop into useful checkpoints, we should have only the ones we need. Great. So lastly, the prefix is going to be not that one, but the following one right here, make an audio outputs. So I'll just paste that in. And then because we are testing, we can just hop into the environment file, still under make an audio, take these two right here, and just paste them in, just so we can test it locally before we ship it to the ECR registry. Now I'll just go to api.py and remove .env and load.env, press save, and then just build the Docker file. So I'll open in an integrated terminal, hop under make an audio API, view the push commands, and the following name right here. Make an audio API is what we're going to use as the tag. So I'll say docker build-f, and that is dockerfile.api. Then I'll say -t, make an audio API, and end with a dot, and just build this. So there was this little problem I just encountered where we said .py twice, so that is obviously wrong. And while we're at it, I'm just going to remove the following environment variables, torch home and hf hub cache. Just leave those out. And then just build the entire thing again. and hopefully it'll work this time. Alright, now that this is done, I can just go ahead and run it locally so we can test it out. So I'll say docker run, then just find the tag we used up here. So make an audio API, just specify the ports, 8000, 8000, and then the name, the tag of the Docker container. So we have something running already, so I'll just say docker ps-a, and then right now it seems like this is running, so we'll say docker stop, and stop that, and just see if we can run this other one again. And now it is waiting, starting up, and the model is loading. So let's just hop into this other terminal and find this command we used the other time as well. Now it's just loading a couple of things in the server right here, so I'll just wait for this to finish first. The server is now running, and we can go ahead and just run this command. Oh, I just pressed a button I shouldn't. We can go ahead and run this command, and it should then hopefully work. So let's see if anything happens over here. We do see some printouts, so that is great. And then I'll just wait for something to happen. Cool, so I just see it finished with 200 OK, so that is pretty promising. Going back here, we do see the audio URL as well. So I'll just open that up and let it download. And now I can just check out the finished results. And here it is. So some audio was generated, which is perfect. The prompt was, if I just hop up, lion roaring in the desert. I also created 3 more audio files with the same prompt, so I just ran the exact same thing 3 times, and here are the results. So as you can hear, there's definitely a large difference in how the quality of these prompts are. But it's pretty cool that you get different results when you run the same prompt a couple of different times. The next step is to actually go ahead and build the Docker file and then also push it to the repository up here, make an audio API. So first we're going to remove the following 2 environment variables and also switch to the correct base image. So we'll go ahead and just remove this. And that should be that for the Docker image. Over here we're going to also remove from .env and also this load.env, and just press save again. Now we should be able to open up a new terminal, and in the terminal we can say docker build -f dockerfile.api, and we can say -t, go into the make an audio API. Under push commands we can go ahead and find the name right here, and just press space and then press space again, and just finish with a dot. So when you run this, the Docker file will build, but I've already done this. After building it, you can go ahead and just run this tag command, so you can just paste this in right after building it. After doing the tag command, you can say docker push by copying the following command and pushing it like so. Cool, so here's how it looks when it has been done. So first of all, I built the Docker image. So I said docker build -f dockerfile, like I explained just before, and then we built the entire image. Then I copied this command in right here. So that is what then I copied in the tag command to tag it, and lastly I copied in the push command to actually push it to ECR. And then this is the finished result. So over here we see the image under latest right there, and then we should be able to create the Docker Compose file for actually starting up all of these Docker images at the same time. So start.js, seed VC, and also the make an audio API. So I would like you to go to VS Code, say file, new window, and then I would like you to open up the root folder. So I'll say open folder, go under repositories and ElevenLabs clone, and just open up this root folder right here. I'll then say open and create a new file, docker compose.yml, and in here we can define what happens whenever we run docker compose up. And this allows us to start multiple Docker containers at the same time, expose different ports, etc. So what I will do is just zoom in a little bit, and then I should be able to define this. So first I'll say version, that'll be 3.8. Next we'll define all the services, so these will be the Docker containers. So we'll say services, and I would like to define the style TTS2 API first, like that. And the image is going to be the image from over here, so style TTS2 API. So we'll copy the URI and just say latest after that. Now we can say ports. Ports are going to be 8,000 to 8,000, like that. And of course we just need to indent this so it's under the style TTS2 API. Next I would like to just say restart, and I'll say unless stopped. So this will restart the service if it crashes, for example, but if we do manually stop it, it will stop until we start it again. So that is what this keyword means right here. Next I can say deploy, and then resources. Oh, I'll just fix this. And then under resources, I'll say reservations. I'll just need to indent resources as well. Reservations. Then I would like to put in devices, and instead of capabilities, I'll say driver. And this will be NVIDIA. I can then say counts 1. And capabilities GPU, like that. And this just needs to be on the same indentation level. And this was the first service I would like to deploy. So now I'll just go down and copy it and call this seed VC API instead. I just want to use the seed VC API from up here. So that URI, and then just paste it in right here and still keep latest. I would like to use port 8001 though. And next I'll just copy this once again. And lastly, I would like to use the make an audio API. So I'll paste this in right here. Call it make an audio API and just leave the rest as it is. Or actually, I'll just set this to port 8002, such that we have different ports for all the different services. And now we're actually ready to start up the EC2 instance. So if I just go into AWS and search for EC2, I'll just open this up in a new tab and press launch instance. I'll just call this ElevenLabs clone, and then under AMI I can say PyTorch. So this one right here, and then the instance type will be g5.xlarge. Great. And then going down, we can just select a key pair. And then I would like to just say 100 gigabytes for the storage. And then I would like to create a new security group. So I'll go ahead and say edit. And then down here we can define some rules. So I'll just say ElevenLabs clone security group 1, like this. And just do the exact same for the description. And then SSH will just say is fine as it is. Custom TCP will allow from port 8000 to 8002, like that. And then for the source, we'll go ahead and say anywhere. Anywhere right here. And then the source that will not matter at all. So this will allow requests to the EC2 instance for these two ports, or for these three ports, so 8000, 8001, and 8002 from any IP. Then the last security group I would like to add is just HTTP. So I'll pick HTTP, and then just port range will just be this, and source type will just be anywhere as well. And then I'll scroll down to advanced details, and this looks fine, I just wanted to check. And then under IAM instance profile, I'll select my ElevenLabs clone EC2, and then just check that everything is fine. And that looks alright. So I'll just go ahead and say launch instance, and then connect to the instance, and press connect right here. So I think we started a little too soon, so I'll just go ahead and refresh just to make sure it's fine now. So I'd like to take the contents of the Docker file right here, just paste it in as a file. So I'll copy everything to the clipboard, hop in here, and then say nano docker compose.yml, and then just click paste. I can then say Control plus X, and then I can say Y, and then enter. So now if I say ls, I can then see this file right here. We can then also say cat docker compose.yml, and that shows us that we indeed have this docker compose file containing what we wanted it to contain. Now we shouldn't have docker compose installed already, so we can go ahead and just say docker compose just to verify that. So docker compose is not found, but I do have the command for installing it, so I'll just copy it from another screen, and this is the command right here, sudo curl -l, and then this entire string. So just go ahead and pause and just copy this command in to install docker compose, and then when you're ready, press enter. And we then just want to make it executable, so I have another command right here. This will make docker compose executable by putting chmod plus x, and then I'll just press enter. And now if I say docker compose, we do see that the command is available and we can use it. So let's go ahead and say docker compose up/d, so it's in detached mode running as a background process. And I'll just go ahead and press enter. And we aren't currently logged in, so I'll just go to ECR and find the following path right there, and then just use that to log in. So to log in, we'll say AWS, which is installed, AWS, ECR, get, login, password, -- region, US East 1, pipe, docker, login, -- username, AWS, -- password, -standard in, and then just paste in the URL which is copied from over here. Cool, so I'll just do that and press enter. And now the login has succeeded. So let me just try and say docker compose up again. And this will then pull the Docker files from up here. So it'll pull the following Docker file, this one and this one, because they are defined and required for it to start. So it'll start by pulling that from ECR, and then after they have been pulled, it'll try to boot up these Docker containers. So in a couple of minutes when this is done, I'll come back and we'll see what happens. It seems like it froze, so it hasn't moved for about 5 to 10 minutes and nothing is really going on. So I'll just go ahead and refresh this. First I'll say docker ps-a, and there's no containers running. Then I'll say docker images, and there's also no images. So what I'll do is just go ahead and say docker compose up and just try and do it again and see if it actually works this time. The pulling just finished, so you see pull complete for all the different images down here, and now the containers are starting up. So right now it should be running in the background. So if I say docker ps, we should be able to see that these were started a couple of minutes ago. And if I go ahead and open up this terminal in another tab, I can then grab the logs from this detached Docker compose running in the background. So I'll say docker compose logs -f, and this should give me the logs for all the different containers. So we see univcon running, and we see that at least, let me just see, uvcon, that is running both here, also right there, and also right there. And that corresponds to the free containers. Corresponds to the free containers that you see out here, Start.js2, Make an Audio, and also SeedVC API. And now for all of these, the models have also loaded successfully. So Start.js2, and then down here, let me just find this. This model loaded successfully as well, and this model also loaded successfully. So how are we actually going to interact with this Docker service, with these Docker containers running on this EC2 instance? And we'll do this with the public IPv2 address. So by clicking the EC2 instance right here, you should be able to see its public IP address. And then we can go ahead and make a curl to that via the terminal over here, for example. I would like to go into the ElevenLabs clone and then just generate commands. So I'll just go ahead and open up Copilot and then just say generate curl commands for the endpoints in each of the API, for all the endpoints in the API files. And then I'll just attach API.py here as well, and then also API.py. And then I'll say this is the public EC2 API address. And then I would like to also just attach the Docker Compose. And then we should have the curl commands ready in just a second. So I'll just open up a new terminal right here. And this is the one we're going to use to actually interact with the EC2 instance. Okay, so first of all, we have the health check for the style.js2 API. So let me just try and click this button. And we can then try and run the command. The API key is just 1, 2, 3, 4, 5 still. So we actually get a response, which is awesome. We can list the voices perhaps. Oh, invalid API key, so that works as well. We can list the voices, and we can also hopefully generate speech. So I'll say 1, 2, 3, 4, 5. And then let's see what happens. So we get this massive URL back. So let me just try and load that. So I'll open it and then just play the file. And here it is. Hello, this is a test. And it sounds like me, so that is perfect. Now let's just try out the other commands as well. So this is for the seedvc API. And the API key again, 1, 2, 3, 4, 5. The list voices. And then lastly, the convert voice. So we'll have to specify the key to the demo file. So we'll just go into S3 bucket up here. So I'll say S3. ElevenLabs clone. And then we can say seedvc audio uploads and just copy its URL. And then this will be, the URI. And then this will be the key in the S3 buckets. So going back, we can paste this in right down here. So if I just delete this and press enter, it should then convert the voice for us. And going into the EC2 instance, we should also be able to see the logs and see that something is happening. So we do see that the conversion was complete. So going back, opening up the link, and just playing the clip. This is what it sounds like.
Some call me nature. Others call me Mother Nature.
So that works as well. Great. Going back, let me just check out the Make an Audio API. First, we'll do this one. The model is loaded, and then we can generate some audio. So we'll go ahead and just say 1, 2, 3, 4, 5. And then down here, we'll say sound of computer keyboard clicked. And then just press enter. And here we have the URL. So I'll open that up and play the sound. So here it is. And that sounds exactly like how you would expect it to. So great, now we have tested all the different endpoints and they all seem to work. So the Docker files, we know there's nothing wrong with. So hopping into the logs right here, we can see all the different commands that we ran. So you can see every time you do a get or a post request, for example, you can see that it was returned. You can see the return code, and you can also see the logs that happens whenever these requests are being handled or processed. So for example, if you run a command and something seems off, you can also hop into this EC2 instance terminal and then just check the logs by running the command we ran up here. And then you can see what is wrong and maybe try to debug your way through it like that. Alright, so I've just clicked or marked my instance over here and then clicked instance state and terminate or delete instance to make sure that we are actually terminating and deleting our instance. And then whenever we have built out the front end and we need to test it end to end in production, we can go ahead and just run Docker Compose up in a new container, because it takes a couple of minutes to set up the backend, so it's not that bad. But it does save us $1 per hour until the front end has been built and we're ready to test. So EC2 instances can be quite expensive if you work with the ones with large GPUs, at least like we do. So please make sure that you turn off your EC2 instance, and you don't just need to press stop, you need to actually press terminate. This is the only thing that will make it not spend your money anymore. Okay, so I forgot one thing we need to do before moving on to the front end. So I've opened up the style.cts2 repository and then found the API.py file right here. Going down to the endpoint called generate, so right here, remember that we created this function called text chunker, breaking the text into chunks that can be processed next to each other and then be put together as a sequence to make the entire audio synthesis. Well, if we take a look inside this loop that loops through all the chunks, we can see that we run inference on the chunk and then append the chunk to audio segments, but then we upload that chunk to the S3 buckets right here and then return straight away. This means that we don't really process more than one chunk because this is done inside the loop, so we really want to move this outside the loop such that we only write the full audio right here containing all the different audio segments. So what I'll do is just take this code right here and do an unindent. So I'll say shift and then tab at the same time. And then I'll move this in a bit. This means it'll happen outside the loop. So we append all the different chunks to this audio segments. And then after that has been done, then we concatenate them, write them to the file system, upload them to the S3 bucket and return. So that's one thing we need to do. So I'll go ahead and press save and open up a terminal over here. And then I would like to just go into my ECR and find the style.cts2 API, view the push commands, and just do this. Follow them. And also the Docker build one. And I got this error up here, so I just had to specify the default flag, so profile default, to make sure I logged in with my root credentials that I set with AWS configure. Now, going back, we'll just take this Docker build again, and copy it in, and then we'll set another flag, .f, and -f, dockerfile.api, and press run. And if you get this, you just need to run the Docker client, the Docker daemon. So I'll just go ahead and run it again, and now it should build. And because if you go into the Docker file, and because all of this has been ran previously, it has been cached, so it'll build very quickly. Now the next thing we need to do is just tag it and push it to the ECR registry. So we'll tag it and go ahead and push it up. Great, and just wait for this to finish. In the meantime, if we go in here, I can search up S3. We'll need to set up one thing before we can move on to the front end. So ElevenLabs clone, permissions. We'll need to scroll down to the cross-origin resource sharing and press edit. So whenever we upload to the S3 bucket or download from the S3 bucket, we might encounter an error unless we set this. So cross-origin resource sharing is a security feature implemented by web browsers that restricts web resources from interacting with resources from different domains. So we'll need to specify what domains are able or should be able to interact with the bucket. So we'll need to specify a configuration. So I'll start with an array and then put in an object into this array. I want to put in the property allowed headers. In here, I'll put in another array and just put in the following star right there. And then I'll also just copy this and add it to a line right under. This I'll call allowed methods. So these are HTTP methods. I'll put in gets, copy that. I'll also put in puts, post, deletes, and lastly head. Good. I'll just take this entire thing and copy it, paste in and call it allowed origins. So this is who we are supposed to call it. And I'll just set it as a star for now, just so we can test it locally. But ideally you would like to set this allowed origins to only the domains or the origins that are supposed to be able to interact with the buckets, and also only allow the methods and headers that you actually do need. This is just to get it up and running quickly. So next I'll just say expose headers. In here I can just define a new array where I put in e tag as the first one, and then the next one is going to be x, amsets, meta, custom, header, like this. We'll then just go ahead and press save changes. And now this should be set up as well. Cool. So now we just need to wait for this to finish, and whenever this is done, we can go ahead and start with the front end. Now my layers have been pushed, the image have been pushed to ECR. So under container registry and latest, we should be able to see the latest time. So that is right here. So with that out of the way, let's go ahead and build out the front end part. We have now finished the first part of the video, and I'll see you in the second part. You can find the link in the description or on my channel.